Okay, so should we start? Okay, let's get started. Welcome to day 2 of the summer school. My name is Manish Gupta, and we will start today's session. Okay, I work at Microsoft, so let me actually first start by spending maybe 5 minutes about what do we do at Microsoft, and talk a little bit about that, and then get started about today's session. Okay. I work at Microsoft Hyderabad. Microsoft has multiple centers in India, but two of them are popular, Hyderabad and Bangalore. Together, they are called as Microsoft Development Center. Well, India Development Center. We don't really develop India there, but anyway, I mean, it's called Microsoft India Development Center. Right? And we work on a whole bunch of things, Bing search and ads. Now, some of you may know about Bing by now, right? And it's a search engine, right? We also work on Azure, so which is Microsoft's cloud platform. We work on the Edge browser, Windows that everyone surely relates with, Xbox. There is also work on security and, of course, work on Microsoft Office, which goes on in these Microsoft Hyderabad and Bangalore offices. So traditionally, people link Microsoft with a software engineering company, but well, that's not completely true these days. We are an AI-first company as well. Besides, of course, other companies in India and outside, right? So I work in the Hyderabad office, and particularly in Bing. The Bing in Hyderabad is also called as Search Technology Center India, which is basically STCI, right? In STCI, we work on very interesting areas, as you see mentioned here. So specifically, we work on Bing search, specifically in these areas. So query suggestions is an area where the idea is to suggest things to people, recommend things to people. These could be auto completions. So the drop downs that you see as you type a short prefix. So a query auto completion. These could be people also ask. So you might have observed that when you query, you also get this small block which contains a few questions that are also related to the query. So that's called people also ask. And the third one is related searches. So essentially, which is probably one of the oldest modules on search engines, right? So essentially, if you search for something, what are other related queries? Okay. So that's that. So that's basically about query suggestions. We also work on improving the relevance of the results which are shown for particular Bing domains, like sports, health, travel, technology domain, and so on. Okay. We also do things like quizzes. So if you have been to Bing, you would also see quiz sometimes, and those quizzes are also designed in India. We also pump things called as on this day. So what happened on this day? So does anyone remember what happened today, 41 years back? No, no. So fun fact, India won the first Cricket World Cup, right? So that's that. That's what happened on this day today, right? Cricket fans, no cricket fans. Of course, there must be cricket fans, of course. Yeah. We also work on Bing Copilot. So Copilot, essentially we do responsible AI and safety there. So ensuring that the Copilot does not entertain any offensive or all kinds of random queries from users and does not really reply to them in that manner, right? Uh, we do type ahead completion, also called as ghosting on Copilot, which basically just means completing rather than showing a drop down in that sense, right? Of course, we are in India, so we work on Indian languages. We do Indian language translation. So we support all 22 Indian languages recognized by the Indian Constitution in terms of translation from those languages to English and English to those languages. And we are now also looking to partner with various institutes on supporting tribal languages like Gondi. So very soon we'll actually start supporting those also on Bing Translate. So we do speech to text and text to speech as well. So no longer you need to fake your voice to show off American accent, right? To ensure that that these phones understand you, right? You can actually talk in your natural accent and they still understand you, right? So that's that. And you can also generate speech. So essentially, if you wanted to read out text in a particular demography, so particular age group, particular gender, and particular region, you can actually do that thanks to the work that we do, that our team does in this area, right? We work on speech dubbing. So essentially, if you open a YouTube video on Edge and you want to actually hear it in Spanish, you can actually do that, thanks to the speech dubbing that we do here in India. Okay. Lastly, we also own the web index. So essentially, the web index at Bing is huge as well. So trillions and trillions of documents out there. That thing, how do you manage the inflow and outflow from that index? Large-scale distributed storage and serving platform to support that is also what we do here. That's a little bit about Microsoft. Now, I mean, of course, what I talked about is the product perspective, but hey, we are all from academia, and therefore, it's important to talk about what do we do academically. So in the past 5 years, the Bing Technology Center in Hyderabad has put out 105 plus publications, which includes papers and tutorials, many of them with academic collaborators, represented at super awesome conferences and venues that you see there, right? So on the left side, you see what we do. So of course, we build models, big deal, right? And we actually do a whole bunch of language modeling, as you see there, coming up clearly. So that's basically the kind of things that we do from publication standpoint. Okay? And that's the kind of venues that we publish at from publication standpoint, which is so relevant to the crowd here. In short, I mean, once you're done with your PhDs, that's the place to be there. Okay. So I'll also talk 2 minutes about Microsoft Academic Partnership Grant. So this is a grant that we started at Microsoft 4 years back. So as part of this grant, the main goal for the grant is to build a strong industry academic collaborations. I'm the director for this grant. So in the sense that I've been leading this program for the past 4 years. We work on problems leading to research as well as product impact. So the idea has to be a win-win idea here, both for Microsoft and for academia. So while students basically get publications, what Microsoft gets is something that is either directionally important to understand where the product should go, or essentially leads to some deliverables that can make it into the product directly. In fact, to think about it, Microsoft Academic Partnership Grant is one of the most competitive grant programs in India. In 2021, we had like about 21 proposals. In 2024, we had like 95 proposals, of which 6 are funded. So basically, the acceptance rate is 6 on 95. So that's how competitive it is. Right? These proposals come from various institutions in academia. Of course, we put out call for proposals, and we get these proposals, whichever align, high quality proposals that align with our areas of work, essentially get funded. Saptarshi is here. One of his proposal was also funded, last year. So that's that. Right? So we made 16 grants in the past 3 years. The funding program basically involves like a rigorous 3-stage process. Both technical oriented as well as business oriented, to ensure that the research work that gets done is also aligned with product interests at Microsoft. Yeah. They are somewhere in between. You're right. So in the sense that they're not really like a specific problem only, and they are not really as open-ended as, hey, I will work on query auto-completion, but it is somewhere in between. But it's not really strictly limited to a particular problem only, that, hey, I'll work on a particular kind of auto-completion only and so on. It has to be both. So it has to be, solutions have to be technical, because this is basically, a good proposal is something that leads to multiple research papers, as well as something that influences the product. Okay? So it's an academic program, so it has to be paper publication oriented first. Right? So this is the main criteria. But at some point, our business folks also weigh in, and then they say, oh, this is too academic, too theoretical. I can't really think about any product around this. Then we'll not basically, consider that one. Right? So the grant money is 15 lakhs per grant, and we have been doing this for the past 3 years. We are in the 4th year right now, and we have made grant announcements. In fact, so the work actually will start in July, just a week from now. Okay? And again, this has led to several publications, several collaborations across institutes, several topics on which we have collaborated. To know more, you can write to me or to this ACAD grants at service.microsoft.com. Okay, so now coming to myself, I graduated from UIUC with a PhD in 2013, moved back to India, and have been working at Microsoft since then, past 11 years. I also work as a faculty at IIIT Hyderabad and a faculty at Indian School of Business, Hyderabad. Okay. I am based out of Hyderabad. Right. 100 plus publications and a good number of citations. I have been a part of several nice program committees. These are my areas of interest as of now. So essentially query auto-completion, because that's what I work closest with at Microsoft. But I also work on areas like dialogue systems, multimodal NLP. Multimodal NLP is actually very, very interesting. So very recently, we got this paper accepted called Circuit VQA, where the idea is that given electrical images, we want to basically answer questions related to those images. So, what is the reading on the M meter, or what is the, how many resistors do you see in the entire circuit, and so on. So those kinds of things. Sorry? Oh, what kind of circuit images? Simple ones, man. So, not really, like, I won't even call it PCB. It's a simple circuit diagrams as you would see in a second year, third year BTech book. Okay, so that's that kind of stuff. Well, some of those images actually have up to 50 different components. So it's not too simple as well, but not too complicated as well. I won't say it has like, so VLSI done and very, very small little tiny transistors. Not really, they're visible, more like second year, third year. No, it's a book-based image. Yeah, it's a hand-drawn stuff or a schematic image, not a real image of a board. Yeah. Right? And that choice was dictated by the kind of data set we had. We didn't manually create it. Okay. But anyway, and there are other fancy things like comic dialogues. So everyone loves comics. So basically, let me hide a particular bubble and ask you what this guy would say. So basically saying generative AI to essentially creatively come up with the humorous text in the context of images, other images in the frames, and what the other characters in this image have said, and so on. Okay, so that's comic dialogues, right? So we do all of these fun, interesting projects. This one, cognitive neuroscience, is about trying to understand the way brain works. This is like very, very different. So very different from most of NLP, but still it is NLP because after all, as part of NLP, we also need to understand how our brain processes language. So in fact, other interesting questions are like, if you're basically trying to use your brain to do image captioning, if I take this image and I try to understand what this is in terms of text, then which part of my brain areas are involved? So which brain areas are multimodal in nature versus which brain areas process text, and then particularly syntax versus semantics, and so on. Okay? That's the work that we do at cognitive neuroscience. So interesting idea to motivate you to think about it is, can I design futuristic interfaces where I would just think that I need to send an email to Pawan Goyal, and automatically the email is typed and sent to Pawan Goyal, right? So basically controlling interfaces using your mind, basically. That's the North Star for cognitive neuroscience as an area. Right? So yet another kind of area is extreme classification, where the idea is to do extreme classification. So let me again motivate why this is important. So all of you know about classification, obviously, right? So binary classification, multi-class classification, right? So how many classes have we dealt with so far? Maybe like 10 classes. Web pages, you want to figure out how many classes, whether it is a science or a travel or a health or a sports web page, and so on. Okay. But what if the number of classes is 1 million, right? So basically, so for example, given a particular ad, I want to figure out what are the good keywords associated with this ad. And my label space is like millions of queries, millions of possible queries that this ad can relate with. Okay? So what is the number of classes is like so large, right? So that's basically called as extreme classification because the number of classes is extremely large, right? And well, I partner with the MSR particularly on this one so as to solve these kinds of problems. Bing ads. So, Bing ads basically where, in fact, a whole bunch of extreme classification solutions are shipped as part of Bing ads, where we want to, and making billions of dollars of revenue for Microsoft right now, where we want to actually figure out what are the keywords that can relate to this ad. So, of course, the advertisers provide some keywords, but they don't provide an exhaustive list, right? And we can actually do a broad match, as it is called, and then match some random things. So we want to avoid that and improve the accuracy of matching. Oh, absolutely. This is the accuracy is improving over time, right? So essentially, yes, the systems have been around since the earliest ad exchanges, right? But systems have been improving over time. Everyone wants more ROI. So that's that. Okay. We also use it for other purposes. So for recommendation scenarios where the user has typed a query prefix and you want to then suggest a suffix, completion, right? And then you can suggest completions as intents from an intent space of 1 million, right? So then you want to figure out, so cheap Nike, if this guy typed cheap Nike, now what can this guy type later, right? Shoes, maybe, right? So, or pants or whatever, right? So essentially then there is a search space of about 1 billion and you want to choose one of those or a few of those, right? Those are other applications of extreme classification. Okay. So I'm extremely thankful to collaborators. So, IIIT Hyderabad, because I'm a faculty there and it's just 3 kilometers away from Microsoft. So it just makes it super easy. IIT Kharagpur, several folks that I've worked with at IIT Kharagpur over years, IIT Delhi, IIT Hyderabad, Jodhpur, Patna, and more recently, INRIA, MPI, and Bonn as well. Okay, so with that, let's basically get started with the topic that we are here for. Any questions so far? Please feel free to ask questions, stop me at any point. Okay? And he has been doing it, so thank you. Yeah, please keep doing that. Okay, awesome. Okay, let's get started. So Srivatsan met you yesterday, right? And he talked about word embeddings. I won't bore you by talking about the same things, but I would build on top of that. Okay. So, why do we need word embeddings? We need word embeddings because neural networks don't understand words. They only understand numbers, right? So you can't feed words to neural networks. You have to come up with some numeric representation. The first representation one could think of was one-hot encoding, things of this kind, where if the vocabulary was just this much, sure, you could basically say, oh, since the vocabulary is 11 words, I will have a 11-sized vector for each of those words. Okay. So if the king is at index 0, index 0 is 1, everything else is zeros. That's called one-hot encoding. Okay. Several problems with this representation. One, this representation is crazy large, right? So essentially, if you had like 50,000 words in your vocabulary, 50,000 squared is the size of this embedding. Okay? So 50,000 squared is the size of this embedding. Okay? Now, the second biggest problem is that not just this is large, but it is also wasteful. It's basically crazy sparse as well, right? So in one vector, there is only a single one. Everything else is just zeros. Okay? And the most important thing, it is meaningless. So it cannot really capture any meaning. So for example, looking at these representations, I can't say that king and man are more similar than king and water, right? There's no semantic information because you do cosine similarity, cosine similarity is 0 for any pair of vectors. Make sense? So no semantics as well. So pretty useless in that sense. 2013, fortunately, Google came up with word2vec, right? So, and you understood how word2vec works yesterday, right? So a word is known by the company it keeps in some ways. So a word is sort of, the meaning of the word is captured by the intents around it, right? So, I used to do Sachin and Virat, but now for today I can do Sachin and Rohit, right? So Sachin hits sixes, Sachin hits fours, Sachin represents India, Sachin is god of cricket and so on. And then similarly, Rohit hits sixes, Rohit hits fours. Well, probably not god of cricket, but anyway, right? So, several of those words match a lot. And therefore, you would say Rohit and Sachin have similar meaning, although that's not there in any dictionary for that matter, right? So that's that. So that's the word2vec embeddings. And Google trained word2vec embeddings as 300-dimensional vectors using 100 billion words from a Google News corpus. So pretty large corpus, pretty generic corpus in that senses. And they were able to train these word2vec embeddings for 3 billion words and phrases. Now that's interesting, right? 3 million words and phrases. Okay? How many words does Merriam-Webster's English dictionary have? Any ideas? About 4 to 5 lakh words. So that's not too much, I mean, fortunately, from a vocabulary perspective. However, our vocabulary is not just limited to Merriam-Webster, right? So in the sense that Sachin and Tendulkar are not going to be there in Merriam-Webster's dictionary. Okay? So if you basically look at that, what Google did was also released n-grams. So they actually released popular n-grams extracted from their Google Books corpus. Okay? Of course, they deleted those which occur less than 40 times as spelling mistakes. So, and if you look at 1 grams, the number of 1 grams from extracted from their English books was about 13 million. So 13 million possible 1 grams exist. So if you care for phrases, then there is just crazy too many. Okay. So they basically still, worked with 3 million of them, and they made these 3 million ka embeddings publicly available. But you can imagine, baki 10 million ka kya, So that is a problem. So the remaining 10 million do not have any representations in this model. Okay. But the good part is that it is super easy to train, super easy to load, and super easy to use. Just use this library called Gensim, and 2-line literal code, literally 2-line code, so as to basically load these embeddings and use them for your purpose. The beauty is that they are semantically oriented. So in the sense that they carry meaning in them. Right? So essentially, they are not as dumb as nowhere as close to as dumb as one-hot encodings. They are meaningful. Okay. So they're meaningful. I mean, in the sense that you could do vector of king minus the vector for man plus the vector of woman, and you can get the vector for queen. Okay. So or close to the vector for queen. Okay. So basically, they captured meaning. In 2013, when Word2Vec came in, Word2Vec was crazy popular. Why was it popular? Because before this, all people had were TF-IDF representations. All they had semantically was SVD representations. But this was way better, way more accurate compared to any other representation. So how did people measure accuracy? How would you measure accuracy for such a embedding? How good an embedding is? Any ideas? How would you measure how good an embedding is? Cosine similarity between between similar meaning words, right? So that's one way of measuring embeddings, right? Measuring the goodness of an embedding, right? But that can be measured only for words for which you know they are similar, right? For example, you cannot measure similarity between India and Narendra Modi, right? Because you don't know. No dictionary basically says India and Narendra Modi are similar, right? So you can basically only figure out for literal for dictionary words whether this works nicely or not. But you cannot figure out for world knowledge, whether it works nicely or not. Right? So the way people did that was to actually create a whole bunch of analogy tasks. Remember in school, in some scholarship exam, you would have solved these tasks like India is to rupee, Sri Lanka is to what? Right? So that's the kind of analogy task that people built a large set, and then accuracy on that analogy set, analogy tasks, is basically the way people have been measuring the goodness of these embeddings. Of course, people have been now measuring the goodness of embeddings based on extrinsic evaluation, in the sense that evaluating how good they perform across several NLP tasks. But in 2013, the way to show that they work really well is to basically evaluate them on analogy tasks and show that they really do those tasks nicely. Yeah. But for letters and symbols, UTF and Unicode are already available. Why nobody values them? Yeah, UTF and Unicode SKI values are also available, right? But they don't carry any meaning, right? So SKI value, how much meaning does it carry? So, Sachin, SACHIN, what do you do? I mean, take the SKI value for capital S and A and, or Unicode value and then add it up. No, it doesn't carry any meaning. Yeah. So therefore, you want some representations which can capture. Okay, so that's great. Any other questions, folks? Any other questions? Okay. So what are the problems that you see with these word embeddings? Any problems? Oh, they are really awesome, actually. So you do, good, or rather, you do better minus good plus bad. That actually gives you worse. Almost the embedding for worse. Okay. You do all kinds of these analogy tasks that you have in mind, and they work reasonably fine. So what is the problem with them, though? It won't capture context. Exactly, right? So basically, Apple is a company, Apple is a fruit, Apple is a band, or sabka meaning is captured in the same vector, right? It's a confused vector, right? So it doesn't capture context. Very nice. Okay, what else? What else? What is any other problems? Huh? Yeah, oh, that's another problem. Yes, you cannot really. So you needed something to represent sentences. Well, one way to do that is called bag of words representation, which basically means that, India is a great country. Take the representation for India is a great country. Sabko add karo, average karo. That's your representation for the sentence. But clearly, things people could do better in the future after 2013, right? Yeah, so Word2Vec could help you get a representation for a sentence, but not natively. So basically, there could be better things. Yeah. What else? What else? What else is a problem? Any other problems? No, but that is similar to what he said earlier, right? I mean, multiple meanings of a word, so multiple senses, and ideally you would expect multiple vectors for each, one vector per sense, right? Or one vector per contextual meaning. Is that what you're saying broadly? So then that is similar, right? Okay. Yet another problem is essentially, as we discussed, for a whole bunch of words, there are no embeddings, and they're called out of vocabulary words. Okay, out of vocabulary words. So what do you do about them is the question. Okay, so and there are other problems, like for example, when you're doing code mixing, right? So as you would observe, many times I would end up using Hindi words in my speech, although I try to minimize that, right? And most of us, when you type messages, you have at least two languages as a mixture in India, right? Clearly, we are all bilingual in that sense, at least, right? So when this happens, what you expect is that the embedding for the word pani and the embedding for the word water should be as close to each other as possible, so that you can actually process code mix text seamlessly. Okay, but Word2Vec does not allow you to do that, because Word2Vec is typically trained on some large corpus in that language, and getting code mixed corpus is not super simple. So essentially, how do you align embeddings across languages so that they can, they are in the same space? Of course, you can train Word2Vec in Hindi and in English separately, but they won't align. So that's some of the problems with Word2Vec. Specifically here, I'll talk about this problem where you do not have representations for several words, out of vocabulary words, as they are called, right? So people came up with this idea over several years of using subword embeddings. So they said, hey, let's ditch words, let's think about subwords. Okay? So, and then they said, hey, the number of words may be very large. Okay? And by the way, 3 million is also pretty large to store. So, I mean, 3 million multiplied by 300, what's that? That's basically about a billion, right? And if I basically want to store like, even a 16-bit representation, 16-bit representation for each of those, words, for each of those numbers, right? 16-bit representation, I need like 2 bytes. 2 bytes for about billion. So billion is giga, right? Billion is 10 to 9, so that's giga. And 2 bytes, so 2 gigabytes. अब किसको चाहिए WhatsApp app with like 2 gigabytes of RAM, right? Nobody wants WhatsApp app with 2 gigabytes of RAM, right? So essentially that's huge. So people, I mean, and the bigger problem is that it has so many out of vocabulary words, right? So 300 million is, 3 million is not enough. So, oh, sorry, my computations had a little bit of a problem. But you get the point. We get the big point, right? Sorry, it was 3 million, not 300 million. But anyway, right? So the point is that even if you basically are able to have embeddings for 3 million things, they are not enough, and they take a lot of space. So people came up with subword embeddings saying that, hey, we'll have a very small vocabulary size, maybe just 30,000, 50,000, something like that, and still be able to capture every possible word. We really don't need, there will be no out of vocabulary words, okay? Because we'll actually store representations for tokens or subwords rather than full words. Okay? So I'll never store a representation for athazagoraphobia, whatever that is, right? But I'll actually break it down into 4 subwords and store representations for each of them, such that popular words, such that so how do I break this down, right? I break this down using a very simple principle. Frequently used words should not be split into smaller subwords, while those which are rare should be decomposed into meaningful small subwords, meaningful frequent subwords. Okay. So how do you do this? I mean, to be able to do this, they actually took knowledge from compression literature. So anyone has taken a compression course? Compression course? No one? No one has done compression course here. Some of you might have done, right? Yeah, I mean, so it's fun to, by the way, go and read how does zip work, right? So essentially the zip utility that we use, how does it work? So they practically did similar things. Of course, that has much more involved stuff, but a very simple way of compressing things is as follows. You take a large string like that, okay? You try to figure out those things which are frequent. For example, AA is very frequent here, AA, and so on, right? So you replace the frequent ones with another symbol. So, not like the capital Z, but some other symbol, right? Of course, it looks like a Z, but, some other symbol, out of vocabulary symbol in that sense, right? And then, similarly, at this stage, you do this recursively. So you try to figure out, oh, AB is repeating. Okay, let me replace by that one. And then ZY is repeating. Let me replace that one. Okay. So what I end up getting is this table, so which basically says that, hey, I have now totally 3 tokens from here. Basically what tokens? AA as a token, AB as a token, and then AAAB as the 3rd token, and then this is my 4th subword. Okay, so I'll be storing these 4 subwords, okay, rather than actually storing the original string as a word by itself. Okay? So that's that. And of course, I do that over a very large corpus. So over a very large corpus, I try to figure out which pairs of characters are frequently repeating and then merge them. So these are merge rules practically. Okay? So now the way I form my vocabulary is to say that, hey, all possible characters are going to be first there in my vocabulary. So how many possible characters are there? Well, I mean, all characters can be represented using 1 byte. So let me just have a base vocabulary of 256. So basically saying, okay, if you give me any word, let's say Sachin, I can always break it down into SACHIN, 6 characters. And I will have representations for all 6 because they are a part of my base vocabulary. Okay? But beyond that, so there are that's just 256. So 256 base tokens. Okay? But beyond that, I can actually do these merges, right, based on frequency. And as many merges I do, that's the number of tokens that I end up with. As many merges I do, that's the number of tokens that I end up with. They particularly choose GPT-2 basically uses 50,000 merges, and that leads to an overall vocabulary size of 50,000 to 57, which includes the base tokens also. Okay? Yeah, we don't have the context part taken care of here. Okay, don't worry about. Yeah. Oh, that's a good question, right? We can take it later. Or rather, you did discuss yesterday RNN Celestians and things of that kind, right? Now, unfortunately, they are not pre-trained models, but people came up with something called as ELMO, right? So, which is a pre-trained model, right? Which also helps you establish context. And more today, we'll talk about other things like GPT-2 and BERT, which helps establish context. Okay. But the first problem that we are tackling in this part is basically how to handle out of vocabulary words. So abhi kya hai ki there is nothing out of vocabulary. Why? Because give me any word, I'll tokenize at worst into characters. And all characters are already a part of my vocabulary. So by definition, I can't be ever out of vocabulary. Make sense? Okay. And then the popular subwords are going to be surely there as it is. So for example, ing, phobia, I'm not going to split them because they were so popular that they led to so many merges that I actually included them in my 50,000 vocabulary. Okay? So this is basically called as byte pair encoding. Okay? So basically because you're talking about a pair of things and you're merging them so as to basically get your vocabulary. Okay? So this is the popular BPE tokenizer. Okay? So when you use these models on Hugging Face, they basically come with some tokenizers. They don't take words as input, they take tokens as input. Okay? And the way these tokenizers work is as follows, right? I mean, essentially BPE tokenizer. Okay? Now, people at that time were coming up with several subword tokenizers. How do we check our tokenizer is good? Yeah, great question. I don't have a very good answer there. Yeah, there's no good answer. I mean, it basically just token. I mean, there are some answers. So, one should not, good point. Yeah, I mean, I have some answers, but maybe not. So I don't know what these papers did to prove themselves as awesome. So some answers are as follows. Now, if you really go to GPT, the well-renowned Chat GPT model, right? You go and you try to generate an essay on Indian Independence Day in Hindi. So what it does is to generate token by character by character. So basically, it generates the first character, and then it generates uske upar ek matra, and then the second character, and so on. Okay. Now that happens because its tokenizer essentially had so little Hindi language data that it cares for every character as a token. But no merges happened there. Okay. Now, which basically has an implication. The implication is that the inference time is much larger for those languages. Okay. So how do you know if a tokenizer is good? If it does not have too many small tokens, because if it has too many small tokens, then the inference latency is too large. Okay? And the time it takes to generate a 300-word Hindi Indian Independence Day essay is going to be way larger, about 4 to 5 times larger compared to an Indian Independence Day essay. So before GPT-4o came in, where basically they reduced that stuff, they reduced that latency stuff for Indian languages. Right? So that's one way of figuring it out, right? Yeah, from an accuracy perspective, I don't have a good answer there. Yeah, from an inference latency perspective, of course, you prefer larger tokens. Okay. Oh, can someone claim that the tokenization was good because the overall results were good? Yeah, I mean, agreed. I mean, but that is typically not seen. I mean, I've not seen papers which say, oh, my accuracy is awesome because the tokenizer was good. Although, I think I should look at these papers. These papers should have basically made some claim why, why they have proposed this new tokenizer and so on. Okay? It's just that I don't know how do they claim that. Yeah. Okay. Okay. But what I am going to do is to talk about 4 tokenizers because they are popular. Okay, so that's the take. Okay, okay. Again, so we talked about BPE. The next one is word piece tokenizer, which is popularly used in BERT. Okay? The vocabulary size is 30K, but how do you reach to this 30K vocabulary size? Of course, the base vocabulary is there. I mean, you have basically brought in all of your individual characters. And remember, right now I'm just talking about English, so I'm not talking about multilingual tokenizers in that senses. Okay? So they also initialize the vocabulary to include every character, but then they also have merging rules, and the merging happens in a different manner. So the merging, rather than frequency-based merging, which is done in the previous tokenizer, here the merging is done using point-wise mutual information. Okay? So which is just this. Okay? So that's another name for this fraction. So basically, you will merge 2 characters, let's say U and G, if the probability of them occurring together is much larger compared to the probability of them occurring individually. So probability of U and G occurring together, I mean together in the sense adjacent to each other, is much larger than them occurring not adjacent to each other. So individually, if this is the largest amongst any possible two characters, then you merge these two. Okay? So then you merge these two. Okay? So just the merging logic differs, but otherwise it's just the same way of computing the word piece vocabulary. Okay? So that's that. Now with these things, with both of these tokenizers, they sort of assumed that yeah. In fact, yeah. I mean, in fact, both of these assume that you start with the base vocabulary and you essentially do merging and merging so as to get those merged tokens as well, okay? And therefore create further vocabulary. Unigram subword embedding is yet another way of doing things where you actually start from the other way around. So in the sense you would say that, hey, let me take like full words and put them in the vocabulary. Let me also try to put all kinds of, small parts of it, small parts, randomly selected small parts and put them in the vocabulary. Okay? And my vocabulary size is then going to be humongous. And then let me start deleting some of those words because that does not really change a particular objective function. Okay? So what would you do? You would start with a large set rather than starting just from the base vocabulary of characters. You start from a very large set and you start deleting things so as to come up with a reduced vocabulary size. So they approached it from the other way. Okay? Now, how would you delete words is the question. So here, rather than merging, they basically delete things. Okay? Delete long words. Okay? So I would say delete long words, but the idea is that you want to delete words such that some objective function is optimized, and I'll talk about that objective function. Okay? So at each trading step, what do? You want to delete something. And how do you delete something? Well, you basically figure out the log likelihood given the current vocabulary over a large corpus. So if you have a very large corpus, let's think about it like a document, right? You can compute the log likelihood for the document based on the current vocabulary. Okay? So what does log likelihood mean? A unigram log likelihood. So what does that mean? So let's say if the sentence for which you're computing log likelihood, India is a great country. Okay? So now let's say in your vocabulary, you basically had the full 5-gram also. India is a great country. Okay? And it occurred, or rather, yeah, that would be too odd. I mean, they don't even start with phrases and so on. But let's say you have all the words. India is a great country, right? So the way you would compute log likelihood is basically saying what is the probability of India, what is the probability of A, what is the probability of is, and so on, and compute likelihood. That is how likelihood is computed. What are these probabilities? These probabilities are simply frequency counts divided by the total count in the corpus. Frequency counts divided by total count in the corpus. So that's your unigram probabilities. You multiply them and you get a likelihood. So that's called likelihood of the entire sentence. Okay. Now, if you drop the word country and rather replace it with CO and count and then RY, then the log likelihood changes because you no longer care about country as a single token, but you rather split it into two parts. And since they are both probabilities, when you multiply, you'll get a different overall probability. You'll have 6 terms rather than 5 terms now. Okay. So when you do this, you do this for every possible word. You try to drop from the input, and you try to check whichever such symbol from the vocabulary, if it is dropped, whichever one causes the lowest loss increase, so negative log likelihood loss increase, those are the ones that you remove. You start with a very large set, you keep removing some of those words, finally ending up with a small set. And that's basically the set that you would call as your final vocabulary. Yeah, that's a good question. I mean, which one is slower, which one is faster? I don't know, honestly. Yeah, we'll have to figure out which one is the one. Yeah. Yeah, good point. See, the idea is that coming up with a tokenizer is very different from using a tokenizer. So once you have come up with a tokenizer, then basically tokenizing a new text is what you care for at inference time, right? At inference time, you don't need to do all of this. You know your vocabulary. And so therefore, tokenizing is much easier. You know? So, but the question probably that is more important to ask is which one of them takes more time to come up with the vocabulary, right? But that's just a one-time job. So therefore, people might have worked on that, but it's not really a very important question. Right? At inference time, what matters is that you have a vocabulary, and then you want to just use it and basically split your stuff. So, and that's not very complicated. Of course it will. Of course it will. But it's just that currently we're just talking about English tokenizers. But when you're talking about multilingual tokenizers, there is no. I mean, typically people don't build language-specific tokenizers. So there is English tokenizer or a multilingual tokenizer. So typical multilingual vocabularies are about 2 lakh to 2.5 lakh for most of the multilingual models. And typical English vocabularies are 30 to 50,000. Okay. So that's how it is. Okay. Absolutely, yeah. I mean, so it's sort of complicated. That is why, in fact, as I mentioned, for Indian languages, when you try to sort of ask ChatGPT to generate stuff, it generates character by character because all it can accommodate are those characters. Okay, so that's the problem. So rather than accommodating larger chunks, basically, in their case, token is basically just a character in that sense. Okay, cool. So that's that. Now, lastly, there is this thing called a sentence piece. Now, sentence piece is not a tokenizer by itself. It sort of builds on top of I think a sentence piece builds on top of unigram or on top of BP. Yeah, it uses BP or unigram to construct the vocabulary. It's just a way of saying that, hey, in BP, unigram, or word piece that we talked about, they all assumed space to be a separator. So they never actually took space as part of the vocabulary itself, right? It was never a part of the tokens. So, but there are situations where you don't want to do that. Okay? You want to care about space, as part of the vocabulary itself. Okay? And that is why sentence piece guys basically took care of that. So therefore, if you think about it, the BP vocabulary, BP tokenizer is used for GPT-2. BERT actually uses word piece, while a T5 kind of model that I'll talk about, we'll talk about all of these models today in detail. T5 actually uses sentence piece, which cares about space also. Okay? Now you might be thinking, why does it matter, right? So, even I used to think, who cares about the space as part of a token? Okay, so but it is very fancy sometimes how these things work. Think about auto completion scenario. Somebody has typed cheap Nike, Nike. And then there is no, the guy is still typing Nike. Now, should you basically predict the next word, or will this guy want to complete the current word? Nike के बाद में भी तो कुछ type कर सकता है, like Nickelodeon or something like that, right? So then, therefore you need to figure out whether the guy will type a space or will just continue the current word. And for that particular kind of inferencing, you do need to consider space also as a part of your generation token in that sense. Okay? And this is where basically space as a part of the vocabulary matters, these kinds of scenarios. Okay? So anyway, sorry? Huh? Oh, no, well, that's true. That's a good point. Yeah. So, but then, when you want to generate stuff in query auto-completion, you have to compete with users' typing speed, right? So, and your models typically, if they're deep learning models, they're running on servers. And you have to also account for internet latency. So what you have is totally 10 milliseconds to do the inference. Um, so in 10 milliseconds, you really can't wait for the guy. Is the guy waiting or not? If the guy is waiting, then do this, else do that. Man, if the guy is, if you already accounted for users waiting time, then you have lost already because the guy has already moved on to the next character. Huh? So therefore, you cannot really afford to even check at any point of time if the user is waiting at this character or not. Okay, good. So that's that. So that was a basic primer on subword embeddings. Hopefully, it makes you excited enough to actually answer several questions that you asked, which I could not answer. For example, how do you measure the accuracy of tokenizers? How do multilingual tokenizers work? Which tokenizers are slow? Which tokenizers are fast? Have people build language-specific tokenizers? Honestly, I don't have answers to them. Go figure out. Okay. So, but hopefully, it tells you how tokenizers work. Yet another interesting questions to figure out is how does tokenization happen at inference time? Is that tokenization probabilistic or is it deterministic? So if basically let's take I mean if you take any word like running, right? RUNNING, maybe the vocabulary contains RUN and then a single N and then ING. The vocabulary also contains running, the entire word. So which one will it choose? Okay? And why? Right. So in the sense, so how do you basically do that in inference time? Okay. So try to figure out those answers. Okay. 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 Any questions otherwise? If not, we'll move to the next topic, transformers. Okay. Huh? But there could be options, as I said, right? So running as a direct word, or you could split running into 3 words because maybe all 4 of them are actually present in the vocabulary. Sometimes redundant tokens will also be there. Okay. So if they're there, then how do you choose which one? Okay. Yeah, maybe you would always go ahead and choose the longest one. But will longest be fixed? I mean, it could be possible that you have always like 2 tokens, but 2 different pairs of tokens possible for a single word. RU and then ning, or then RUNN and then ING. Which one would you choose? Right? And does it really, I mean, is there a deterministic way of doing it? Is there a probabilistic way of doing it? If probabilistic, then it's okay. I mean, maybe you can just do probabilistic and, sometimes choose this, sometimes choose that, and so on. But then, yeah, I mean, that's homework. Okay. Okay, so let's get to the next topic, transformers. Okay. So you all know transformers. Yesterday, Srivatsan covered transformers. So why are transformers called transformers? What do they transform? What do they transform? No, yeah, translation is just one of the applications for which transformer models are being used, right? Huh? Now, yeah, you can think about it like that. But transformers basically transform the representation of any token over several layers, right? Each layer, all it does is to just come up with a transformed representation of an input token, right? So I think as Srivasan discussed yesterday, right, transformers basically are encoder-decoder networks. So they are very similar to RNN encoder-decoder networks, or rather, if you try to think from that perspective, just like that, they have an encoder, they have a decoder. They have several transformer layers rather than recurrent layer. So, if you think from a standard deep learning 101 school perspective, right? I mean, what kind of layers do you know? Dense layers, which are fully connected. And then there are CNN layers, convolution layers, which are sparsely connected. There are recurrent layers that people know about. And then there are transformer layers and transformers, new kinds of layers. Okay. Compared to a typical RNN encoder decoder, however, in transformers, there is no recurrence. So there is no recurrence at all. Okay. So in fact, the reason why people came up with RNNs or LSTMs or GRUs and so on was that human text or rather text typically has a sequence aspect. And if you want to capture that sequence aspect, you need some model which considers sequential behavior as first class behavior, right? And therefore, people came up with these recurrent models. Transformers said no recurrence. Okay? So now, how is that possible? So if you have no recurrence, then how do you care about the sequence aspect? Okay? So that's that. But anyway, no recurrence, right? And then unlike a encoder-decoder, RNN-based encoder-decoder, the last layer of the encoder is connected to all layers of the decoder. Okay? So in an encoder, RNN-based encoder-decoder, the last layer of encoder is connected only to the first layer of the decoder. But here in a transformer, it's an encoder-decoder network where there are several layers of encoder, one feeding into the other. The first layer basically gets the input tokens, right? And then the output is generated by the decoder, the last decoder layer. Decoder layers, of course, connect one to the other, and the last layer of the encoder is connected to all layers of the decoder. Yeah. So transformers could be used for translation as a task. So encoder-decoder models could be used for sequence-to-sequence learning tasks. Machine translation is one. What are the other sequence-to-sequence learning tasks? Summarization. Yeah, input is a document, output is a summary. Yeah, sequence-to-sequence. Any other tasks? Huh? Time series forecasting. Yeah, multi-time forecast. Yeah. So basically, you have a time series and you want to forecast for the next few days or months and so on. So that's right. Yeah. What else? Any other tasks? Named entity recognition. Yeah. I mean, well, you could say, yeah, that way that the input is a text sequence and the output is named entity tags for each of those tokens. Yeah, some ways, right? Speech recognition, yeah, speech to text. So that's basically also sequence to sequence learning task. Input is speech sequence, but it's fancy. Try to think about how would you get a speech sequence and encode it, right? So we learned about word encodings, no? Homework. Figure out how do you encode speech. How do you encode speech? Anyone knows? Huh? Using MFCCs, right? So baki local homework. What is MFCC? So Mel frequency Kepstrom coefficients, but try to figure out how do you get. So it's fun, how do you encode speech? Anyone has used? Of course, except you, probably people have not used Pi Audio. So try to figure out Pi Audio, Librosa. Those are interesting libraries for processing speech. But anyway, yeah, thanks for bringing that up. Yeah, I mean, so transformers is not just applicable for text; it's applicable for any kind of input sequence that leads to output sequence, right? So time series, speech, videos for that matter as well, because after all, videos are also a sequence of images. Okay? So if you think about it, video is nothing but a sequence of images. Okay? So for all of those kinds of tasks, where sequences are both at input and output, transformers are usable, and transformer-based models are usable. Okay, so now each layer of the encoder actually contains two sublayers, self-attention and feed-forward. Okay, so that's that. Each layer of the decoder contains three different sublayers: self-attention, encoder, decoder attention, and feed-forward. Feed-forward. Okay, so that's that. Now, of course, on the decoder side, there are three sublayers because there has to be a sublayer which cares about these connections, right? So connections coming from the encoder side, and therefore you have this encoder, decoder attention sublayer. To basically care for that extra information which is coming from the encoder side. Okay, so that's that. Now, and then there are these concepts of what is self-attention, what is multi-head self-attention, what are positional embeddings, residual connections, masked attention, and so on. Okay, so what is self-attention? Any ideas? What is self-attention? Let's start with a simple one. What is feed-forward? What is feed-forward connections? Huh? Feed-forward attention, feed-forward connections are basically just a typical hidden layer. Okay, it's just one hidden layer. That's all. Okay, so it's not like a big deal at all. Okay, so what is the feed-forward sublayer? It basically just contains one dense layer. That's all. So the input to transformers is basically, as you see, these tokens. These tokens for any transformer architecture are fixed in terms of their sizes. So, for example, word2vec, the standard word2vec has 300 dimensional, But here, you could basically fix the size to whatever you like. So here the embeddings are actually learned as you train the model for various tasks. Okay? So if you want to use an existing embedding, then you have to fix to the embedding size that you have. But typically in transformer-based models, people don't use some existing embeddings. They actually learn them with the task. Okay? They learn them with the task. And therefore, they fix them to whatever size they prefer. Something like 512, BERT, which is also a transformer-based model, actually has a size of 768. Okay? What does that mean? That this token is going to be represented as 768 dimensional vector. Okay? These models also take a limited number of tokens as input. So basically, for example, you can't feed like 10,000 tokens as input. You can basically take like standard transformer takes maybe like something like 256 tokens as input. Okay, that's that. So feed forward, what does feed forward layer do? So and by the way, all of these layers are super symmetric. So if the input basically was like say 3 words, each 512 sized, each 512 sized, the output of the encoder will also be like 3 tokens, each 512 sized. Every encoder layer for that matter. Okay, and then at the output maybe I'm generating 4 tokens. Of course that can happen, right? 3 French words can lead to 4 English words. So then, my input also is basically, actually it's not shown here, but you also provide those shifted inputs, shifted outputs as inputs to decoder. Okay, they are also, 4 into 5 and 2, exactly the same sizes, right? So basically, it's super symmetric. It is so symmetric that if you delete a decoder layer, you can actually connect from the lower decoder to the upper decoder layer. Okay, it's super symmetric. Okay. So now the way the feed forward layer works is as follows. So basically, let's say if the input was like 3 of those tokens, the feed forward layer is going to give you an output, and the processing basically happens like this. It's a position wise feed forward. What does that mean? That basically means that the architecture is like that. It's not something that I'm showing on the right side. It's not that there's a single hidden layer feeding into the same things. Feeding into it, and all of them then feeding out from the single layer. No, it's not like that. Okay, it's not like that. It's basically position-wise feed forward. Okay, so why is that so? So as to of course reduce the number of parameters, right? So and the interesting part is that it has 2 matrices, WA, WB, right? And they repeat. So basically, the same weight matrices are going to be used in all of those positions. Okay, if you had something like this, imagine how many weights would be there. So you can't share weights. So you'll basically have like a very large weight matrix. Okay, so therefore they have position-wise feed forward layer as part of position-wise feed forward connections. Okay, any questions about this? This simple stuff. Okay. Self-attention. What happens in self-attention is the question, right? So, which is what basically made transformers popular. Okay, so you should basically at some point read this paper. Attention is all you need, right? And by the way, yeah, I mean, if you find some of these concepts difficult to understand, just search for these 2 things: annotated transformer and illustrated transformer, right? So the top link that you click on Bing or on Google, right, will lead you to 2 pages. So the annotated transformer leads you to a link from Harvard, and the illustrated transformer leads you to a blog by Jay Alamar, a guy called Jay Alamar. Both of those are super awesome pages to understand how transformers work. Okay? But anyway, in fact, these pictures that you see are exactly from that blog. Okay. Okay. So let's try to understand what happens in attention. So in the attention layer, self-attention, what happens out there? Okay? So let's take a sentence. The animal did not cross the road because it was too tired. The animal did not cross the road because it was too tired, right? So the word it. Now the word it by itself carries no meaning, right? It has hardly any useful meaning, right? But when you think about it, what do you think about the word it? Right? The animal did not cross the road because it was too tired. It refers to the animal, right? So the meaning of that word it is the animal after all, right? The animal did not cross the road because it was too wide. So if it was too wide, then basically it represents the road. Right? So essentially in our heads, we understand the meaning of the word very well. Right? And we don't understand the meaning of the word because I referred to a dictionary and then it said, acha, it basically means the animal or it means the road. I just understood the word by paying appropriate attention to words in the same sequence. Right? So basically the idea is that if we pay good attention to other words in the input, then I can actually come up with a very good representation of each word in the original input. And that's the idea which is encoded in a neural way in the self-attention layer. So in the self-attention layer, somehow for every word, I need to basically figure out which other words in the input should I borrow my meaning from, and therefore come up with a transformed representation. Okay? So I'm going to come up with a representation, a better representation for every word by actually borrowing meaning from other words. Okay? And now the big thing is to learn whom to borrow that information from. Okay? So whom to borrow the information from. Some words like animal, now, animal says, hey, I don't want to borrow any information. I'm self-sufficient from that perspective. Sure, so be it. Okay? But words like it, they have to basically borrow information from other words to be meaningful. Okay? So we'll take a simple example of these of a sentence with just 2 words, thinking machines. Okay? Thinking machines. And we'll try to understand how this self-attention concept works. So how do you basically decide how this borrowing of information happens? Okay? So you have these 2 tokens, thinking machines. The first step that is done, so we'll try to first understand how it is done. We'll try to understand how it is done, and then we'll question every step. Hey, why it was done this way? Okay? Or rather, it will become clearer after you understand how it is done. Okay? So you take each of those tokens, and I'll use the words word and token interchangeably. I always mean tokens, okay? Because all of these transformer-based models work with some subword vocabulary. Okay? So I take this embedding and then I basically create 3 forms of it, and these 3 forms are called QKV. Okay? So queries, keys, and values. And the way I do that is by using these matrices WQ, WK, and WV. WQ, WK, WV. Okay? These are learnable weight matrices. In fact, these embedding vectors are also learnable. So they are also not fixed to begin with, right? So they are also learnable. All that is fixed is the tokenizer. Okay? So all that is fixed is the tokenizer. I know what are the tokens, but I don't know what are the embeddings. I'm going to learn them as part of my task anyway. Okay? So, and then these WQs, WK, WQ, WK, WE are also learnable. And the way I obtain Q1 is basically by multiplying x1 with the WQ. So that's how I get that. Q2 is equal to WQ times x2. And similarly, the other stuff follows, right? WK times x1, WK times x2, and so on. So that's how basically I get these QKVs. Okay? Now we'll of course understand why are they required. So why are we getting like 3 different feature representations of the input x? So input x token, we basically got some feature representations, QKV. Okay? So the way we did that, the way we did that is basically, let's say I want to come up with a revised representation for the word thinking. Of course, I want to come up with the revised representation for the other word as well. And we'll call that revised representation after the entire self-attention layer is done as Z1. Okay? So X1 ka Z1 lana hai. And similarly for X2, we basically want to get Z2. Okay? And I want to, in the process, borrow information from other words in the input. And that is why it's called self-attention, paying attention to self, I mean, the entire input in that sense. Okay? So the way this is done is you basically get QKVs for each of those, for each of those tokens, right? And then the way you come up with the revised representation for this one is basically by taking its query, and computing which keys are most similar to this query. So for example, for the word it, hopefully, somehow, if I consider the current embedding for the word it, in the sentence, the animal was too tired, because the animal did not cross the road because it was too tired. Right? The word it must have very good similarity with animal. Now, why should it have that similarity? So that's not known. But let's assume for the time being, if it has very good similarity, then what would happen? You would say that, hey, Q1, K1 is very high, Q1, K2 is very low, where K2 is any other random word. So basically any other random word in the input. Okay? So the similarity of a word from which it should derive the meaning should be high. If it is not high, backpropagation will punish it through these matrices WQ, WK, WE, right? That is why words which should be used to borrow information, they will have high similarity with the current word. Okay? So basically, how is the similarity computed? Simple cosine similarity, Q1.K1. So you take the query at this current position and you try to figure out similarity from all other keys. It's basically like doing a lookup on a key value store. Key value stores using a query. The current position wala query is a query. And then baki ka key value store, everything else is key value store. And you just try to figure out how much do all of those keys match. Okay? And that's the proportion with which you will take their values and then aggregate. Makes sense? So that aggregation logic should be pretty simple in that sense. Is now, basically if the current query matches 80% with this key, 20% with that key, or rather 10% with that key, 5% with that key, 5% with that key, well, you will take their value vectors and then do that weighted addition, and you will get the full revised representation. Okay? So how does this work? So you basically compute q1.k1, q1.k2, and do some normalization. So it's basically dividing by 8 here. I'll talk about that in the next slide. Okay, but that gives you basically that, hey, care about this key 88%, or rather, this token 88%, 12% that other token. Okay, and then what you do is to take this value vector from here, v1, take this v2 from there, multiply this guy by 0.88 to get this thing, multiply this guy by 0.12 to get this thing, slightly lighter, right? Because 12% of that value vector. Okay, and then you add these guys up to get z1. Okay, now that's just z1. Now, as the box also indicates, it's just computation for the first token. For the second token, of course, you'll do similar computations, but this time you'll care about q2 rather than q1. Okay, so we'll compute the similarity with k1 and k2, but with q2 this time. So q2.k1, q2.k2. And that will, and then again you normalize, that will give you some other softmax values, the output values, and that's basically then going to define your Z2. People understand what is softmax? What is softmax? What is softmax? Softmax is an activation function. How is it defined? What is so special about softmax? Yeah, it's an activation function that you always use in the last layer of a multi-class classification problem. In general, it's a nice, cute function. Why? Because it takes whatever vector and always gives you a probability distribution. Therefore, it's like the best vector that a statistician would love, right? Basically, best function, right? I mean, it basically takes any random vector, right, and gives you a probability distribution out of it. It's such a beautiful normalization vector function. Okay. Okay, so essentially saying that when you compute similarity, there may not be any probability distribution, but what you want to do is weighted addition. And typically, if weights are probability distributions, a linear combination is always nice, right? That's what we learned in school. Linear combination is always cute. So weighted addition. So the way this is done is as follows. So you basically take q1 k1, q1 k1, and you do q2 k2, right? And you get some similarity values s1 and s2. So that's that. Okay. Uske baad mein what you do is normalize them. So normalize meaning you divide them like that and you do softmax. Okay. So what that gives you is alpha 1, alpha 2. Okay. So those are basically your two coefficients. In this particular case, that's alpha 1, that's alpha 2. Okay. And then what you do is you define Z1 as basically alpha 1 times V1 plus alpha 2 times V2. That's weighted addition. Okay. So it's weighted addition. Now, of course, this is done here just two terms because there are two input tokens. If there were like 10 input tokens, you would do alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 all the way up to alpha 10 V10. Make sense? Okay. So that backprop part we'll talk about, but because there are multiple layers, so it's not just there is one layer, right? So when backprop happens, of course, everything gets updated, WQ, WK, and WV, because those are weights. See, X's and Z's are not going to be impacted by backprop directly. So backprop impacts weights. They are going to be updated by backprop. So, when I said X1 is going to be updated to Z1, all I meant is X1 is the input for the self-attention layer, Z1 is the output of the self-attention layer for that position. Now, the word update may not be accurate because after this, I'm going to tell you that they are going to be added. Okay, so therefore, by update, I just mean that the input and output for that position for the self-attention layer is X1 and Z1 respectively. Yeah. Okay. Any other questions? We'll maybe go into a little more detail. So. Yeah. So we saw that, well, I mean, you can basically take X1 as a vector for the first position, get Z1 as the output, take X2 as the vector for the second position, and get Z2 as the output. Okay? Of course, you can do this in matrix form. You can write this in matrix form like that. Okay? There's nothing new on this slide. All I've done is to take the previous slide and write it in matrix form. Okay? So what have I done? I've basically taken these two rows, thinking machines, thinking and machines, right? And that's represented as a matrix X. Okay? I multiply by WQ, WK, or WV, those three matrices. Okay? And I basically get the QKV tokens for each, QKV representations for each of those tokens, you know, QKV matrices. And then what have I done? Basically, remember, for every query, I must, compute similarity with every key for a particular position. So for a particular position, I take that query and compute similarity with every key. Second position, again, compute, and so on. All that can be done together by just saying QK transpose. QK transpose exactly does that, compute similarity. Okay? And then remember, I did normalization. So that's the normalization being done here, and then softmax normalization, and then finally weighted multiplication. So softmax of that multiplied by the V matrix. Okay, that gives me Z1 and Z1 and Z2 for the two words. So transforms the matrix with X1, X2, two rows to two rows Z1 and Z2. Any questions so far? Yeah. 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 That's right. That's right. Here, query is basically a semantic representation of a token. It's a vector representation of a token. And what you want is other vectors which are similar to it. Okay? So now what is the query exactly capturing is unknown, or rather it's not interpretable, just because it came out as an output of this operation X into WQ. So if X was thinking, now you applied some WQ matrix to it and you came up with some query. Now what does it exactly contain? Who knows? Right? So it's not interpretable in that sense. The text embedding be the query. You mean the original X itself can be used as a query? Yeah, why not? You could use that. It's just that people would have tried various kinds of ways of thinking, okay, which one could be a better query? Should it be learnable, or should it be transformable or not? Right? That's right. WQ, WK, and WV are learnable, not QKV themselves, right? So the weights, the WQ, WK, and WV are learnable. Okay. So the X1, X2 are outputs, basically, right? Outputs of those, or rather X1, X2 are rather inputs. I mean, for the first encoder layer, first self-attention layer, right? And then when you get those QKVs on the right side, they are outputs. But learnable things are right there. W's, weight matrices. Okay? Can you use X's as queries? Yeah, I mean, maybe you could use that, but it's just that it will not give you as good accuracy. So therefore, what people do is to have the WQ, a learnable WQ, so that you can actually impact what should be extracted from this word, so as to define a query. Good point. Yeah. I mean, I think some of your questions can be answered. I mean, that's not true. Okay, so what you said is good, and it's good thinking at this stage, but that's not true. Especially if you think a little deeper. The idea is that the first layer of the encoder basically takes your tokenized embedding representation, but the second layer basically just takes the output from the previous layer. So there is no notion of ye to learnable acha tha, and so I mean it has all transformed and so on, right? So that's one thing, right? And there are other things which will become clearer. But right now, the thinking is good. Oh, if I trust this initial embedding, then why the hell do I need another query, right? It's a good thing, good way of thinking, but that's not true, as I said. Okay? These are of same dimensions, exactly the same dimensions. Which are which, exactly. Good point. Yeah. Huh. 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 Yeah. Exactly. We have just given it names. The network does not know those names and does not really care about them as queries, keys, and values. I mean, sub MoMA at the end of it. But yeah, I mean, I relate with what you're trying to say. You're right. I mean, see, if I really think from a perspective of what is going on in the bits and bytes, well, all they think about the network is basically it's a graph, and you're just running back propagation on the graph. It doesn't care whether the input was text or the image or speech or whatever, right? From that perspective, it is extremely abstracted out for it, right? It's just our human way of thinking that this is what must be going on. And this thought process is what went on to design these networks so as to connect them in a particular way. Okay. So there is no notion. I mean, of course, the network does not know the back propagation. In fact, if you really go back to the extreme details, the gradient descent doesn't really know whether it is basically operating on a text network or an image network. All it knows is that kuch to network hai with some nodes and there are mathematical operations defined. But you've just given it name so that we can interpret it in that way, right? And design it in that way. I mean, it is capturing semantics in some ways for that token. You cannot differentiate, unfortunately, that hey, what is query semantics, what is key semantics versus what is value semantics for this token. You're right. I mean, from that perspective, it's sort of impossible to differentiate that. I agree. Okay. So, but I mean, again, to design the network, they had to come up with this kind of a naming scheme in that senses, so as to make sense about, or rather think about it this way. Okay. Now, I mean, in general, right, whether you take convolution, any kind of networks, right? I mean, of course, as I said, after all, it's basically just a network with some connections between these neurons. But the way the neurons are connected is basically defined by what we make out of them, what we think about them, right? What is the meaning we associate with them. And the idea is to basically mimic the human process as much as we can, right? Our way of thinking. Okay. Yeah. So, so that's not right that Q represents questions and K represents, the keys and so on. So those three, and that is why, in fact, we had that discussion, right? That, hey, it's not like they're questions. So in fact, they're just a representation, a vector representation for that particular token. So it's basically, in fact, that Q vector is just a vector. It's a numeric vector. It's not a bunch of words which make a question. Okay? So just a numeric vector. K is also a numeric vector. So key is also a numeric vector, and value is also a numeric vector. Okay? They are just three vectors. And the naming is what we have given to them. I mean, they don't really mean like question or keys and so on. So therefore, don't try to look at them that way. If you look at them that way, of course, your point is, hey, what is the value? I mean, typically I give this as an example to people. Let's say that there are like 5 people with the name Sai here. Okay. So Sai is a very popular Telugu name, right? Sai is the prefix of a popular Telugu name, right? So there could be Sai, whatever. Any Sais here? Sais? No Sais? Okay. So yeah, I mean, yeah, think of it as a popular prefix. It's a popular prefix with many Telugu names. Okay. Now somebody just basically walks in and they basically ask me, and I'm the school, not school, whatever, right? The course instructor. So I must know everyone. Okay. So this guy walks in and asks me, hey, what is size height? Okay. I'm like, yeah, size height. So probably I have a database with like 5 size in them, right? And then I basically know their height. So that's good. But then this guy is asking what is size height. Now, I mean, there's no person called Sai. There are like 5 of them. So what do? I basically so that's a query coming in, and I have a key value store called size height along with essentially their actual height, person height. I have a mapping somewhere, right? What will I do? I'll basically just to figure out, oh, there are like 60 people here. Baki 55 are not useful. Only 5 of them are size. So for those 5, what is the most obvious thing I would do? Just do an average and give that average to that guy, because that guy is so ambiguous about the query. Okay. The query is pretty ambiguous. What is size height, right? And what is the best that I can do? I can only figure out, which of them are looking like size for that matter, right? And then, if I have some similarity notion, I'll figure out similarity and then do a weighted addition of those values, heights, and return that, right? And this table that I had, what is it capturing? It's capturing this relationship between the word called psi and the height. So it's capturing height relationship. Okay? So it's capturing, given a query, given a key and a value. So what is the relationship it's capturing? It's capturing height relationship. Okay? So similarly, there are several relationships between pairs of words. Okay? And when you're doing this similarity analysis, QK, Q into K, you're trying to capture some sort of relationship between every pair of words. Okay? For example, you could be capturing, rather than height in this example, you could be capturing a relationship like the co-reference relationship, it, animal, it and animal, or it and road. Okay? And there could be other kinds of relationships, like, you could be capturing subject and verb relationship. So the boy put the tortoise, so the boy put. So boy and put, the relationship is verb and subject relationship, right? So there could be several relationships, and these WQ, WK, WV, those matrices help capture those relationships between a pair of words. Okay? Sorry. Oh. Eventually, it should happen that the combined meaning should lead to a very good translation, because if the good translation doesn't happen, there will be loss defined there, and backpropagation will happen so that WQ, WK, WV are aligned appropriately. Typically, it is less dependent on tokenization, because if you have like millions of instances to fine tune, then it does not matter how good or bad your tokenization was, unless your tokenization is like character level. Well, people have actually built character level transformers also, so even that works fine. Actually. Ground truth is training data, of course. Yeah. I mean, this is all supervised learning, so you'll of course have like labeled data to train these kinds of models, right? Okay. Questions? More questions? Huh. No, you don't design these matrices. First of all, let's stick to text, right? Because that's very complicated when you go to images and audio and so on. I mean, that's another session, right? But the idea is that you don't design manually. They are randomly initialized and updated by backpropagation over time. What are the parameters? By parameters, you mean like convolution layer has like number of filters and so on. How do you initialize your dense matrices typically in neural networks? So you just do random here, or you do Xavier initialization if you want to. I mean, there are several ways of initializing, and there's no standard here. I mean, you can just do random initialization. Okay. Okay. Any other question? What specific task? Our story is around translation, but you can do whatever task you feel like, whatever task you have data for. That's right. So for whichever task you want to train it for, you'll have to train a different transformer representation. Okay. Now, transformers by themselves are not pre-trained models. So which basically means that if you train a transformer model for, for translation, you can't, it's not like you can download it from Hugging Face. So there's no transformer checkpoint on Hugging Face. There are transformer-based models which you can download from Hugging Face, but transformer by itself is not a pre-trained model. And that is why the topic was pre-trained transformers today, which basically means that once we understand transformers, then we'll see how people have pre-trained them and made them available. Okay? Yeah. 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 Oh, I see. Yeah, much beyond the scope of this course. Yeah, coming to the question that you really asked. Yeah, but why the question? That's the first part. Yeah. Hey, by the way, in Mamba, we do train. Okay. So actually, although the matrix is, so this is basically only for this guy, most likely, because most people don't know Mamba. Anyone knows Mamba? Some people know Mamba. Okay, so it's for those people. Okay, others, and maybe we'll spend like maybe 5 minutes on this. But anyway, right? So in the initial state space models, basically people said, hey, we'll not train A. We'll basically fix A. But Mamba does train A. In fact, it doesn't train A because A is diagonalized. So it basically trains that diagonal in that sense. Okay. So now the other part that you asked, right? Have people tried to sort of initialize these matrices with A, right? With hippo initialization, and then have people figured out stuff. See, I mean, hippo is a very, very specific way of initialization, and that applies to matrices which are square in nature. A is a square matrix. These matrices are not square. Okay. Now, your next question could be, why are they not square? You could still have them as squared. Who basically told you they can't be squared? They can be, but again, the hippo initialization works for a particular reason. So the initialization works because somehow you want to compress the entire history and represent them into a basis space of a fixed number of n functions, n polynomial functions. Now, that's not the same reason why you want to do it here. So you don't want to basically, learn a representation for a particular token just based on the history. You have the future as well. I mean, it's a bidirectional stuff here. So therefore, yeah, it's a good idea that you're trying to understand why hippo initialization does not work here. But it doesn't work here because there is no need. Because you use recurrence there. There's no recurrence here, right? So the worlds are very different worlds. And most importantly, transformers came in 2017. Mamba came like a month back. So how can they use in 2017, which came in after like 7 years in time, right? Anyway, so coming back now to this stuff, right? Good. But that's a good thing. I mean, you should basically always question what happens if you basically try to apply a piece of knowledge from somewhere else to other settings broadly. Okay. Yeah. Not really. See, because beach mein I am also doing the softmax operation, na? So it's not like it's completely fully expressible as a single matrix. Yeah, yeah. Oh, absolutely. Absolutely. In fact, you can do all of that. So people have done that because people have realized that there are problems with this as well, right? And then people have realized that it's not as accurate as this, though. But there could be other benefits of it in terms of efficiency. Okay? So people have tried to do such alternate representations of this process, but this is the way it works the best. Okay? Empirically validated over multiple experiments. Right? Okay. Good. So let's keep going. To complicate matters a little, so this is basically what is called as a self-attention head. So what does this mean? It captures a kind of pairwise relationship between words. So as I was saying, it captures, let's say, co-reference resolution as a relation between a particular pronoun and a noun, right? But there are so many other kinds of relationships, like which words come next to each other. So, or basically, do you know about dependencies, dependency parsers, dependencies? Everyone has, again, if you have not looked at it, you should basically, and if the demo works, you should basically just go and look at it. Core NLP.run. Yeah, it may or may not work, but it works. Yeah, which is good. So, the cat sat on the mat, or rather, sorry, let's take Modi. Modi gifted Obama a shawl. So, how many of you have used this? Everyone has used this, I'm assuming. No. You can see my screen, right? So no one has looked at this before? Too bad. Okay. So just search for corenlp.run. It's a Stanford project called Core NLP, which is what pumps NLTK and many of the parsers in Stanza as well, right? And Spacey and so on. So essentially, it's a very simple demo, right? It basically talks about if you take a sentence, how you can figure out part of speech tags and so on. This is also called as dependencies. So for example, you can actually find these dependencies that Modi is the subject for the verb called gifted. Okay? Obama is the object for the verb called gifted. Of course, a shawl is also another object. So remember in school, we used to do this SVO kind of stuff. So there are 42 different kinds of such pairwise dependencies that one can find between words in English. Okay? So there's if you just search for Stanford dependency manual, you can actually figure those out. Okay? So there are so many pairs, so many dependencies between pairs of words. So why only care about a particular dependency that you allow your WQ, WK, and WV to learn? Okay? Maybe there are many of them. So therefore, let's allow them to learn many of them. And how would you do that? The way to do that is basically rather than defining one triplet of WQ, WK, WV, you basically just define several of them. And they are then called as heads. So basically, you say that, hey, one is not enough. The standard transformer basically says there are 8 heads, meaning you will have one WQ, WK, WV, another one, and then 8 of them of this kind. Okay? 2 of them are shown here. Okay? 2 of them are shown here. Okay? So if you have 8 of them, then clearly you will have 8 of these Zs. A single X will basically lead to 8 of these Zs. Caring about a different triplet of WQ, WK, WV, and therefore coming up with 8 different Z representations. And then what do? Well, you just merge all of those 8. You just concatenate all of those 8 together and get your final Z by projecting them using another dense matrix. By projecting them into using another dense matrix, you get your final Z. Okay? So in the process, what are you trying to do? You're trying to basically learn relationships between pairs of words. Why relationships matter? Because they are the way that you can pass information from one word to another, right? They are the way using which a word can revise its own representation. Okay? So, and standard transformer says I care about 8 such relationships, and basically therefore come up with a revised representation. Okay? Now, the interesting part is that most of it is uninterpretable. However, you can visualize these weights which are learned. So if I basically take this sentence, the animal did not cross the road because it was too tired, for the token it, I can actually figure out in this first self-attention layer, what was the contribution, what was the Q into K, right? The weight basically for each of those other tokens, okay? And therefore I can visualize these attention values. Okay? So remember, since there are like 8 different heads, I will have 8 different attention values between any pair of positions. Okay? So this head basically, this head is at layer 5 in your transformer encoder, and there are so many different, each color is like a different head. Okay? Each color is different head, and the orange head basically says it pays a lot of attention to the words the animal. Okay? The color, the intensity tells you how much is the weight. Okay? There could be other heads. For example, this head, if you look at it, it basically tells you, and there's another sentence, we have grumpy neighbors. If we keep the music up, they will get really angry, right? And if you look at it, this head basically relates words which are next to each other with a very high weight. So keep up, or will get, or get angry, we have, and so on. And there could be other heads which relate subject with the verb or verb with object, and so on. Okay. Any questions so far? How many heads transformers should have ideally? Yeah, that's a great question, right? So simple answer is that have lots of heads. So it's basically like asking how many features my data should have in traditional machine learning. So how many features should you have? Have lots of features. Hopefully your model is good enough to only care about useful ones and take them, right? So that's a simple answer. And the complicated answer is that the more number of heads, the more is the inference latency, right? So therefore have as little as possible so that it can infer faster, less compute power requirements, right? But then there is also other literature which says that, hey, train with multiple heads and then delete them after you've trained them. So essentially pruning of heads, basically much like pruning your decision tree. You grow much and then you prune away because you don't see much of accuracy loss, right? So people, when they train their architectures, they have some standard number of heads not driven by any useful information. I mean, yeah, it's basically black magic in some ways, like 8 heads, 12 heads, 16 heads. Yeah, interestingly, people don't take odd number of heads. I don't know why. But no good reason for that. Huh? Yeah. 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 It's successful, and that is why the paper retention is all you need, has like 50,000 plus citations. Yeah, it's fairly successful. Right? In fact, it was so successful that I like to divide NLP into like a few eras. There was an era before 2014, where people were doing non-deep learning things. 2014 to 17 was a pre-transformer deep learning era, And then, after 2017, all of NLP is basically transformer based only. It was so successful. It redefined the way people do NLP. Yeah. Good point. Yeah, they do work really well with the non-English as well. Yes. Okay. Okay. Good. So now, transformers don't have recurrence. So which basically means that they don't have a notion of position. So they don't know. So if you basically, so if you don't have a notion of position, what could happen? If you're, let's say, using it for translation, Ram is going to school, right? Now, of course, translation in Hindi should be Ram Pathshala ja raha hai, right? Now, basically, if there's no notion of position, I might as well give input as like school Ram going is to, right? And that should also lead to Ram Pathshala ja raha hai. Now, that doesn't make sense, right? So that is why you had like sequence information as recurrence, encoded as recurrence in RNNs. Okay? Now, since you don't have recurrence, what do you do here? The way you do this here is by actually encoding position information separately. So you say that the input to the first encoder layer is not just going to be the token embeddings themselves, but you will also add position embeddings. So as to say that, hey, this is the first word, this is the second word, this is the third word, fourth word, and so on. So stamp on every word that, hey, this is a position. So that the positional information is also passed as input. Okay. Now, how do you do this? So the way you do this is that you basically have the embeddings for the token, and you actually add some sort of a position embedding. So the position is not concatenated. Another way of doing it is, okay, your input is 512 size long, usme ek aur extra mark, another number to just say position. It just turns out that there's a fancy way of adding position embeddings. It's basically a vector of the same size as your original token embedding, and you add and then pass it as input to the encoder. Now, in the beginning, it may seem like a little, messy. Hey, why would you add up semantic information in that token with the positional information and it works? Okay. So, but well, in the original transformers paper, that is what you do. And transformer-based models just do that. Okay. Of course, there are other kinds of, papers later which try to disentangle this information, the content and the position information, and treat them separately. Okay. And there are minor improvements, but not as large as to justify why this is bad. Okay, so this is reasonable. Okay, and there is a way of learning this position vector using these functions. Okay? Again, I'll not go into details of those, but there is a way of doing that. Okay. So basically saying transformers don't have recurrence, but they do care about positional information. They do care about sequences. Okay. So this is my last slide before we can take a break. I don't know what's the time for the break and what's the time right now. 11:36. Oh, we are very close to the break time. Not bad. Okay. So yeah. So we talked about encoder, transformer encoder. So it basically contains self-attention layer and this position-wise feed-forward layer. Now the way they are connected is basically, the input basically gets, the position embeddings get added so that the input to the first encoder is ready to be consumed by the encoder. Okay? There is also this notion of residual connection. So what does this mean? That you take X, the input, and you take the Z, which is created by this self-attention layer, you add them and you then do normalization. So why do you add them is the question. Okay? So you add them and then you do the normalization. So you add them and this addition is basically called as residual connection. These connections are called residual connections. It's as good as saying, hey, you take the X that was generated here, you take the Z, and you basically have this short circuit connection at the side. Yeah? And then you add them. So adding them is as good as like supplying your initial features beyond these processed features in that sense for every position. Okay. So why do you add them? You add them so that certain tokens, think about them, certain tokens don't really need too much of processing. In that case, you want to actually retain the original meaning of the token itself. Okay? While some other tokens in the entire sentence may need crazy number of processing, multiple layers of processing. So for them, Z is very important. Okay? So X is very important for those tokens where too much of processing is not required, while Z is very important for those tokens where multiple levels of processing is required. Okay? And therefore, you have those residual connections. Actually, this idea of residual connections in 2017 was borrowed by these guys from vision. So in computer vision in 2016, there was this network called as ResNets, which became super popular. It actually won the ImageNet Hackathon Challenge. Okay? They were also based on residual connections. And people figured out that residual connections is the only way to do stable training for deep models. So, people used to think, oh, deeper the model, more the money that you have, the better the GPU, and then, deeper the models that you can train. But in 2016, people realized that's not true. If you basically just keep putting more and more GPUs and train deeper models, they may not work as well unless you have residual connections. Okay? So these guys basically, in the true spirit of research, just borrowed those ideas at work and made residual connections a part of text models as well, right? Transformers. Okay? So you have residual connections around both the feed-forward sublayer and the self-attention sublayer as well. And then you have normalization as well. So normalization is made to ensure that your outputs don't grow too large. So you do layer-wise normalization. So the last concept that is left is what happens on the decoder side. So we've understood the encoder completely now, right? We understood multi-head self-attention. We've understood residual connections. We've understood position encodings, right? On the decoder side, there is this third extra layer called as, there are two differences, right? One, there is this third extra layer called as sublayer. What is it called? Encoder-decoder attention. Encoder-decoder attention, so what happens in that encoder-decoder attention thing? Okay. So in the encoder-decoder attention, let's say the input is Ram is going to school, and you are trying to decode Ram Pathshala ja raha hai, right? The decoding happens token by token. So the first thing is that you will generate Ram, okay, and then you will use the word Ram that is generated in Hindi, okay, and then you are basically going to pass that as the input, generate the word part, maybe part because Shala is another token, and so on, okay, and then generate the next token Shala and so on, okay. So when you're doing this, you of course want to be conscious of what was being generated at the last layer of the encoder, okay, every position on the encoder, okay. And that is the job of the encoder-decoder attention. So it's basically when it's trying to generate the word Pathshala, okay, it must basically try to figure out which particular word in the encoder side I should pay attention to, okay. So of course, we generate Pathshala, school is important. So it should pay a lot of attention to school, okay. And the way you can do that is by doing cross attention, okay. So what would cross attention mean? Remember, what is self-attention? QKVs, all that logic, right? Given a query at a position, you want to figure out the matching key. Now, in encoder-decoder attention, what happens is that your queries are on the decoder side, okay, and your keys are on the encoder side. So you're basically going to say, that for generating the word Pathshala, right, I'm basically going to care about the query for that particular position. I'm going to care about the keys and the values on the encoder side, all of those positions. Ram is going to school, all 5 positions, and I'm going to match, hey, which key on the encoder side matches with the query on the decoder side. Do a dot product and then take the appropriate value from the encoder side. Okay, so that helps, that facilitates information propagation from the right encoder tokens to the decoder, right? Encoder tokens to the decoder. That's what happens in the encoder-decoder attention thing. Lastly, in the decoder, when you are doing self-attention, you can't do self-attention on the future things because future is not observed. You're generating it. So, Ram Pathshala ja raha hai, you generate the words ja raha hai, right? So basically, therefore, you can't pay attention to the future words anyway, okay? So when you're generating the word Pathshala. So therefore, it's called masked self-attention. So what is masking here? Masking basically means that you compute self-attention on the decoder side on the left tokens only because the right has not been generated anyway. You don't even know how much you would generate on the right side. So that's basically masked self-attention. Okay, we'll stop with this nice animation. Okay, so it basically shows you a 3-layer encoder and a 3-layer decoder. So of course, it's doing translation. It starts with English words, 4 words or 4 tokens, right? And there are 3 layers. So the encoder stops here. And then you start decoding. So you start decoding with the start of translation token. You generate the first word or the first token. And then you pass that first token as input to the next guy, next position, and you start generating at the next position. So layer by layer. So it is also a 3-layer decoder. Of course, the first 3 layers are encoder. These 3 layers are encoder. These 3 layers, the lower 3 layers are decoder. The lower 3 layers are the decoder. Okay? Now, let's basically play this again and now observe what's going on really. So there are 4 tokens in the input, right? And there is a massive self-attention which is going on. You see, all of them are feeding into each other. The thickness of that line tells you what is the level of self-attention, right? Degree of self-attention, okay? So all of them feed into each other. Decoder side, so it takes all the information from the last layer of the encoder, okay? And it also takes information from the previous decoder. So previous position on the decoder, because the future positions are not generated, so it cannot use that, right? So masked self-attention. So mass self-attention and cross-attention coming from the last layer of the encoder. So it's basically taking information from this last layer from the encoder also. Okay? So, so this very, very simple animation explains it all. I mean, how transformers work. What is the output? The output is actually this, right? So, so whatever gets generated here. So the French translation. English to French. I mean, that's the task for which this model has been trained. So the output is you start with start of token. It generates some output. I mean, which is not shown here, but that's copied here. So that's the first token that generates. The second token that generates is this one, which is basically fed as input to the next position. Just because your backpropagation makes it learn all of that. Yeah, your backpropagation makes it learn. Well, I mean, given a sequence, a particular sequence should be the output. Now, if there are patterns of subject-object change, not in some languages, all Indian languages, basically it's not subject-verb-object. So it learns all of that, okay, through labeled data. Okay. Sorry. The start token is a fixed token, fixed embedding. So basically, in every vocabulary, you will always have some special tokens, like a start token, to say that, hey, this is how this is where my translation will start. It's a fixed embedding. It's also learnable, so but it's a fixed token. Okay. Okay. So we'll stop here and then we'll continue with GPT. After the break. Let's take a 5-minute break. Yeah, some very awesome questions. So, and I just thought we could basically just take them all together, right? So, there was one question, interestingly, hey, why do people train transformers in a supervised manner? You basically said, oh, we need supervised data and so on. So yeah, that's what people thought. And after 2017, people thought, okay, transformers is a great idea, but the text community is so poor, right? In the sense that in vision community, by that time, people had come up with awesome pre-trained models called as, LXNet, VGGNet, ResNet, and so on. And all that the text community had at that time in the name of pre-trained models was embeddings, word-to-vec embeddings. That's it. Well, there were other embeddings as well, like fast text and glove embeddings and so on. But there was no interesting representation, pre-trained representation in that senses. Okay? And that is why in 2017, people said, hey, we'll use the transformers idea to pre-train some models such that you can download them and and fine-tune them so as to essentially get better representations, okay? Or rather get representations for your task-specific things rather than every time training from scratch. Okay? So that's that. So that is what we'll talk about now. So we've understood how these word embeddings work. We've understood how transformers work. Transformers are not pre-trained, which basically means you can't say, oh, I can download transformers. There's no checkpoint called transformers. Okay? You can download transformer-based models like BERT and GPT, but not transformers themselves. They're not pre-trained. Okay? Okay. So many of you have many other questions, right? And please feel free to email me gmanish@microsoft.com later as well after the school is done. Also, some of you, if you are interested in collaborating, please feel free to email me later. But let's discuss this stuff for now. Okay. So let's continue. So you see, when you have the transformer architecture, so how does the transformer architecture look like? Well, there is an encoder, there is a decoder, and there are several layers of encoder, several layers of decoder. Of course, the last layer of encoder is connected to all of those decoder layers. The input the input goes to the first layer of the encoder. Output comes from there. Okay. Now, if you basically take this encoder-decoder architecture and just take the encoder part of it, right? Just this architecture and pre-train it, it's actually called as BERT. Okay, so what is BERT? BERT is a pre-trained model which uses the transformer encoder architecture. Okay? And if you take the decoder part of this transformer model and you pre-train it, it's called as GPT. Okay? So what is GPT? GPT is the decoder transformer decoder which is pre-trained. Now, of course, what does pre-training mean and how it is pre-trained are questions that we'll answer in the next few minutes and hours. But the idea is that when you if you take the transformers decoder architecture, you pre-train it, it's called GPT. You take the transformers encoder architecture, you pre-train it, it's called BERT. Okay. In fact, BERT actually stands for bidirectional encoder representations from transformers. Okay. So they're basically encoder representations from transformers, and they're bidirectional because, well, representation of a word can be derived from words both before and after it. It's bidirectional. Okay. As simple as that. Okay. So we'll first talk about GPT, then talk about BERT. And by the way, if you basically do a full pre-training of the entire transformer architecture, one of them is T5. So T5 model is basically one of those models. A pre-trained encoder decoder transformer model is basically called as T5. Right? There are, of course, other models also, by the way, everywhere, right? So for example, BART is also encoder decoder pre-trained architecture. There are other such models here. Rather than BERT, basically there is so many other models like Roberta, there is Albert, and there is this Electra. There is several other models, which are transformer encoders, and there are several models which are transformer decoders also, like GPTX. So 1, 2, 3, 3.5, 4, and 4.0, and so on. Okay, and there are many other such models in all of these. And there are, of course, multilingual models. So there is multilingual BERT, there is XLM, which are multilingual transformer encoders. So basically, in the multilingual world, you have MBERT, multilingual BERT, you have XLM, and so on. In the multilingual decoder space, you have Bloom. So Bloom is a multilingual decoder. In the multilingual encoder decoder space, you have MT5, you have MBART, things like that. Okay. And on the Indian language side, people have done Indian language specific stuff also. So you have like Indic BERT. Somebody was talking about Indic BERT, right? So Indic BERT is just another kind of a BERT, which is basically here. Okay. Of course, here you also have Llama. So you have all heard about Llama, right? So Llama is also of the transformer decoder kind. So Llama and all models derived from Llama are effectively transformer decoders, basically. Okay. Okay. So we will talk about, we will of course not talk about Llama and everything here, because there will be more sessions later which will talk about all of those things. But we will talk about the basic ones, the BERT guy, the GPT guy, and the T5 guy today. Okay? And at some point, I will also switch to code and actually show you some of this in code. Okay. So let's talk about OpenAI GPT. So this is basically 2018. OpenAI pre-trained a model called as GPT and made it publicly available. So this is the GPT-1. So in 2018. Okay. The model has 12 decoder layers. So 12 decoder layers, as you see them. So here, and since there is no encoder, there is no encoder decoder attention also. So each decoder layer here has only two sub-layers. Self-attention, of course, masked self-attention, because you cannot really look at future words. Okay? So it has masked self-attention, and basically it has the feed-forward layer, feed-forward sub-layer. Okay, so those two sub-layers. Okay, so there's no encoder, hence there is no encoder-decoder attention. Okay, it would still have self-attention, and that's basically masked self-attention. So that's that. Now, how is this guy pre-trained, and what does pre-training mean, right? So pre-training basically means coming up with a very good representation of weights, which is generically useful, not really meant for a particular task in mind, but generically useful. Okay? What does generically useful mean? Generically useful, let's say in the image world, meant that I need to come up with a model that understands images, that understands what kind of features make sense to be extracted from images, not for a particular task. I don't care whether the task is caption generation for an image or classification, or you can do so many things from the image, right? I mean, fake or not identification and so on. There could be several tasks. But pre-training basically means I need a generic model which takes an image and understands what the image is all about. Okay? Similarly, a pre-trained GPT model is a model which sort of takes piece of text and understands its semantics, much like a second grade kid would understand. A second standard kid would understand. Okay? It does not really know any particular task specifically, but it basically just understands English. Okay? So And that is why, our embeddings, word-to-vec embeddings were also pre-trained models. They are also pre-trained models in that sense because they generically understand the meaning of words. Okay? GPT solves one problem with word-to-vec. Word-to-vec, one of the problems you guys mentioned, it doesn't capture context. I think you mentioned, right? GPT is going to capture context, and that's the difference, basically. Right? So why is GPT kind of representation pre-trained model better than word-to-vec? Because word-to-vec cannot really capture context at all. And if you cannot capture context, of course, you lack so much. Okay? You cannot understand a whole bunch of stuff. Okay. So now, we know how word-to-vec is trained, right? In very simple words, how is word-to-vec trained? You basically take maybe 5-word window from any Times of India article, and you basically give 4 words, hide the central word, and ask it to predict the central word. That is how the model is trained. Okay, that is how you can actually teach English to someone, right? I mean, essentially the hangman game, right? So essentially, you give like 5-word things and ask the guy to basically predict a hidden word. And if the guy knows English really well, the guy can predict the hidden word. If not, you back propagate and teach that guy, hey, you made a mistake. Update your weights. Okay, makes sense? That's how word-to-vec is trained. Now, to train this guy, GPT guy, what they did was to make the guy learn how to predict the next word. It's as simple as that. If somebody knows very good English, they must be able to predict the next word nicely. Okay, so I mean, we are very good at predicting the next word typically. So whenever you're reading text, you can always imagine what the next word could be, right? So basically, for example, your WhatsApp can do such an awesome job, right? So if you're typing happy, it basically shows you birthday or anniversary or things. Now, why can it do that? Because, well, I mean, we all, if you look at statistical counts of these bigrams, trigrams, fourgrams, and so on, you can always do that nice job of predicting the next word if you understand English really well. Okay? Now, there are a few things. For example, what words come after which words, bigram distributions in that sense, right? Or what words make sense syntactically, so capturing the English grammar syntax, or what words make sense from a world knowledge perspective, so blood test versus blood laptop, ऐसे तो कुछ नहीं होता, blood test होता है, right? So and so on, right? So basically, there is all of that knowledge, and interestingly, all of that knowledge can be captured by models if you show them billions of such pieces of text. Okay? So the way GPT models have been trained is basically using the very, very simple concept of predicting the next word using massive unlabeled text. Now, this is where we'll basically pre-train it without using any supervised data. Okay? It's pre-trained using unlabeled text, completely unlabeled data. What you do is basically give it like first 4 words and make it predict the 5th word. Okay? If it predicts, great. If it doesn't predict the right word, back propagate and tell it that, hey, you made an error. Update your weights. What kind of weights? Remember, all of these 12 layers basically have feed-forward weights, and they have those WQ, WK, WVs, and so on. So all of those weights, you basically update them until this guy learns how to predict nicely, how to predict the next token nicely. Okay? Sorry. Not fill in the blanks kind of task. In this particular case, it's only the last word. Why not fill in the blanks kind of task? We'll answer that question later. In BERT, actually, in fact, it does fill in the blank kind of task also. Okay? So that's right. Yeah. No, I mean, well, the pre-training, अब question answer, if you have to do, then you need labeled data. Somebody has to give you a question is the answer, right? So what you want to do is to pre-training, the basic principle is that you should not use any human labeled data specifically, and it should be available in plenty. Plenty bole to billions of such examples. Okay. So now, I mean, well, in the vision community, that's not the principle. In the vision community, Stanford started this ImageNet competition, and that's how they got a huge amount of image classification pre-training data. With the text community, we've always believed in using not manually labeled pre-training data, right? Unlabeled data in that sense. Okay. So therefore, always the task is next word prediction in GPT models. Okay. So I mean, so the first thing is that basically word-to-vec does not have a notion of sequence aspect at all. Word-to-vec basically takes a word, gives a vector. Right? So GPT cares about the sequence aspect by actually using transformer decoder, which basically takes position embedding. So therefore, it incorporates sequence behavior first, right? And then second, basically, when it is doing these things, it's actually incorporating these word relationships, which are so important to capture when you are trying to generate coherent text, right? Let's say if you want to generate a pronoun, I mean, you must know which noun it refers to, co-reference resolution, or you want to understand some text which has a pronoun. You need to basically understand which particular thing it is referring to. If you want to understand a verb, you must figure out what are the subjects and the objects on which it is being applied. So relationship capturing between pairs of words is super important. Therefore, word2vec doesn't do that, right? I mean, why would you say that? I mean, oh, no, no, no. So this is all English only. Huh. What is the analogy? One kid can read but cannot understand the words. What do they mean? And another one can understand how to read and no, not really. So that's not a good analogy, actually. No, I mean, both word2vec and GPT basically read English and they can actually understand the words also. It's just that the understanding is way better in GPT because it can understand a collection of words together rather than, or rather, what do they mean? For example, word2vec will not understand blood and test as blood test, right? But GPT will understand, oh, blood test has a different meaning. It doesn't have the meaning as blood and test separately. Okay, so that's that, right? Or meanings of phrases, meanings of idioms, right? A dark horse or throw in the towel. Word2vec will not understand all of those, but GPT will understand. Okay, word2vec will not understand things like the service was not bad. Word2vec would say, oh, this is positive and this is negative sentiment because the word bad is basically negative. It doesn't understand not bad means positive. Okay? So. Sorry, what did you say? And then, I mean, well, they chose decoder only because many tasks are generative tasks. So, and using encoder, you can't generate stuff. So basically, because encoder is supposed, by the name itself, it's supposed to encode rather than generate. So therefore, they chose decoder as a universal. And that's basically the philosophy that the company sort of thought through. OpenAI basically just said, oh, we'll basically just use decoder, right? But that's not, I mean, well, we will see other models also. Of course, BERT is encoder based. So I'll also argue why encoders are good. So there's nothing specific about, hey, decoders can understand better. There's nothing like that. Okay? It's just that they chose to use decoders. Okay? Yeah, yeah, yeah. And when we talk about GPT, it's much more related to text generation. So it's definitely word generation, and I think this is happening. We also have the task of next sentence prediction, right? But that comes under word. But how is that? So therefore, let's not confuse people with more questions. Okay, we'll come to BERT and we'll talk about next sentence prediction as well, right? So, but let's take concepts one by one. Otherwise, there will be confusion. Okay? So the idea is that I can think about the field of NLP as two parts, right? NLP actually has two parts. One is NLU, natural language understanding. The other is NLG, natural language generation. Okay? Now there are tasks where you want to do just understanding, right? And those are classification tasks. For example, given an email, tell me whether it is spam or not. I don't want to generate anything. I just want you to tell me whether it is spam or not. Okay? All classification tasks, all text classification tasks are natural language understanding tasks. Given a particular query, tell me whether it is a sports query or not. Given a tweet, tell me whether it is fake or not. Given a tweet, tell me whether it is offensive or not. So many text classification tasks, right? And you would use BERT there. Okay. But then there are generative tasks, like given a summary, given a document, tell me the summary. Given a question, tell me the answer. Given a prefix of a query, tell me the completion, and so on. Translation. So there are many generative tasks, right? So you'll use decoder kind of models for generative tasks. You'll use encoder kind of models like BERT for your classification tasks. Okay. So the goal is to first understand one by one that, hey, how people have pre-trained them. And then if you still have a question, you can ask, right? The next sentence prediction thing, not now. Okay. Okay. Okay, so how did people train GPT? And again, there is no bias towards just decoders are awesome, encoders are bad. There's nothing like that. All of them are good. Okay, it's just that what people thought and believed in is what drove them to do certain projects. Okay? So basically, in fact, in 2018, while OpenAI was busy building GPT, Google was busy building BERT, and BERT is completely transparent encoder based. OpenAI was busy doing decoder based stuff. Okay. So that's that. So predict the next word using massive unlabeled data. So you don't need any labeled data here. Just hide the next word, and you try to make it predict the next word. If it predicts, great. If it doesn't, backpropagate. Okay. So, and they basically used 7,000 books. Okay. So OpenAI at that time was not funded by Microsoft. So, they basically just used 7,000 books. They were not so rich, and created the first GPT model. Okay. Um, and the first GPT model had this paradigm of pre-training and then fine-tuning. As I told you, pre-trained model just gives you a generic model which understands English and English sentences now, not just words. It understands context also and so on. Okay. And it's basically this 12-layer architecture with the self-attention and feed-forward layers. Okay. And it's trained on this loss called as the text prediction loss, the next word prediction loss. By the way, this next word prediction loss is also called as autoregressive loss. Autoregressive loss. Why is it called autoregressive? You all know regression. Regression uses features, for prediction. But when you use the previous few things for prediction, it's called autoregression. So some of you may know about autoregression in terms of time series. So then basically you're using the previous time points to basically learn the next time, forecast the next time point. That's called autoregression. And here we are just trying to forecast the next word, right? And therefore autoregressive training. Yeah. Generation. Yeah. Yeah, that's great. Yeah. I mean, well, you could actually use it for several tasks. Good point. I mean, decoder, typically the idea is to generate stuff. But you could also use it to do classification tasks in some ways that I'll talk about. And that is why, in fact, the title also. Okay? So, but decoder only models, typically they are meant for generation. Of course, you can use them in ways that I'll talk about to do classification kind of tasks also, understanding tasks also. Okay? Good. Uh, any other questions? So that's a good. Yeah, I didn't really think that they actually had language understanding in the paper title. But anyway, okay. Any other questions? GPT stands for Generative Pre-trained Transformers. Let me tell that, right? It's actually Generative Pre-trained Transformers, so it doesn't really have understanding in it. But well, I mean, in the paper title they have understanding anyway. Okay. Okay. What else? Any other questions? So what do? You basically, pre-train it like that. So for next word prediction. And then when you wanted to use it for some NLP task, you would fine tune it on that task. Fine tune kya hota hai? You take the pre-trained model and you initialize with that pre-trained model. And then for fine tuning, you must have labeled data for that particular task. And on that labeled data, you'll supply that as your X, your input. And then you expect a certain kind of an output. If you get that output, great. If you don't get the output, again backpropagate and update the weights. Updating the weights is called fine tuning. Okay. Now you can do that for various kinds of tasks. The obvious task that you can do that for is generation itself. So basically you can do it for summarization by actually using document and summary kind of data. You can do it for translation. Well, translation GPT se nahi kar sakte because GPT is English only. But you can do other kinds of such sequence kind of tasks. But in fact, they basically wanted to say that decoder is the way to go for NLP. So they said that even if you have a classification task, we will actually do it using this kind of a framework. How? Well, they said input agar spammy mile to dalo, output mein I will basically just guess a word called spam or not spam. The idea is that I can always fold in classification tasks to look like generative tasks. Okay. So I would basically ask things like, hey, I'll give the entire email and then I'll say, is this spam or not? And the guy is supposed to say spam. Okay. So I can always express classification kind of tasks as generative tasks, and therefore then do a whole bunch of understanding scenarios as well. Generate the class label as text itself. And that is how basically they were able to show that if you have a classification task, I can give the input as a start token, a special token, and then give the text, and then just give this extra token called extract. And then my GPT transformer is going to essentially, basically generate the next token. And hopefully, if I have fine-tuned it to generate spam or not spam, at test time also, when I give it a new email, it will basically just generate spam or not spam. Make sense? Sorry? At pre-training time, it was unlabeled. Remember, at fine-tune time, you have to have labeled data. Fine-tuning is always done on labeled data, task-specific labeled data. Okay. 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 Yeah. Yeah. That's not the case with other decoder paradigms. Which decoder paradigms? Huh. That's right. So models which are trained on multilingual, clearly you can do that. But models which are not trained on multilingual data, you cannot do that. Okay. In fact, transformer decoders in general, yeah, I mean, they can be used if they are multilingual in nature. Then they can be used for translation. GPT-1 model was not trained on multilingual data. It was just trained on English. Okay. Okay. Uh-huh. That's right. Yeah. Yeah. Absolutely. You can train a domain specific GPT model, but then if you yeah, you can fine tune it, but then, then that's not called fine tuning. That's still called as domain specific pre-training. Actually, it's called DAPT, domain adaptation based pre-training. So unless you have a task in mind, if you have a task in mind, you will have labeled fine tuning data for it. Otherwise, it's just called pre-training. Yeah. I mean, what is the goal, right? So basically, why would you want to, let's call it generically train, on finance data? Why would you want to do that? Domains what? Those kinds of text I understood, but what is the application? What would you use it for? Next word prediction in finance? So then it is still called as basically pre-training. It's not called, fine-tuning. Fine-tuning is typically done on labeled data, and that too for a particular task in mind. If it's just next word prediction, you're just saying you're changing your pre-training corpus to finance domain. That's all. Okay? Yeah? Huh. For that particular kind of thing, well, it's called domain adaptation. I mean, I would basically just call it domain adapted pre-training. So, and until it is pre-training, and so the idea is the tag called fine tuning is applied to labeled data. Until you are not using labeled data, you keep calling it pre-training, and then you can basically, of course, pre-train it with whatever kind of task, kind of data that you like, in French data or legal data or any kind of data. It's still called pre-training until you're not using any labeled data for a particular end application in mind. Okay? Okay? Good. So basically they said that, hey, I mean, you could use the pre-trained model and fine-tune it for various kinds of tasks. For classification tasks, which take one text string as input, it could be like a review for sentiment analysis or email for spam versus no spam kind of case and so on. Or it could be also used for cases which take two pieces of text. So there are some classification applications which can take two pieces of text, like like text entailment. So given two sentences, tell me whether the second sentence is contradictory or supportive of the first sentence. Okay? So the first sentence called premise, the second one is called hypothesis. So you can give both the sentences with some special tokens: start token, delimiter token, extract token, and given lots of labeled data for this text entailment problem, you could basically then predict whether it is a contradiction or supporting or neither of the two. Okay. So you could also use it for figuring out similarity between strings. So these are other tasks that people do typically with text. They want to basically do text classification given one piece of text, or text classification given two pieces of text, figure out similarity between two strings, try to answer question answering, but with multiple choice questions. So if I have only 4 options, then I have to just select A, B, C, D, which one is correct, right? All of those could be done with GPT, is what they wanted to show. So they basically wanted to show that GPT is a very, very generalized model, could be used not just for actually creating text, generating more text, but can also be used for doing all of these kinds of other tasks as well. If you have enough amount of fine-tuning data, enough amount of labeled data. Okay. Questions? Any questions? What will be the process? Yeah, I mean, here essentially you need labeled data. And the way you do that is basically if you have like text 1, text 2, and you have some label associated with it, how similar they are, you can train GPT or fine tune GPT to so as to be able to figure out similarity. Yeah. Sorry, I'm IPC and Indian Penal Code. Yeah, yeah. Uh, uh. Huh. No, I don't understand the question. You are saying you have two text strings and then you are asking, okay, what is the benefit in using transformers? Uh-huh. Oh, mapping. Yeah. See, I mean, see, these models are not God. Okay. So they basically have to be trained. If you have trained them for a purpose, they'll work for that purpose. Otherwise, they will not. So essentially, if there is this new knowledge, let's say basically for that matter, right? Let me basically rename, what, Kerala to Keralam tomorrow, right? There is no knowledge around the world. Now, if you basically ask GPT model, hey, what will Modi rename, Prayagraj to in 2026? It can't tell you. How the hell can it tell you? Even Modi doesn't know that, right? So you're asking it to behave like God. So that doesn't work. If you have labeled data and that knowledge is generic enough, then it can learn from that labeled data. Else not. These models are not godly that they can predict, forecast the future without any patterns, right? Check the similarity, exactly. See, that's again a different problem to do, but mainly the way you would do that is basically based on labeled data. If you had enough labeled data to capture certain kinds of similar patterns, you could basically capture that similarity. If not, then you cannot. So for example, if all your labeled data said was that, hey, ABC is whatever is the full form of ABC, right? So full forms is one kind of similarity. Semantic similarity is another kind of similarity. So if all your examples had was syntactic similarity, it can't learn semantic similarity in that sense to do semantic similarity. Yeah. GPT cannot do plagiarism check. Why not? Absolutely. If you have not fine-tuned it to do so. Absolutely. And GPT-1. So we'll basically, of course, talk about later models. GPT-1 couldn't do that. In 2018, the model that you had surely couldn't do that. Okay? Because they had two parts, pre-training and fine-tuning. Unlike the latest GPT models, where the pre-trained model is so awesome and thousands of times larger than the current, than the GPT-1 model that we're talking about. Okay? Okay. Any other questions, folks? All good ones, interesting things. Yeah, I mean, the way this field has progressed is crazy and fun. The point is, the problem is that people see the way the field is today from an application standpoint, and then they're trying to relate to, hey, what it was like 6 years back in time, right? So today, what is called as zero-shot inferences, right? The word zero-shot, the phrase zero-shot did not exist at that time. So therefore, there is no way that you can expect it to be able to also do, similarity checks 6 years back in time. Okay? But anyway, yeah. So coming back, right? What OpenAI said is fine. I mean, you can basically pre-train it for next word prediction tasks, large amounts of unlabeled data, and then if you have a particular task in mind, fine-tune it based on that task. Okay. So in 2019, OpenAI basically started coming up with larger models. Okay. So GPT model was pretty small. It's basically just a 12-layer decoder, and 12-layer decoder was a few 100 million parameters. That's it. Okay? Of course, it is way larger compared to your RNNs and LSTMs, but it is basically just a few 100 million parameters. Okay? Now, to put things in perspective, right? Our human nervous system contains 10 raised to 11 neurons. Okay? So, and each of those neurons is connected to 1,000 to 10,000 other neurons. Okay? So basically, our system basically has at least that many connections. Okay? That's basically 100 trillion connections. A trillion is 10 raised to 12, and that's 100 trillion connections. Okay? So GPT 3.5 is rumored to be 2 trillion, about 2 trillion. Okay? 2 trillion parameters. Of course, I don't think they ever publicly mentioned how many it has, but 2 trillion. Okay? GPT-4, nobody knows. Who knows? Even at Microsoft, don't get to know how much is the number of parameters in that model, right? So, but whatever it is still not close to a human brain. Okay? It is still not close to human brain. Okay? And we're talking about in 2018 when these were like a few 100 million parameters. Okay? Over time, of course, OpenAI got more and more compute power, but they still kept believing in the same idea: next word prediction. I'll only do next token prediction more correctly, right? But build deeper and deeper models. So GPT-2 small, which was 12-layer, GPT-2 medium, large, extra large, and so on. So 48-layer models. So they were able to build the first 1.5, billion parameter range model, a 1.5 billion parameter model. Okay? So this was 2019. They basically built a model which was way larger, 48-layer deep model. And fortunately, thanks to residual connections, this model could also be trained really nicely. I mean, it worked fine. It didn't have any degradation with increase in depth. And it actually was better in terms of quality compared to GPT-2 small or GPT-1 model itself. Okay? And you see, now going by the paper names, right? So if you notice the name, language models are unsupervised multitask learners. So they basically said in 2019, people were starting to think, hey, pre-training and fine-tuning is good, but that's not how the human brain works, right? I mean, essentially, when we grow, we sort of tend to learn tasks. Our single brain tends to learn so many tasks, right? It's not like I have one brain for spam classification, another brain for translation, and another brain for some other understanding and so on. I have only one brain, and it is a multitask learner. It can actually do all of those. Okay? So can I actually train a multitask learner without the need for fine-tuning? Okay? That is when they started asking this question. Okay? And they said, okay, the only way seemingly is to basically just increase the size of the model and see if it has enough capacity. Okay? The technical term is really capacity to be able to actually capture multiple tasks together and do it together. Okay? So GPT-2, of course, not just larger size, but also it was trained on 8 million documents for a total of 40 GB text. So it was trained on way larger. Remember, 7,000 books versus 8 million documents. So it was way better, way more, way better. So architecture is still the same, transformer decoder, nothing much changed there. Okay, but what they started showing is that this zero-shot learning is possible. What does that mean? That basically means that pre-training is enough. Okay? At fine-tuning time, you need to, the model was just pre-trained for next word prediction. Tell me the next word, next word, next word. And then they said, okay, now let me ask this model to do spam classification. Matlab kya ke? I'll give an email and then I'll literally tell it, hey, tell me whether it is spam or not. And it must be able to generate the next token spam or not spam, even without you fine-tuning on spam or not spam data set. Okay? So no labeled data is required. All you need is this pre-trained checkpoint, download it from Hugging Face, right? And basically just ask it to do whatever task you have in mind. Okay? So that's called zero-shot learning. Okay? And that is where this term called prompt engineering started off. That, hey, how do you ask this model to be able to do that task, right? And that's basically what is called as prompt engineering, being able to tell it, given two strings, tell me whether they are similar or not, right? Or how similar they are. Sure, I mean, you have to basically tell it in some form. If you tell it in that form, hopefully it listens to you and, tells you that that's the answer, okay? Now, of course, this was 2019. And if things were so successful in 2019, people won't be learning chat, or rather talking about prompt engineering and ChatGPT now, right? They talk about it now because at that time, the accuracy was poor. Okay? Yeah, of course, you could do that, but the accuracy was dismal, okay? So more accurate, more concretely, I'll talk about the accuracy. They brought in this concept. So this basically requires a whole bunch of trust in your idea. In 2019, OpenAI had enough trust in their idea that if you keep putting more and more compute power, you will be able to get a model which basically at the end of it will not need any specific learning. You can basically just pre-train it using unlabeled data. At the end of it, it will basically be such an awesome learner that you can actually ask it by prompting and it will do what you ask it for. Okay? But in 2019, things were not so rosy. Basically, these charts basically tell you, there's a chart at the top also, but I'll ignore that. Let's look at the charts, look at the things at the bottom. Okay? There are 4 different tasks: reading comprehension, translation, summarization, question answering. All of us know those tasks. Reading comprehension basically means you are given a large passage and you have a question and you have to answer based on that passage. Come up with an answer, generate an answer. Okay? Translation, of course, everyone knows. Summarization is summarization, question answering, right? So that's that. Now, basically, what you see on the x-axis is the size of these models, a number of parameters in these models. Okay, and as we said, GPT-2 had like 4 different sizes, so that is why you have like 4 points on each of those curves. Okay, on the y-axis is accuracy. So basically, in some ways, so for reading comprehension, it's F1, for translation, it's blue score, and so on and so forth. Some accuracy metric. Okay, so the dotted lines basically show you standard systems which were fine-tuned to be able to do those tasks. The state-of-the-art systems in 2019. Okay, so for reading comprehension, and of course, there's human baselines also in some cases. So human could basically accurately identify the answer in 90% cases. The best system could do around 60, 65, 68, whatever it is, right, and so on. But you see this zero-shot model, it basically means a pre-trained model just for next word prediction, and you basically then tell it, hey, answer this question. No? That guy couldn't do much. I mean, as you notice, it was way worse than human. So many points, 40, maybe 35 to 40 points worse than human. Okay. Now, no journalist would have basically talked about this kind of a model, right? 5 years back in time. It's not practical. It's useless, right? People would say, academic paper, that's enough. That's all, right? But this is the kind of gap that is closed in the past 5 years, which is why now even the rickshawala knows what ChatGPT is, right? But 5 years back in time, yes, you could do that. OpenAI said, yes, you can actually do zero-shot training, but that's the kind of accuracy gap that you have. Okay? Translation, yeah, I mean, if you basically use statistical machine translation, what does statistical machine translation mean? Machine translation before the deep learning era, before 2014, actually, which never used any deep learning, right? Yeah, I mean, that was actually way better compared to the best GPT model, right? Summarization, yes. I mean, open domain question answering, yeah, I mean, if you compare it to some human baselines, it will be really, really bad on several data sets. Okay? The models were worse. But there was a green lining, there was a silver lining. What was the awesome part? The awesome part is that all of those curves that you see are increasing. What does that tell you? That tells me that if I have really large models, maybe at some point I'll be able to compete with the best systems out there. Okay? So that was the hope. In most cases, as you increase the model complexity, as you increase the number of parameters, you would see that this curve is going up and up and up. So which basically means that there is scope to explore more. But even then, if you look at these things in 2019, 5 years back in time, it could actually do question answering, awesome question answering that an average human does not know answers to, right? So, for example, who wrote the book, The Origin of Species, right? And it could actually generate Charles Darwin, it could actually generate those tokens automatically. And that was the first time that people actually saw that, hey, here is a model, and you ask whatever question. It's like, hey, here's a model, ask whatever question, right? And it basically generates answers. Of course, it generates many, many wrong answers. These are handpicked, some top few questions that it answered correctly or inaccurately. But, it could do some magic, some level of magic, right? Not as good as current GPT, but GPT-2 was still good, okay? What is interesting is that it was pre-trained for next word completion, and you could use it for really good next word completion. Okay, so at the top are the context. Those are the things that you would give as input. Okay, I mean, of course, in today's world we call them as prompts, but this is the input that you would give, the context, and it would come up with these generations, these outputs. Okay, and if you read them, you would realize that they are not bad. I mean, if you look at them, even 5 years back in time, the output was not really too bad. It was reasonably okay. So next word completion was really a greatly solved task, even at that point. Of course, there's a crazy amount of hallucination and sometimes bad grammar as well. But that's 5 years back in time. So it was doing very good job in that sense, if you think from 5 years old perspective. Okay? It was able to actually copy some styles also. So for example, in the input, if you said outfit 1, it would generate output 2. I mean, assuming that, hey, somebody is typing about a list. So yeah, I mean, let's basically carry that kind of style of writing text. Okay. And it could generate recipes also. So given this input, these are various completions which are generated by the GPT model. So it could generate things. Okay? 5 years back in time also, it could generate reasonable things. It could basically, so this is again 5 years back in time. And this is the way that this input was provided. So OpenAI in 2019 actually started this concept of in-context learning. What does that mean? That basically means that if you give a paragraph and you tell it that, hey, these are the ways in which you can, one example of how you could answer a question. Okay? So you basically give the passage and also give an example at test time itself. This is a question, this should be the answer. It will learn the task. So you don't need to really specifically train for this task. It will learn the task, understand the task at runtime itself, inference time. And then if you give a question, new question, it will be able to come with the answer. Okay? So this concept basically is different from fine tuning. They've said that, hey, GPT-2 model is so good that you don't need the fine tuning stage at all. Pre-training is good enough. Pre-training is good enough. And at test time, what you could do is just give any new task, and if possible, also give an example to explain that task to it at test time, not fine-tune time. So no backpropagation required at test time. Give one example. I think in this paper they never bothered about giving more examples. Just one example, and it knows how to do that task. It knows how to do that task. Okay. There are more examples here. I'll skip them. But what was very interesting to me, 5 years back when I used to teach this thing, what was really, really interesting and a little bit of a worry is that it was able to generate articles which really looked like real news articles. Okay? So which looked like real news articles. Okay? And this was the first time that GPT became very popular in press as well. So several people essentially got to know about GPT even 5 years back, because the way journalists would put up is that, hey, here is a model which can actually generate fake news. So the deep fakes as a terminology, deep fake as a terminology became popular 5 years back thanks to this example. So what is this example about? This example is basically saying that, hey, in the first few tokens in the GPT transformer decoder, you actually feed in this. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. Okay? And then you ask GPT to continue. So of course, unicorns don't exist, right? Essentially, if you talk to a villager and you tell them scientists have figured out unicorns somewhere in the Andes Mountains, usko to ye bhi nahi pata Andes kidhar hai, right? So basically, yeah, I mean, if you say that scientists have found, this guy is going to believe it clearly. Especially if you support it with awesome facts, like the scientist is George Perez. I mean, what is this guy going to ask you? He's going to ask you more details, right? Which scientist found that? And you tell which scientist, right? And you tell which university they belong to, and you tell several other things, like what do they speak? They speak perfect English, and so on and so forth. Okay, so that's the interesting part. I mean, you could generate fake text which is constructed so well that it really looks like written by some good news reporter. Okay. And what do you believe in, by the way, right? Do you really go and check on the at the situation, hey, did this event happen or not? You just believe press, right? You just believe media. So you believe articles as they come to you. If they come from Times of India, you're like, हाँ ठीक है, होगा, मतलब हुआ होगा ऐसा, right? I mean, you don't really go and check. You don't call up the person and check, हाँ accident हुआ क्या, right? I mean, you believe in that, right? So that's the thing, right? I mean, and that was very worrisome because fake text generation, fake news generation is so simple now. Go ahead. This is the prompt. That's it. There was no other prompt tokens, so to say. It's just next word completion task. You don't need any specific tokens. You just give this text as prompt. That's it. Yeah, it will continue to generate. That's it. You don't need to give it any prompt as such, because next word completion is what it is meant to do anyway. Oh, so next word completion is always meant to generate several words. It's not meant to generate only the next word. Yeah. I mean, next word completion task, yeah, although you train, a good point, yeah. You train it for one word, but then you give that word as input for the next token, and then you generate the next token, and then you keep doing it until you meet something called as the end of sequence token, a special token. That's right. It's basically because of pre-trained data. In the pre-training data, of course, it would have read several stories also about unicorns and so on and so forth. It's basically trying to understand all of that and reason over it in that sense, is given those 12 layers or whatever. I mean, 48 layers of reasoning on top of that input data. Okay. Questions? More questions? No. How does it know? Good point. So basically, I mean, when you are pre-training, you typically, it's just next word completion in that senses. So at that point, it does not know how to stop. And therefore, you basically just let it generate until it generates an end of sequence token. It may generate an end of sequence token if it has been pre-trained in that manner. But if not, you basically just say maximum so many tokens. Okay. So now, when you generate things using these models, every token generation has some latency. So especially, let's say, next word completion, query auto completion, when you see that drop down, right, it basically generates stuff, right? And there, if you generate, let's say, 100 tokens, it will take forever to generate. So therefore, you basically stop it and give a max limit, saying, hey, 5 tokens only, and then just stop whatever you generate. Okay? Or you basically fine tune it in a manner, especially for query logs, right? You know that queries are of this kind, right? So you fine tune it such that you add an end of sequence token at the end so that it knows when to stop to generate the end of sequence of the token itself. Okay? Huh. Yeah. Yeah, the accuracy of the zero shot learners. Yeah. They measure according to how the words are arranged. If these words are these words present, if they are present, how they are arranged according to that word. If it is outputting, it is different words, or if the sentence is paraphrased. That's right. That's right. Oh, absolutely, absolutely. But that's another philosophical discussion on NLG metrics, right? So essentially, which natural language generation metrics are good, right? And again, you can ask this question in today's world. In the world in 2019, these were the metrics that you could use. Okay. In today's world, yes, people don't like Blue and Rouge because they are syntactic metrics, as you call them, right? So in today's world, you have other metrics called as you know them, huh? Huh. No, don't mix several concepts, okay? Human eval is something else, MMLU is something else. Don't mix those concepts. Metrics include things like Meteor, CIDR, DEB. They are semantic metrics, which basically look at two pieces of text and then they say, hey, they are semantically similar, and therefore let me consider it as accurate. Okay? So human eval is different. Human eval is a software engineering benchmark, by the way. Human evaluation is different. Human evaluation basically means a human actually looks at it and says, oh, this is the same meaning. Okay? MMLU is completely different. MMLU is in fact a data set or a benchmark. Okay? Uh, no. Well, yes, but they are not for NLG evaluation. They are not to solve the problem that you brought up. That hey, Blue and Rouge are metrics which care about syntactic match between words. To solve that problem exactly, there are metrics like Meteor, METEOR, or CIDR, CIDER, or DEB, right? Look up those metrics. So they are the correct ones, but they came after 2019. In 2019, these are the metrics people used to use for evaluation. Which score? There might be several scores, man. Yeah. I mean, there are like 100 plus NLG metrics. So clearly there are more than what I can name here. Yeah. That's right. Yeah. At least in the GPT story, that there has not been. I mean, in the GPT story, it has just been that they took the same transformer decoder architecture and just increased the scale and scale and scale with minor changes in the architecture. Okay? There are some minor changes that I'll talk about slightly, but mainly it has been just the same architecture, self-attention and feed forward. That's it. Okay? And increase the scale, increase the quality of data set. So that has mattered. So what is the kind of data set you pre-train on? So good quality data sets lead to better results and so on. Yeah. Quality of the model, you mean? Oh, acha, quality of the data set that is used for training. Good point. Yeah. Now that's a question, right? So how can you judge the quality? So of course, that's a question that we at search engine companies also have to deal with. So somebody is coming up with a query. We don't want to show low quality documents at the top. Right? We always want to show high quality documents. Now, so how can you basically judge the quality of documents? Well, there are several ways of doing that. PageRank score being one, and many other things. Right? Yeah. Okay. Go ahead. So this pre-training is also called self-supervised learning. Basically, you are using next word prediction. Na koi label karke nahi diya hai. It's like self-supervised. You're basically just using the existing labels. That's right. Yeah. Yeah. This is also called as self-supervised learning. The pre-training is also called self-supervised learning because like you're basically automatically getting the labels without any extra human effort. Hmm. Well, at least they claim so. So essentially, if you look at the GPT-4o videos, you will see that they claim that they are very good at understanding text and images together, text and audio, text and video, and so on. Hmm? Hmm. Where the model has to understand what is the summarization task by giving it to itself. We'll talk about that, right? I mean, of course, if you have labeled data, then you expect the model to get better. But there are a few catch. There's a little bit of a catch there, right? First, you need to have labeled data. Second, you need to have compute power to be able to do fine tuning, right? If I give you a trillion size model, you can't even load the model. I mean, how will you fine tune is the question. Yeah. So exactly. So hold on, right? I'm not talked about few shot at all. I mean, so you'll get there. Yeah. Yeah. So basically, in 2019, people were like, yeah. I mean, if you basically just give a large amount of training data and you train those models, deeper models, you can actually afford to do away with the fine tuning aspect, especially if you also give examples at test time for it to learn from. Okay? And it started becoming like complex when you could actually generate entire articles which look like human written articles about various about various topics, even fictional topics like this. Okay. GPT-3 paper, language models are few shot learners. And this is where OpenAI brought in this concept of few shot learning, or in fact, the concept of in context learning more specifically. They said that we categorically now do not want any fine tuning to be done. So they said that, hey, just zero shot is enough. And clearly, they showed way better accuracy compared to GPT-2. So this was 2020, right? And they actually started training models like 175 billion parameter models. This is like, this is like 100 times larger than the largest GPT-2 model. GPT-2 model, if you remember, was 1.5 billion parameters. This is 175 billion parameters in size, okay? So with such a large model, they basically said that, hey, we don't really need any fine tuning. Just zero shot learning is good. Zero shot meaning, you just tell it at runtime any new task and it will be able to come up with an answer for that task, right? You'll be able to generate very good outputs. Okay? So they said that the traditional way of learning is as follows. You basically have a pre-trained model like GPT-1 or GPT-2, and then you do fine tuning. So if you wanted it to learn how to do English to French translation, you will have to fine tune it, let's say, on 1,000 labeled examples. Okay? You'll have to tell it, hey, these are English examples, these are the French outputs, and then you fine tune the model. Okay? And fine tuning the model basically meant that you have to do gradient updates, you have to do backpropagation over the model. Okay? But with GPT-3, you did not need to do any fine tuning. They said that, hey, at test time itself, you take the pre-trained model, at test time, just directly tell it, translate English to French, and then give it the word cheese. And with a very good probability, it will come up with the right translation for the word cheese. And then they said that, hey, not just that this zero shot guy is good, but if you really wanted to improve the accuracy, you could make it one shot in the sense that at test time, you can give it one example just to understand how this thing is done. Okay. But again, this is at test time. So you don't do any gradient updates. You don't do any fine tuning. At test time, just give one example. Or if you have more examples, just give them at test time itself. Okay. A few examples. And then those are called as zero shot or one shot or few shot. Learning, in context learning. It's called in context learning because you don't do fine tuning with these examples. You basically just tell them how to do that stuff. Okay? So consider an office boy, right? Now the office boy basically does not know all the tasks. So I mean, of course, the guy is a good guy, basically understands how things are done. But let's say if I have to tell this guy, how to look at an email and either ignore or tell me to read it. Okay. So essentially, I want this guy to act as a filter before the email actually comes to me, right? I just need to give him 2 or 3 examples that, hey, देखो अभी ऐसा random email आया तो उसको पढ़ो और तुम्हें basically just reply कर दो तो चाहिए, right? You just reply back whatever, right? But if it is a useful email, coming from some credible place and so on, I just tell him like 2 or 3 rules and just tell him 2 or 3 things, and the guy learns really well. Okay. So that's basically exactly what in-context learning means. You don't really give it many examples and fine-tune, but you just tell a pre-trained model, you basically at test time itself, just give it like 2 or 3 examples, and it learns how this is done, okay? At test time itself, and does it really well. So that's basically what we call as ChatGPT today, right? Basically, if you want to get some task done, yeah, you basically just prompt you just describe the task, and then maybe give it like 2 examples. If you give 2 examples, you actually end up getting better results compared to not giving examples in that sense. Okay. So in 2020, these guys figured out that if you increase the number of examples in the context, so in the context at test time when you're giving examples, if you increase the number of examples, typically your accuracy improves. Okay. Also, what they found was, of course, larger models give you better results. So these are accuracies over several tasks, so averaged over several tasks. If you basically give 0 examples, you get poor accuracies. But the moment you start giving 10 examples in the context with 175 billion parameter models, your average accuracy across many tasks is across like 42 different tasks is basically much higher compared to giving 0 examples. Okay. Or compared to basically having just a 1.3 billion parameter model. So they said that there's something interesting about the size of the model. If you basically scale it up 100 times, right? Suddenly, the accuracy crazily increases. And also the accuracy increases if you have a few examples rather than 0 examples at test time. Okay? Few examples rather than 0 examples at test time. So that's that. And at this point, people also started questioning how much compute power it takes to train these kinds of models. Now, GPT-3 was possible because of Microsoft funding. So there was a whole bunch of funding to be able to procure crazy number of GPUs. At this point, there is no other data center as large as the one that OpenAI has. Even inside Microsoft, we don't have that kind of compute power that is funded to OpenAI to basically build large models. Okay? So there is no other parallel system on the planet which basically allows you to do this kind of pre-training. Okay? That OpenAI can afford to do because what they have right now. So, but anyway, GPT-3 was trained on very large amounts of data. So data coming from Common Crawl, which is a web snapshot. So web crawl, right? Web text 2, which is a cleaned version. Books corpus, Wikipedia. So lots of books, openly available books, Wikipedia as well. So all of that was used so as to train these GPT-3 models. Okay? So much larger compute power, much larger amount of data so as to train these models. Of course, it takes a huge amount of compute power as well. So the compute power to train this model was larger than any other model that was ever trained, in terms of petaflops per day of compute power that is required. Okay. But the output was really awesome. Now it could basically generate things which no other model could do. Right. So no other model could basically generate news articles just given the title of the news article. You could do news article generation. You could also define new tasks like this. So you could basically tell it that, hey, this is a new word usage task, in the sense that I'll give you a word, I'll tell you what it is defined as. It's a new word, never there in the vocabulary, right? And you have to create a sentence using that word. Okay? The gray ones are the ones that are input. The black one is the output. Okay? So you can tell it, let's say that Watpu is it is a fictional word, but Watpu is a word which is a small furry animal native to Tanzania, right? And then here is a sentence, if Watpu was an animal of that kind, what is the sentence that makes sense? We were traveling in Africa and we saw these very cute Watpus. Okay? And then you can basically say, now that you've understood the task, I'll give you a new word called fardaddle. That basically means jumping up and down really fast. Generate a sentence which uses this new word. It could solve that task, right? It could solve such new tasks for which there is no labeled data. There is only one labeled text example that you gave as part of the context itself. Okay. It was able to do English grammar correction and many other things like poem generation. Okay. So in fact, I started using it to actually put out abstracts for talks. So essentially, rather than giving the abstract as normal text, it's fun to actually give abstract as a poem. Okay. Uh, uh, yeah, I mean, you didn't really need to be creative to become a poet. You could basically just use GPT. Okay. Uh, and you could and basically GPT-3 fan pages started coming up. There are many websites, GPT fan websites, basically where people have come up with interesting tasks like converting movie names to emojis or or other things like coming up with SQL queries to be able to take a natural language query and a database schema and come up with SQL to answer that query. Right. So there are many such examples where people started using GPT. Okay. Of course, there are limitations. So the first limitation was model was not bidirectional. So which basically means that it only has forward learning. It doesn't have backward learning. And sometimes backward learning is important. So for example, in normal text, to be able to understand that certain word is an adjective, it's good to know that the next word is a noun, because the probability of this word being adjective increases if the next word is a noun. Right? So backward learning, bidirectional learning is important. So model is not bidirectional. It is too large. The model is too large, right? So essentially, GPT-3 model, 175 billion parameter model, you can't load on a phone anyway, right? 175 billion parameters, no way, right? And of course, all of these large language models have known problems like biases, toxicity generation, offensive stuff generation. If you basically have a drop down, Modi is a, now you have to be very careful. It should not generate things like moron, right? What if it generates moron in the drop down, right? Or Deepika Padukone dances like a, what if it generates monkey, right? And so on, right? So basically, yeah, I mean, we live in a very offensive world. After all, we train these models using query logs, and query logs are query logs. I'm sure you have also typed several offensive queries several times, right? So we use all of this collective information to train these models. And unfortunately, when you train these models on offensive data, you end up having models which generate offense. And that's very bad, right? Because it's okay in academia, but not good in industry, right? I mean, not good when you want to show it off as Microsoft product. Yeah. Because they push for bigger models and more. Yeah, I don't know what was the exact thought process they had, but they were basically trying to see whatever you can get. See, bidirectionality has its problems also, because that also means less efficiency while training, right? You have to care for other side as well. So there are pros and cons of both the things. There's a trade-off. Clearly, there's a trade-off. Okay. So few shot learning is a kind of in-context learning. In-context learning क्या होता है? You have a pre-trained model, and in the prompt itself, you basically give whatever for it to learn. That's called in-context learning, because in the context itself, you give whatever to learn, right? And in-context learning could be of three kinds: zero shot, one shot, or few shot. So few shot matlab kya ke in the prompt that you give, you of course give the task description, but you also give a few examples for it to understand the task more clearly. Okay? Or if you give zero examples, it's called zero shot learning. If you give one example, it's called one shot learning. If you give few examples, it's called few shot in context learning. Okay. That's right. See, so here in the in-context learning, it's not like you are updating the parameters. So it will not overfit. And because you are basically just giving it at test time, just telling it, I mean, it's basically just using it to compute, to condition on the previous text. It's not updating its parameters. And therefore, there's no question of overfitting. Sense? Okay. We continue. There are several things to discuss. So we'll maybe talk about BERT as well. And then I'll switch over to code, because that will be a nice break from this monotonous discussion in that senses. Okay. But as usual, please feel free to ask questions also. Okay. Yeah. So we have talked about the transformer decoder so far. Okay. So we talked about GPT, and we saw how OpenAI went on its journey of trying to just explore the transformer decoder. and train it with the way larger amount of data, way deeper models, so as to get the zero shot or just the in context learning based models that we see today. Okay? Let's talk about the other journey called BERT. Okay? And in fact, in several of these things, we need to be very, very thankful to Google, because I mean, if it was not for Google making the source code for transformers publicly available, none of this would have been built on top of it. 2017, Google just made transformers publicly available. Similarly, in 2018, they made BERT publicly available, and several of the models that we see today are actually built on top of that. Maybe OpenAI, Microsoft might have come up with similar things later, but it's just that it improved the progress in this field, made it faster. Right? So BERT, unlike GPT, which is basically decoder based, BERT is encoder based. So it's basically bidirectional, basically saying the self-attention layer pays focus on the left side and the right side both. So essentially, it's the transformer encoder architecture. Okay? That's basically the main difference in the architecture part. So of course, each layer has two sublayers: self-attention sublayer and the feed-forward sublayer. In 2019 time period, Google released two checkpoints, BERT base and BERT large. So of course, they pre-trained it, and we'll talk about how the pre-training was done. But they actually put out two checkpoints publicly. I mean, well, talking about the GPT guy, well, GPT-1, GPT-2, OpenAI made them publicly available. GPT-3, there were like several variants. The largest two variants, OpenAI did not make publicly available, did not make them publicly available. In fact, that was the time when people started putting up these sections called as ethical considerations in their papers. Before, 5 years back in time, nobody bothered about ethical considerations in that senses. And the GPT-3 paper had a very interesting and a fancy ethical consideration section, where they basically said, hey, we are too worried about fake news being generated using these models, and therefore will not make these models publicly available. Okay? So that narrative by itself was a little screwed up, because, well, I mean, you're making an API publicly available anyway, so why not make their models also publicly available? But anyway, right, I mean, they did never release the largest GPT-3 models. Other people actually, repeated that same framework, and they retrained and made those publicly available. GPT-4 models are not public anyway. They are only APIs that one can use. Right? Similarly, there are models from Anthropic, Claude models. There are models like Gemini from Google, which are not available as public models, but you can use them as APIs. Right? Now, on the encoder side, BERT models, yes, I mean, these BERT models were made publicly available by Google, the BERT small and BERT base and BERT large. BERT base is 12 layer, as you see, right? And BERT large is a 24 layer model. Okay? They have different kinds of attention heads. So BERT base basically has 12 layers, 12 attention heads. BERT large has 16 attention heads. And they have differing dimension as well. So essentially 768 sized representations for BERT base, and BERT large is 1024 sized representations. And accordingly, the number of parameters differ. So BERT base is 110 million parameters. BERT large is 340 million parameters. Okay? Now, if you think about it, these number of parameters are still very large. On one side, they're too large. But if you compare with the human brain, of course, they're too small, right? So, but if you think about, let's say, being able to ship or productionize a BERT-based model as part of Windows, edge browser, right? If you basically use BERT-based model to do something in your browser or something in Windows, users won't really prefer such large RAM usage. Okay? So therefore, in Windows, in Edge browser, we are trying to productionize these kinds of models, but the limits are effectively maybe 20 MB RAM. That's all. So which basically means I can't use these models as it is. So I have to somehow compress them, and that is where this entire large literature of model compression or parameter efficient tuning and so on become very important. Okay? But again, that is out of scope, so we'll not talk about that. Let's basically talk about how did they pre-train these BERT models, right? BERT base, BERT large models. So pre-training was again done using unlabeled data, using these two loss functions this time, something called as masked language modeling and next sentence prediction. Okay? So don't confuse this masked language modeling with the masking that we talked about in a traditional transformer architecture. So masked self-attention is different, right? That's on the decoder side, and this masked language modeling is different. Okay. So we'll talk about this master language modeling and the next sentence prediction. But BERT always believed in the two-step training. So they always said, hey, we'll pre-train, we'll basically make a model which understands English well, and then we'll fine-tune it for particular tasks. So first stage is always going to be this pre-training phase, first phase. And then in the second phase, we will fine-tune. Okay? The pre-training is going to make this model learn English. It's going to make it a generic English-based model. Fine-tuning is going to make it work nicely for particular tasks like natural language inference, named entity recognition, or question answering, and so on. So you can make it work for several tasks. But hey, yeah, so but that is going to be a part of fine-tuning. Okay? So pre-training is unlabeled. So you basically use unlabeled data. For fine-tuning, you will actually use labeled data for that particular domain, labeled data for that particular task, Okay. Now the BERT model actually uses the word piece embeddings that we talked about in the morning, right? With a 30K vocabulary size, so 30,000 vocabulary size. Okay. The inputs to the BERT model look like that. So remember in the transformer, I told you there are two inputs per position, the token embeddings, and then there is also position embeddings. In BERT, there are three parts. The first part is the token embeddings, as you see there, the yellow ones, right? The green ones, and then there are position embeddings. So token embeddings and position embeddings you already know about. There's also something called a segment embeddings. Okay? By definition or by the nature of it, BERT model has been pre-trained to take two sentences as input. Okay? So of course, if you have one sentence, you can always say that the second sentence is empty. Okay? But by definition, it has been pre-trained to take two sentences as input. For the first sentence, you would use a specific embedding. For the second sentence, you would use another embedding. So first sentence EA, second sentence EB in that sense. Okay? So to indicate that this token belongs to the first sentence or the second sentence, you have this segment embeddings. Okay? So you have three inputs basically per position: token embedding, segment embeddings, position embeddings. You add all of them, and you give that as input to the first encoder layer. Okay. You see, so basically, for example, the input here is my dog is cute, he likes playing, right? Now, when you give these two sentences input, you have to separate them. So you have a special token called as a separator token, which is not just the separator, but also a delimiter to say that, hey, my input has finished here. Okay? And before you give any input, you prepend again with a special token called as the CLS or the classification token. So just like GPT had special tokens, if you remember, there was a start, delimiter, and extract tokens, right? Here also there are special tokens. They're called as the CLS, classification token, and the separator token. The CLS token is always the first token in the BERT input, and the separator token are basically there to separate sentences which are fed as part of the input. Okay. Any questions about how the input works for BERT? Any? We will get to know that very soon. So it plays a very big role in classification, and that's why it's called, BERT is used for classification tasks, but the way classification is done really depends on that token, and we'll talk about that. That is why it's called classification token. Sorry, they're two different text embedding. Oh, so see, there is no embedding for the sentence as such. So in a transformer encoder, there is an embedding per token, exactly. So there's no embedding for the sentence as such. Oh, segment embeddings. Oh, okay. Yeah. So there is one fixed thing for EA and another fixed vector for EB. Yeah? It's randomly initialized and trained over iterations. So, but it's fixed and it's used. There are only two vectors. They are basically used per token of the first sentence or per token of the second sentence. Now they are. What do you mean by deterministic? Yeah, all embeddings are deterministic. Yeah. So they are randomly initialized but trained over time. Okay? Trained over iterations. Okay. So now how is BERT model trained? So let's talk about how is it trained? How is it pre-trained? So again, the principles of pre-training: one, large amounts of data, and second, unlabeled data. Okay? Now, the way you pre-train BERT model, as we discussed in the previous slide, is basically using two different functions, MLM, two different ways, MLM and NSP, mass language modeling and next sentence prediction. What do you mean by change with model? Oh, अच्छा, oh, GPT के लिए कुछ और था, इधर कुछ और है ना? हाँ, yeah. So the change in model typically you would observe, but typically, for all transformer decoder kind of models, there are certain kinds of special tokens for. So basically, special tokens are for a kind of vocabulary. So each model that uses word piece will basically use these kinds of tokens. Each model that uses, BPE, byte pair encoding, uses certain kinds of special tokens. Okay. So let's talk about MLM. So BERT guys basically said that, hey, to be able to make a model learn English, we are going to do the same kind of thing that Word2Vec did. Okay. It's just that rather than using a single layer model, Word2Vec is a single hidden layer model, right? We will basically use an entire transformer to do that. So what they said is that, hey, I have a sentence, my dog is cute. I will basically just hide the word dog and mask it in that senses and ask the model to actually predict the word dog after 12 layers of entire processing, based on the other words in the input. So my is cute. So all of those I'll use so as to predict this hidden word. Okay? So, and that is how it will learn English. So that is how you wanted to make the model learn English. Now, if the model basically learns how to, how those words, if the model learns English, it will not predict random words out there, right? So my dog is cute is okay, my cat is cute is okay, you can't use, let's say, verb there, right? So you would typically always understand that some noun has to come there. Only if the model understands those basic principles, it can come up with the right words. Okay? So mass language modeling, what is that? It basically means, masking out certain words in the input and asking the model to actually predict those hidden words, Okay? To make it more interesting, what these guys did was, rather than actually masking just one word, you would mask out a few words. Okay? In fact, specifically, you would mask out 15% words. So if you had like 100 tokens in the input, you would mask out 15% tokens. And based on the remaining 85% tokens, you would basically try to guess those 15%. Guess those 15%. Okay? Unlabeled data, na? Because mask करने को क्या चाहिए? I mean, general sentences from any large corpus, and you basically just hide some words. Okay? Unlabeled data, right? And you ask the model to predict those hidden words. Okay? So that is the first loss. Okay? So you basically, let's say, take some tokens and you mask them out. So this token is masked, and therefore what you want to do is, at this position, you should be able to connect a dense layer, a vocabulary sized layer at this position, and hopefully that layer predicts the right word. Hmm.
It has some embedding for dog, but it doesn't have any compare it. And your input is also an input. So how does it make
dog? So you randomly initialize the embeddings with some values. So to begin with, you have some embeddings, some representations. Exactly. Eventually, it has to basically ensure that at the output layer, which is a vocabulary sized layer, it must generate the token dog, right? If it doesn't generate, then, as I said, backpropagate and update the weights. What lookup table?
Training lookup table of all the maybe 100
yeah. It's looking at a lookup table of 30K words. That's right, because it's a 30K vocabulary. That's right. Yeah. But that's a very, very, layman way of saying it. The right thing to say is, yeah, there's a dense layer of 30K size, and it's trying to come up with a softmax distribution on top of it. And hopefully the probability associated with the right token is highest. Right? So that's the right thing. Okay, cool. So that's one way of training. But then, to make it even more fancier, what they did was, for those 15% tokens which you chose to hide, right? You won't always hide them. Okay? So what you would do is, in 10% cases, you would not even touch them at all. Okay? You would say, my dog is cute, so dog ko dog hi rakha. You keep it as it is, right? And you basically ask the model, hey, generate the right thing there. So you're confusing the model enough to try and say, no, this should be something else. But then the model should be robust enough to say, no, no, the original word itself is correct. So there is no need to change. Okay. So in the other 10% cases, what you do is actually replace that word not with a mask token as such, not hide that, but in fact replace with some random word. Okay. So some random word which has no sensical meaning there, right? And you expect that the model will correct that word. Okay? So it's like correction rather than just fill in the blank. Okay. In the remaining 80% cases, you actually replace the word. Replace with the mask token. So the input was my dog is hairy, right? 80% of the times you'll make it my dog is mask. Mask the token, hide it, saying that yes, I'm hiding this word, and you tell me guess the word, right? 10% of the times you're going to replace it with some random word like apple. My dog is apple. Okay, and then the model is expected to basically look at that word apple and guess the right word at that position. Okay? And in the remaining 10% of the cases, you don't make any change. And then you basically just try to confuse the model saying, hey, figure out the right word. Well, the input word was the right word. It should be able to figure. Of course, you don't tell the model which, whether you've done like 1, 2, or 3 for a particular word in the input. Okay? That's that. Okay? And isn't that a good way of making a model learn English? Well, that's not the way in which we make our kids learn English. But it turns out when you have lots of data, you can actually make models learn English in this way. Okay? So that's that. Okay? I mean, and when I mean lots of data, I don't mean lots of labeled data. It's like self-labeled data or self-supervised data in that sense, is because you don't need to specially do any extra human annotations for this purpose. Right? The second task is NSP, next sentence prediction. Okay? So the task is actually very simple. So anybody, yeah, let's any Tamil person here, Tamil person, yeah. Yeah, we'll pick you, yeah, because you asked also several interesting questions, right? Yeah, okay. Now you have to basically say 2 sentences, okay? You have to say 2 sentences in Tamil, okay? Okay? Say anything, man, whatever comes to your mind. Just say 2 sentences, okay? You tell us that you are done with first sentence, and then you tell us that you're done with second sentence, because you won't understand the boundary also, okay? So, very good, okay? Second sentence, man. Very good. Yeah. Okay. So now my question, are you Tamil? No. Okay. So you tell me those 2 sentences typically, when somebody is writing Tamil text, would they write it next to each other, or are they typically you would find them in 2 different web pages, or would you typically find them next to each other? Next to each other? Seriously? Huh? Is that true? You will typically find what is the meaning of the 2 sentences that you said? How is that to be related, man? Okay, but anyway, I mean, you get the point. See, if you understand the language, you can actually say if these 2 sentences are expected to be next to each other or not. Okay? I mean, yeah, we can argue that may be next to each other, but the idea is at least I couldn't figure out from those 2 sentences. Until I learn the language, I can't figure out if these 2 sentences are typically expected to be next to each other or not. Okay? And that is exactly how this model was trained, right? I mean, the next sentence prediction task is basically give 2 sentences input to the BERT model, and if the model has understood English nicely, it will be able to nicely classify whether these 2 sentences will occur next to each other or not. Okay? So it will be able to do this binary classification task with a very good accuracy. Okay? Now, how do you do that? So the way you do that is basically take the model as it is, right? You pass the first sentence here, you pass the second sentence here with the CLS token and the separator token. Okay? And you do all of this BERT 12 layers of BERT processing. Okay? At the end of it, if you look at this CLS token, a representation for the same position, right? You actually connect, you take the representation, the 768 sized vector that comes here, you connect it to a dense layer. Actually, you connect it to a dense layer, and then to a single neuron. This neuron basically is there for binary prediction, next sentence or not. That binary prediction. Okay? Basically saying, when you process things through BERT, thanks to self-attention, the CLS token has understood the meaning of the entire 2 sentences. Okay? So the idea is that the CLS token is a special token. Thanks to self-attention, it basically knows the meaning of the entire input. And therefore, if you want to just classify whether this input basically had next to each other sentences or not, you can actually just put a dense layer on top of the CLS token and predict whether these two sentences are next to each other or not, in this particular classification task. Okay? Intuitively, what is the right way of doing it? Somebody was asking, you were asking, I think, what is the representation for the sentence? Now, you could basically take, let's say, these tokens, which are representative of that sentence, and maybe some average out or something like that. So that's called pooled representations. Okay? And people figured out that rather than using these representations, just using CLS is enough. Okay? So and that is why people ignore all of those representations that are coming out here, but just take the CLS token. On top of that, put a dense layer and a single neuron to figure out whether it is next sentence or not. Okay? That is why you see the NSP task is basically just labeled out there on the first token. Okay? That is why it's called CLS token or the classification token, because for classification purpose, you can just depend on the representation for that token. Okay? Now, it can generate any of those. That is true. But and you will backpropagate and penalize it for doing that as well. But remember, backpropagation is done using cross entropy loss, right? And cross entropy loss basically tells you that until it gives sufficient probability for dog, you are not penalizing, saying, hey, you're totally wrong. It's a soft loss. Yeah, it will still compare against dog because there is no manual label to say that cat is also okay here, right? So it will still compare against dog only, but it's just that, until there is good probability on dog, it's doing okay. It doesn't need to be always 100% probability out there. Okay? Yeah. Okay, so that is that. So basically, how is BERT pre-trained? Well, it's pre-trained using these two loss functions, mass language modeling and NSP, next sentence prediction. Okay? And those are two reasonable ways of teaching English to someone. Okay? Of course, pretty unreasonable when you're trying to teach to humans, but pretty good when you have lots of data and you want to train models. Okay? So BERT was pre-trained on 800 million words from Google Books corpus and also on 2.5 billion English Wikipedia words. Okay? That's right. They are trained simultaneously. In fact, the input really looks like this. CLS token, the man went to the grocery store. Grocery is masked, right? He bought a gallon of his masked milk, right? And the BERT model is asked, hey, tell me, is the label is next or not next? Binary classification token, okay? Binary classification task, right? So the two are done together. Okay? Two are done together. Okay, and I mean the other example is right there. I mean the man went to the store. Penguin babies are flightless birds. Now the two have to do nothing with each other, so therefore the label should be not next in that sense. Okay. Okay. No, each of those tokens are 768 sized in BERT base and 1024 sized in BERT large. Well, I mean, that is why you connect, a dense, so you take the 768 sized vector, you connect it to a dense layer, and then you connect it to a single neuron. So single neuron gives you one value, but the CLS token is going to give you 768 values. Those are 768 features in some ways. Okay. Okay. No, there is no, I mean, oh, good point. Good question. So NSP में वो label data है क्या? I mean, that's a good question to ask, right? It's all self-supervised. See, folks, I mean, neural networks cannot be trained without defining a loss function. And to define a loss function, you need to have some label, right? It's just that that label is automatically obtained. Yeah? So how do you obtain, automatically labeled next sentence prediction data? So what do? You basically just go to Wikipedia, take two sentences which are next to each other, and you consider them as positive label, right? Then you take one sentence from a Wikipedia page, second one from some other random website, and then you say they are not next to each other. It's as simple as that. That's how you obtain self-labeled data in that sense. Okay, good point. Yeah, and you hope that if you take random sentences, they are not really next to each other. Huh? Unsupervised? It is not unsupervised. It's basically unlabeled data. I mean, or rather, it's not data which basically requires extra manual annotation effort. Right? It's a self-supervised learning. Let's call it that way. It's not unsupervised learning. Yeah. Okay. Questions? More questions? No? Okay, good. So basically, I've understood how BERT is pre-trained. Okay. Now, how do you use BERT? So of course, BERT, a pre-trained BERT model is as good as like a second grade English guy. You know, it understands English really well. It can relate words with each other. Yeah. But if you have to use it for a certain task, for some particular task, then you download it. So you can download a BERT base or a BERT large model. Okay. And then fine tune it. So let's say if I want to use it for spam classification, then I need lots of spam labeled data. So let's say 1,000 examples of emails with spam and 1,000 marked as not spam. Okay. And I'm going to give each of those examples one by one as input here, and take the same CLS token representation, connect it with a dense layer, and then with a single neuron to classify it as spam or not spam. Okay. Just like I did for NSP, I'm going to actually do fine tuning using the same architecture, same method in that senses. So, but this time, you know, since it is based on actual labeled data for a particular task, we call it fine tuning. Okay. So we fine tune, for example, this one is being fine tuned for spam versus not spam classification. You can fine tune for sentiment versus not. You can fine tune for 10 class classification by actually having, rather than just one neuron, having like 10 neurons in the output layer here and appropriate label data for the same. Okay. Good. Okay, and you know, in 2018, 2019, at that time, BERT became very popular. Huh? Uh-huh. Uh-huh. That's right. Yeah. Because of the BERT pre-training, no? Transformer has no pre-training in it at all. Transformer is just an architecture. It's just like saying I'm giving you code. But here you're doing pre-training. And while pre-training, because you are using NSP loss, the CLS token becomes special. It has to actually learn the meaning of the entire two sentences so as to be able to say whether they are next to each other or not. Right? And then fine-tuning further improves on this, because then fine-tuning refines the representation of CLS to capture the meaning of the entire input. That's right. Exactly. CLS token gets a particular representation depending on the two input sentences, whether they are next to each other or not, so that it is predictive finally at the final output layer. Right? While doing pre-training, you know, the accuracy of pre-trained BERT is about 98% on next sentence prediction task, which basically means it has been pre-trained really nicely. It can actually do next sentence prediction with a very good quality. Okay? Yeah. In fact, we'll actually use it, you know, in hands-on demo to do next sentence prediction using BERT. Okay? So in 2019, BERT was like super popular. It is like it was at the top of leaderboards. The concept of leaderboards in NLP, in fact, started at this point. Before this, NLP was a very, very disorganized field in some ways. I mean, people would just come up with their own data sets and then say, hey, you know, my model gives the best results. But in this time period, people started building hackathons in that sense, basically saying benchmark data sets on which you can actually prove if your model is doing good or not. Okay? One of those hackathons was called as GLUE. Okay? So basically, general language understanding evaluation. Okay? So it comprised of 9 different tasks, and people basically said, hey, you know, build models and a standard test set. So standard test set, standard train sets. So build models such that you know, you basically see improved results on these 9 tasks. So these are the 9 tasks that you see here. Okay? These tasks include natural language inference, paraphrasing, you know, sentiment analysis, grammatical correctness. So this is the corpus of linguistic acceptability. So grammatical correctness and so on. So there are many such tasks. Several of those tasks, and then people would evaluate how good their model is performing. Right? So you can still go and look up GLUE dashboard, so a GLUE leaderboard, and you would actually see that BERT is probably like the 70th or the 80th model now on that leaderboard, because there are so many other models which have come up. But in 2019, it was at the top of the leaderboard, right? Because so that is why people like BERT a lot. So of course, you know, just 1 year after the GLUE was introduced, people found that there are now models which are better than humans on those tasks, which perform better than humans on those tasks. And then people came up with another leaderboard called as Super GLUE. So you know, look up these things when you get time. So Super GLUE is also 9 tasks, but they are more complicated tasks, more complex tasks. And yeah, in a year or two, again, people built models which are better than human baselines, expert human baselines on these tasks. There are many other leaderboards in today's world. And there are leaderboards with very long input documents kind of tasks. There are leaderboards for multilingual kind of tasks, and so on. So there are many, many leaderboards. But these were the two initial popular leaderboards where BERT basically was shown to be really good. Okay. Yeah. Many multilingual models also started up. So in fact, 5 years back in time, people would ask me, hey, there is a nice part of speech tagger for English. Why is there nothing for Telugu? And I would just tell them that, hey, I mean, there's no funding, so there's no work that happens on Indian languages. So that is how the world is, right? So essentially, it's mostly central on English and European languages at best, but doesn't really work for Indian languages at all. But fortunately, after these transformer models came up, these models basically demonstrate zero-shot transfer to other languages also, which basically means that, let's say if you trained a BERT, not a BERT model, but a multilingual BERT model has been trained mainly on English corpus, so therefore it doesn't generalize to other languages. But if you trained a multilingual BERT to do sentiment analysis in Chinese, you could also use it for doing sentiment analysis in Hindi, even without giving it training examples for Hindi. Okay, that's called zero-shot language transfer. Okay? Which basically means you can train on one language and it actually works nicely on other languages also. Of course, the quality is not going to be as good. If you basically train in that particular language, you would get better quality, but it's not like you would get like really pathetic quality either. You would get something reasonable. Okay? So therefore, there was work on multilingual things as well, and I'll skip more details about this slide. This was the first work, first time that people started talking about models that can handle several languages. Okay? So multilingual BERT, for example, was trained on 104 languages from Wikipedia. And therefore, most of these multilingual models now work on 100+ languages. So which includes 12 of our Indian languages, 12 popular Indian languages. Okay. Yeah, I'll skip some of these things anyway. Yeah. Okay, so we have understood BERT, we have understood GPT. Any questions so far? Questions? No? Let's basically switch to some Jupyter Notebook stuff now. Okay, so that we can look at some code also. Yeah, go ahead.
It's based on a more the social aspect. So the way humans are trying to learn certain things from time they're born to the time they grow. So I just wanted to understand that, I wanted to understand the parallel between the way we are training our models now and the way humans learn to retain information. So are we close to that benchmark, or is there a huge?
Yeah. See, I'm no good expert to answer this question nicely, okay? But I'll just tell what I think, right? So the idea is that when humans learn, of course, humans are way more efficient. So the kind of data that these models have seen, GPT model or the BERT model, is way larger than multiple humans seeing this kind of data in their entire lifetimes. Okay? So humans learn much more efficiently. That's one. Okay? Second, humans just don't learn from text. In fact, they learn more from the visual aspect than from text, right? So essentially, so basically we understand a whole bunch by seeing things, many things, rather than just looking at from text. In fact, we are all multimodal, right? We basically learn from several senses together. So, and BERT and these kinds of models are just being trained on text modality. So therefore, multimodal models are better rather than just training these ways, right? Humans also learn in a curriculum way, in the sense which is popularly called as curriculum learning. So basically seeing some simple examples first and then more complicated examples. You don't teach calculus to a first standard kid, right? So that's that. But these models, there is no order in which the data was provided. It was not like, oh, simple data first, then complex data. Just give everything, right? Humans learn in a much more controlled setup. So parents don't give all kinds of random stuff to a kid, right? Essentially, you give like consumable information for the kid. And then, later when the kid becomes older, they can consume more noisier information in that sense. Okay? So there are many differences. And yeah, I think people are working on trying to bridge those differences. Specifically, there are efforts where people are trying to learn based on very clean data. So basically saying, oh, let's basically do away with the garbage and take very clean, refined textbook kind of data Now, there's a paper called as textbooks are all you need, right? So where people just give very, very clean data so as to make these models learn closer to a human. Okay? So those are some of those answers. But again, I mean, is there effort to basically make the models learn as good as a human? I don't think so. I mean, there is lots of things to do that. There are lots of things to do. I mean, to achieve that goal. Yeah. Yeah. Okay, so let's talk about some Jupyter Notebook stuff. So there's several Jupyter Notebooks. All of them have been coded or at least curated by this person called as Divya Patel. She works with me in the at Microsoft itself. So internally, we did a similar kind of a school inside Microsoft. So I'm using her code, so crediting her as well. Okay. So this is a basic introduction to Hugging Face. All of us know Hugging Face by now, right? Hugging Face is a very great website where you can actually search for several models and data sets also, right? So several models and data sets are posted on Hugging Face. Okay. If you do not care about how these models work internally, a very simple way is to essentially just create something called as transformer pipelines from Hugging Face. And literally in like 5 lines of code, you can actually achieve whatever you want to do. I mean, several kinds of tasks that you want to do. Okay. I'm just going to do run all and then show you stuff one by one. Okay. To be able to, let's say we will try to do, let me just check if, so yeah, let me in fact just kill this because this is probably, maybe let it run, that's fine, okay? So let's start by doing a few tasks. So in this Jupyter Notebook, I'll do a few tasks. So for example, I will use it for code completion task, So basically, I'll ask it to write some code and then ask it to complete that code. I'll also ask it to do image captioning in that senses. So several of those things without knowing how those models work. Okay? So the first thing that you need to do is to install transformers and grid.io. Okay? So I'll also talk about why this library is installed. But the first thing, of course, is to ensure that transformers and grid.io are installed on your environment. Right? So that's basically just a single line of code there. Next, to be able to use any model from Hugging Face, all you need to do is to basically say from transformers import pipeline. And in that pipeline, basically give this model name. So Microsoft /5 1.5 is what I'm using. Okay? This is basically a model, small model. So Microsoft 5 1.5 is I think a 1.5 billion parameter model approximately, 1.5 to 2 billion parameter model. I actually forgot. So 1.5 doesn't mean it's a 1.5 billion parameter model. It's probably about a 2 billion parameter model. Okay? And what is going on right now, as soon as I say that, hey, create this pipeline with this model and with this task. So this is a task name. And you can actually replace this task name with like hundreds of task names that are possible using deep learning. Okay? Any task that you want to do, and there is a standard model to do that task, you can actually take that code from that Hugging Face page. So for example, Microsoft 1.5 actually has a Hugging Face page also. I'll just show you very quickly. Just search for 5 1.5. When you go to the Hugging Face page, it basically has sample code. So you can actually take the sample code, not here. There is sample code here. And essentially, you can use the sample code. So essentially, whatever is the task, you can actually figure out the task from here. Text generation is a task for which this has been trained. But as we will see in the other task, there are other kinds of tasks that you can take and corresponding models. All you need is just this 2-line code, literally. So just this 2-line code. What it does is to actually download the model. So here, essentially, it downloaded the model and other things around it, like what is the tokenizer associated with that model, and other things, vocabulary associated, and so on. Okay? So once it downloads the stuff, you can, so essentially that is what this means. So it's creating the pipeline, downloading the model for a particular purpose. Okay? So once it does this, so pipe is basically the model. You can refer to the model using this variable, right? And then give it whatever input. So the input is define print prime n. So you're basically trying to create a Python function which basically prints nth prime. So print all primes between 1 and n. In fact, print all primes between 1 and n. That is what the functionality you want. And as you see, this is basically the command that you have passed. And 5 1.5 actually has been trained for not just next word completion, but also for generating code. Okay? So therefore, whenever you do that and you set max length equal to 100, saying that, hey, after 100 tokens are generated, just stop. Okay? You see that is what it generates. So you could basically generate the output in output. And then, well, there's a standard format in which you basically get the generated text. So once the output is generated, of course, for this particular task, the way to access the generated output is output of 0 of generated text. And hey, here is the overall generated text. Here is the overall generated text. Okay. So basically saying, if you want to really use, let's say, Microsoft 1.5, 1.5 model for text generation, you literally need to write just 4 lines of code, literally 4 lines of code. That's it. Okay. And tomorrow, if you want to replace this with any other text generation model, all you need to do is to just change this string to whatever string you see. So for example, Microsoft 1.5, you don't want that. You want, let's say, llama. No problem. Well, llama to yani milega. Maybe you can actually, well, yeah, why not, right? So you want to change that? No problem. Just change that string to meta llama / meta llama 38 billion instruct. Oh, there's no prompt which is required here, or rather, the prompt. I mean, well, just to answer that, right? The prompt is exactly this. This is the prompt. This is the prompt actually, right? But it's just next word completion. So, I mean, you don't need to really say complete this code or so on. You can actually say that if you want to, generate the completion for this code and so on. But typically, since it's just next word completion, you don't really need to say anything further. Yeah, after that, the next word will be generated. So the comments end, since it is a comment, right? In Python, you write comments with 3 multi-line comment with 3 apostrophes. The answer is right here. Okay, so that's the generated output. Okay, now it may or may not be correct. I mean, that's a separate problem. But well, it is the way that you can generate output using large language models, so using any model for that matter, which is hosted on Hugging Face. That's right. It's generating Python code. Okay. However, as I mentioned, if you want to use some other model, I mean, it's really simple as that. So you can basically say, I want to use GPT-2 model. Sure. I mean, you can basically just use the same code, replace the model part rather than saying Microsoft /5 1.5. You can actually say OpenAI community /GPT-2, because that's the GPT-2 model. That's the string to represent GPT-2 model. It downloads that model, and then you can say, this is a prompt here. GPT-2 is not trained for generating code, so the typical code example won't work there. So you can just say once upon a time, and it will come up with some stuff, 100 tokens. Once upon a time, the 2 armies of the Romans were already in the midst of fighting 2 different wars and so on and so forth, right? So basically, it generates some story, some long 100-word story, okay? 100 token story. Okay? So in short, if you just want to not understand, if you don't want to care about how the model works internally, who cares? I mean, basically just have 4 lines of code literally, and it just works fine. Okay? That's that. If you wanted to do some other tasks, you can do several such tasks. You can do sentiment analysis also. So you can just say create a pipeline with sentiment analysis. If you specify the model, well and good. If you don't specify the model, Hugging Face has a default model to do things as well. Okay? So we'll just fall back to the default. And in this particular case, it defaulted to distill-BERT / this model. So it's basically a BERT-based model, specifically called distill-BERT, because it is knowledge distilled representation of the BERT model. So it's a compressed BERT model in some ways. Okay? So if you specify the model, it uses that. If you don't specify the model, Hugging Face for every task has a default model also. Okay? And then you can basically use the same classifier and say, hey, here is the input. Tell me the sentiment. We are very happy to show you the transformers library, and the output. Of course, it will generate positive and negative dono ke liye scores. And basically, it shows you the positive, I mean, the label with the higher probability. Okay? This is the model that it internally used anyway, right? The default model. But the same pipeline could be used, as I said, multiple tasks. I already showed you text generation and sentiment analysis. You can also use it for image to text. Okay? Sarcasm is not covered in sentiment analysis. Well, it depends on who trained the model on what data. So if they had labeled data with sarcasm also covered, it will be covered, else it will not be, right? Now, again, I mean, Hugging Face has a few tens of thousands of models, so I won't know if sarcasm is covered in each of those or not. Yeah. I mean, ideally, it should be covered clearly, right? So sentiment, typically, the polarity changes. Ideally, it should be covered, but it's very difficult to get a labeled sarcasm data set. So therefore, it may or may not be covered. By itself, maybe there are classifiers to detect sarcasm in that senses. So sarcasm classifier, GPT-4 data, some Some people have trained, and again, anybody can train a model and upload here. So not all models that are uploaded here are super awesome. Okay? So therefore, when you use these models, basically look at how many people have basically downloaded them, right? So for example, Llama 3 is trustable because about 2.7 million downloads have happened last month, right? But some sarcasm model may not be trustable because maybe like 2 downloads happened. Well, this is also reasonable, not too bad, but not too many downloads, right? So essentially, you can trust to a certain level only. Yeah, it may change. Correct. Right?
There is also the problem that the text corpus is big. It fails to provide correct text. The model either provides a highly positive corpus or a very highly negative corpus to be.
By corpus, you mean review?
Text,
Piece of text. Corpus typically means a bunch of documents. Small paragraph, correct. Yeah. Again, we are not talking about sentiment analysis here. My idea was to just show you how to use these models in Hugging Face, right? I agree. I mean, sentiment analysis on large pieces of text is difficult, but that's a topic for some other time. So that's that. Here, what I wanted to show you is the general applicability of this pipeline. I mean, literally just 4 lines of code allows you to do various kinds of tasks. The next task is image to text. And again, I'm not going to talk in detail about how image to text works here. Yeah. Yeah, it will just stop after 1 or 2 tokens. It just stops generating. It may or may not make sense. I agree. It can actually have an abrupt end. That's true. It may or may not make sense. Okay. Yeah, that's right. It will not ensure that it will not have an abrupt end. It can actually have an abrupt end. That's true. Okay. So if you want to ensure that, then you'll have to do some post-processing on that output to ensure where is a reasonable logical end. Yeah. Yeah. Thick. Yeah, I mean, so typically the best way is to do fine tuning. So for example, when we are trying to complete queries, right? So on on Bing chat, yeah, so essentially on Copilot, when you go and you start typing things, so, so yeah, well, so, when is, and so on. So basically it is coming up with reasonable stuff. But if it comes up with, I mean, well, type ahead completion, you don't really expect a proper end anyway. But in some cases, you do expect it to be completing in a reasonable manner. If you want to ensure that it doesn't have abrupt ends, then you have to fine tune on some task specific data. But otherwise, there is no nice way of ensuring that, hey, it should not have abrupt ends. Some post-processing heuristics help. For example, in this type ahead completion, let's say when you're typing emails, if it ended with some punctuation mark and then started some other sentence, then you would just stop wherever the first punctuation mark came in, right? So as to just finish the sentence and then let the user type the remaining thing else. Okay? So I was saying, as I was saying, you could use the same pipeline to do image captioning as well. Basically, just use image to text kind of thing, and you have a particular model which does image to text, and then you can give some image. So in this particular case, I gave Tom and Jerry image. So essentially, I can just show you the image quickly. So as the image, yeah. And I asked it to come up with a good label. So it generated Tom and Jerry as the label for it. Right? You can also, by the way, set up a demo around it using this Gradio library. So what it does is to basically take the model, the image to text model that you created, and it basically creates a web API out of it, supported by Hugging Face. Okay? So which is active for 72 hours. So what you could do is basically then share it with anyone. So for example, I could basically give that link to you. And let's say if it is using a particular model that I just created and hosted on Hugging Face, you can basically share it with people for them to try out the model. So for example, here, now I can upload any image and ask it to come up with labels. So for example, yeah, I've not tried this, but let me just try it anyway. So let me save it. Yeah, I'm actually risking it quite some. Asking it to come up with a, no, but it just happened that I don't have an image in my downloads. So, but let's see what kind of a label it will come up with, right? So it basically, so it's a nice demo. You know, I actually had to write no code to create this demo. Well, hopefully it doesn't come up with something very nasty. A man with a green shirt smiles at the camera. Not bad. Okay, it's reasonable. I did smile and I'm a green shirt. Good. Okay, so pretty good, right? That's that. So essentially, just with 10 less than 10 lines of code, you could actually, use Hugging Face to create really awesome demos. Okay, really awesome demos. Okay. Now let's go a little deeper and try to understand what's going on while Hugging Face is allowing you to use such a huge amount of power in a few lines of code, right? What's going on? And of course, knowing what's going on is important if you want to customize stuff, right? If you want to basically customize stuff. And since I'm using all free compute, let me just kill my current thing and just run this guy. Okay. So let's see what is going on. So when we said from transformers import pipeline, and then we created a sentiment analysis pipeline, and then we did a classifier, what was going on behind the scene was first, it was loading the pre-trained model, right? It was actually downloading it. So it is downloading the distill BERT pre-trained model here, and also downloading the tokenizer. So essentially downloading the tokenizer, which should be used to give input. To convert this input, we are very happy to show you the transformers library as something that DistilBERT understands. Okay, so the first step, of course, is to load these modules and then download. So no model was supplied. Understand the default is this one. It downloads the configuration for the model. It downloads a safe tensor. Safe tensor is the model itself. As you see, it's like a 268 MB model. Okay. And then what it is trying to do, and it downloaded the tokenizer also, the vocabulary for the tokenizer, and finally it basically came up with the label. So the tasks that are being done: one, load the pre-trained model, download, and then load it in RAM. Right. Second, tokenize the input. Third, do model inference, and then do some post-processing that is required to return the result. Now, the post-processing could basically be like provide the output of the most popular class, give the probability. So basically, whatever is the output, you come up with the right, depending on the type of the task. So for sentiment analysis, just binary sentiment analysis, but image to text, it's basically the generated text and so on that needs to be output. So format it appropriately and give it out as output. Okay. So let's understand this one by one now. So how it is going on, right? So if one were to sort of figure out what was written in that pipeline, right? What is the code? So this is the code. So the first step is basically to load the pre-trained model. So if one were to basically write this by themselves, this is how you would write it. So from transformers import auto model for sequence classification, because after all, you're classifying a text sequence as positive or negative. Okay? And you're using a pre-trained model called as you're using a pre-trained model called as distill BERT. So sure. Yeah, so basically, therefore, give this thing distill BERT / distill BERT uncased, a base uncased fine-tuned SST2 English. It's basically just say that it has been fine-tuned on a data set called as SST2. Stanford Sentiment Tree Bank, I think. That's the data set on which it has been fine-tuned for sentiment analysis. Okay. So once you load this model, you can actually print the architecture of this model. So this is the architecture of this model. It's basically just a BERT model, so which has embeddings layer, and then it has transformer layers, specifically transformer encoder layers, 6 of those layers. So actually, in fact, a 6-layer BERT model in that sense. Okay. And in each of those, what do you expect to have? Well, you expect to have QKVs and then a linear transformation. And then you have the feed-forward linear layers with some activations, some dropouts, and so on. Okay? So you can print the architecture also. And then lastly, there's a classifier, which takes your 768 sized embedding to a hidden layer of 768 size, and finally connects it to a 2-layer final output, which two neuron final output, which predicts positive or negative. Okay? So if you wanted to understand what's going on, this is what you could do. You can actually load the model yourself. Then the next step to do is to really load the tokenizer. So you have the model and you've loaded it, but the next step is to load the tokenizer. So that one is called auto tokenizer. And auto tokenizer, from a pre-trained model, it automatically figures out whether what kind of tokenizer works for this model. So Hugging Face in this particular class, auto tokenizer class, there is a dictionary which stores for each model what is the tokenizer to be used. So it basically gets that tokenizer. And then you can actually, for the tokenizer, you can actually pass the text input and ask it to tokenize. So, and then when you try to print these tokenized outputs, basically this is how they look like. So this is how they look like. There are two parts to it: input IDs and attention mask. Input IDs basically tell you that in the tokenizer vocabulary. Now remember, distilled BERT is basically based on BERT, which basically means it uses the word piece embedding, word piece tokenizer with 30,000 vocabulary size. Okay, so around 30,000. I think it's like about 32,000 or something, but that's what it is, right? So it's basically telling you that, hey, V is 101, token number 100. Oh, well, V is basically, yeah, token 101. Rather, 101 is not V. Actually, I think V is 2057 because 101 is the CLS token, the special first token that is provided. Okay? So that's that. And then once you have the tokenized inputs, you can actually pass it to the model to generate the outputs. Okay? Pass it to the model to generate the outputs. What is the attention mask? Oh, sorry, good point. Yeah. So what does this tell? Well, this tells basically that, hey, this entire input which is present is supposed to be considered for computing self-attention. Okay? So we will see applications later, and it will become clearer why that is required. Of course, अब जब input इतना बड़ा है, तो of course all of them should be considered. So this should always be one big deal. Why is it there, right? For that matter. So you'll understand why is it there in the next example, where I will actually show you some of those getting zeros as well. Now, of course, it is needed because I can always say service was bad or service was not bad, right? I mean, like, see, everything is needed. I mean, at some point or the other for some application or the other. So if the application is whether the sentence is written in passive voice or active voice, clearly those things are needed, right? So there could be several applications. If the application is translation, now, I mean, of course, you need every word, right? So that's that. Okay. So in NLP, typically you never throw away stop words unless you are doing search where stop words don't matter. I mean, well, even there stop words matter because there is a movie called The, and there's a phrase called to be or not to be. So, you know, so stop words always matter. It's just that you have to treat them specially for some applications. Okay? Yeah. Well, so, you know, once you have those tokenized inputs, you can give to the model, which you created right up there, and then get the outputs. And once you get the outputs, you can actually print the outputs. And the outputs here are these logits, you know. Now, therefore, the post-processing step is needed. So as to basically convert them, apply softmax, convert them, and figure out what is the probability for the negative label, what is the probability for the positive label, and then finally print that, well, I mean, the positive label with a probability score of that. Okay? Where? Sorry. Oh, yeah. Well, I mean, the classifier output could have several things out there, and you may want to care or not care about those. So here we only care about the logits and ignore everything else, right? For our purpose, only the logits matter, and therefore we've just taken those. Okay. Okay. So that is what goes on inside that call. So when you do this simple call, I mean, or rather these two lines, that is what goes on. Internally, the model is downloaded, tokenizer is downloaded, you apply the tokenizer to the input, get the IDs, give it to the model, get the outputs from the model, post-process them so as to figure out the logit scores, softmax them, figure out the max probability, put out the label. Okay? Everything happens as we saw, you know, part by part in this code piece. Okay. Okay, so so that was about you know, that step. Now let's talk about the next one. So what is going on when you're doing tokenization? So let's go into a little bit more details about what is going on in the tokenization. So, you know, we talked about word embeddings and so on. So let's see, you know, what those tokens are. Again, let me just quickly manage the sessions nicely. Terminate, yeah. And just run this. So, what is being done here? So, I mean, we've already done these things before. So, I'm basically just downloading the distilled BERT model, loading it in model, and then also using the pre-train, also getting the tokenizer corresponding to this model. Okay. So that's that. And I will basically take the input and tokenize, and then we'll try to understand what those IDs particularly mean, right? So we liked the embedders, we were okay with encoder decoders, but we love the transformers. This is basically just the input. And what we are trying to see is the IDs that get generated. Okay? So you see, these are the IDs that are getting generated. So essentially, we are basically just passing this input. And basically, we see that there are these IDs which are getting generated as a tensor. And of course, again, there is a mask thing, which is always 1 in this case as well. Okay? So what happens when you're doing tokenization? We already talked about what happens. So there are these subwords and so on, which are being used and so on. But we can also see how the model actually tokenizes this. So you can actually figure out that this embedders, there is no word called embedders in its vocabulary. And therefore, it splits it into parts, EM, BED, and DERS. Okay. So those are the three parts that it splits into. So you can actually visualize that, hey, what is happening in the background when it is trying to tokenize. And for each of them, you can actually print the IDs. So you can actually say that, hey, here is a text converted to IDs. So these are the IDs which are associated with the particular tokens that you see there. Okay? And then you can actually also say that, hey, but I also heard that, hey, BERT model also does the CLS tokens, SEP token, and there's also something called a padding token, which I will talk about soon. Okay? So which also are special tokens in the vocabulary. So what are their IDs? So special, CLS token has 101, 102 SEP token, pad has 0 as the ID. Okay, so that's the IDs. Okay. Once I'm done with that, this is how the input is actually processed and prepared to be given to the model. So when you say, hey, here is the tokenized output which can be given to the model, the way this is done is that you actually get the CLS token, so CLS token ka ID, you get the tokenized input IDs, and then you get the SEP token ka ID, and this is the input. In the previous Jupyter notebook, when I essentially, when I got the inputs tokenized using the tokenizer, this is what it was doing. It was actually prepending CLS and appending the SEP token automatically, okay? Which we actually did manually here. So if you really wanted to manually do this, you can actually do it like this. Okay. Okay. So that's that. And you can actually check that, yes, whenever you do it manually, like as inputs of input IDs and this tokenized input ID, so this is manually created, and this is the actual one that tokenizer gives you. You can actually check that this is exactly the same. So the same IDs appear as well. Okay. You can of course also use the dot decode to decode the any tokenized input. So you can give those IDs, tokenized input ID, and ask it to actually get back the text. So it actually can get back the text. Even those words which are broken can be combined nicely because it knows, which word was a continuation of which word, thanks to these special hash markers. That's essentially the special markers out there. Okay. And then, of course, you can look at the attention mask, but this is all once, so it is not really fancy. Okay. But why is this attention mask required? And let's try to understand why this is required, right? So when you do processing, let's say when you're doing fine tuning, you're typically fine tuning using a batch of instances. A batch typically means more than one, right? So typically, let's say in this particular case, the batch has two things. This summer is killing me, and then there is another one, me too. Okay. So when you're doing this batch of instances, not all of the examples in the batch are of the same size. But when you have to pass through the transformer, you have to pass the entire batch in one go. Okay. So, and therefore, what you need to do is the second one, which is smaller, you have to pad with zeros so as to make it of the same size. But then you have to tell the model, don't do self-attention on those padded guys, right? And that is why you have the mask IDs. So essentially saying, when you give this to the tokenizer, it's basically going to give you the outputs, of course, the word IDs for each of them. But in the attention mask, there'll be ones for the first guy. Actually, slightly more ones because there's a CLS token also and so on, right? SEP token at the end. But then for the other guy, which is shorter, there'll be lots of zeros, basically saying that, hey, my input was done in a very short space, but then the remaining things I'm just padding for the sake of padding so that the inputs become of the same size for the batch. Okay. Okay. So that's that. You can, of course, always look at the tokenized inputs like that. Okay. Now, we already know how did it decide to split some words and not others because it is subword embeddings and so on. But what we could also do is try and check if the model actually has a particular word in its vocabulary or not. So this is the way to check if embedders was there in the vocabulary. Okay. So get the vocabulary from the tokenizer. And after you get the vocabulary, it's basically just a dictionary of the token and its ID. Okay. So if there is no embedders, it just prints none. But there is transformers, so therefore it prints its frequent. In some ways it's ID. So 19,081 is the ID for the word transformers in its vocabulary. Okay. You can also, of course, get the size of the vocabulary. That's like 30,522, right? And you can actually print the entire vocabulary. So this is the entire vocabulary. So you can actually print it, and you can look at the entire vocabulary by printing each of those things one by one. Okay. So if you want to build your customized application, your customized tokenizer, you can add things to the vocabulary manually. So you can say, I'm not happy with the actual vocabulary. Maybe I can add some manual stuff as well. So this is useful when you have particular IDs. So let's say you have a particular kind of a ID which you want to also include in the vocabulary. In that case, you can basically just say, let's say, embedders is that ID. You can just say add tokens, and it basically gets added as the last token. Okay, so last token. So therefore, the vocabulary size becomes 30,523 rather than just being 30,522 earlier. Okay. And then once you have added this one, now you try to tokenize, you will see that the embedders is not going to be tokenized into those small parts. Well, it is basically going to be kept as it is because there's a single word which represents the entire token itself. Okay. So that's a little bit of drill down into tokenization. So how you can actually mess around with tokenization also. Okay. But if you don't want to do all of that, using tokenization is super simple. Essentially, just give it the right model name. It will figure out the tokenizer and then give it the input. It will give you the tokenized inputs. Okay. Any questions so far? Questions? No questions, huh?
Not very clear, or it's not very transparent on how the semantic meaning of the particular word is being taken and is being represented as if that is the case with English, then when we do it with index word kind of models, or if there are any low resource languages for that sake, then it's going to be very tough for us to create our own tokenize or our own auto tokenizer or text embedding scheme for a low resource language. If we don't know what is happening inside it, or how the textual or the semantic meaning is captured.
So, how the semantic meaning is captured, I think like Word2Vec tells you how it is captured, right? By looking at other words in the context.
These other words, say for example, sun is the largest star or something like that. So, sun is mapped to a star, or it's mapped to the largest words like that based on the self-attention that is there. Right? But when we talk about text embedding, let's talk about a lot of astronomical bodies, Uranus, Neptune, Pluto. They, in a vector representation, they are going to be in one space, and say hibiscus rose or lily, those kind of flowers are going to be in a different vector space. That's how the semantic meaning is actually being captured. But how that thing happened is still a question.
Yeah. So, but there's no answer to it because these models are not interpretable.
It's very difficult for our own language. Like if someone wants to do it in Telugu or someone wants to do
but why would it be very difficult? Why would the difficulty be there across languages? If it is difficult in English, sure, the difficulty is similar in Telugu. What is the special thing?
The training data
that's true. Agreed.
The text is able to identify the semantics of a particular word just by the immense data that is being given.
That's right. That's right.
Training data.
And
the text is going to be something much more random.
That's true. I agree. Yeah.
The semantic meaning is not being captured.
Fair enough. Fair enough. I agree. That is why Indian language models may not be very good. So, maybe that is why a model trained on Assamese may be really poor compared to a model trained on Telugu. But big deal. What next? What is your question? Yeah.
Training data or the growth small data set that they have in such a way that it performs better than what.
Absolutely. Yeah, that's a good point. So basically what you're trying to say is that can we interpret what each of those dimensions is capturing, right? So that's a question. Yeah, it's a 300 dimensional thing, but is the first feature in that 300 dimensions capturing, let's say, the length of the word? Second one, is it capturing, is it a noun or not, right? Third one, is it capturing, whether it is a plural or a singular, and so on, right? If we can somehow understand that, then maybe we can train better ones, right? With smaller amounts of data. I agree. So, and several people agree. Nobody will disagree with this clearly, right? And there is therefore some work on trying to interpret the what is being captured in those embeddings. Okay? And your thought is not just that. What you're saying is that if I understand that, then maybe I can use it to define a better way of doing embeddings. You know? So I've seen the first part happening. So what people have tried to do is to understand what kind of basic linguistic properties of words are being captured by those embeddings. But I have not seen anybody saying, hey, since I've understood that, and therefore, here is a better way of doing embeddings. Unfortunately, that I have not seen anybody do. But if you're really, really curious about it, sure, work on it. I mean, I've not seen people do that though. So, but there are people who have basically tried to figure out, okay, I mean, these are BERT embeddings. There's an interesting paper by one of my students. I mean, this was done after he graduated from, my thing. So interpretability, interpreting BERT embeddings. Let's search. I don't know if I'll find that paper. Ganesh Jawahar. Let's see. Yeah, this one. What does BERT learn about the structure of language? In fact, this is the exact question which you're asking. Hey, in these embeddings, it will come up. It will take some time. Yeah, I think it's coming up. Yeah, that, what is the exact thing that this thing is learning? How is it capturing meaning, right? And what he tried to do is to basically try to understand if these embeddings are actually capturing the notion of sentence length, or are they capturing word count? Are they capturing tree depth? If there is a sentence, I mean, basically he worked at the sentence level because BERT basically gives you representations for sentences, right? So tree depth in the sense, you can represent the sentence as trees as well. And then is it capturing that property of sentence? What is it capturing exactly, right? And that's just an analysis. And I've seen several such analysis papers which try to understand what is it that they are capturing. But nobody has basically, at least no paper that I know of, has said, oh, I've come up with a better embedding method because I've understood this. Okay? Of course, the goal probably is that, but at least nobody has been able to do that for sure. Okay? Okay? Good. So, but if you are interested, sure, take it up. And, you may find it interesting enough to do a PhD or something in that area. Okay? Or you might already be doing, but anyway, what are you doing? Are you doing a PhD? Huh? Latent text. Legal text summarization. That's what you're working on? Okay, nice. Okay. Good. Okay, so let's basically look at the BERT model, especially the mass language modeling. So, hey, can I use the BERT model to actually do mass language modeling? Okay. The way to do that, this is what is being shown in this Jupyter notebook. So let me essentially, let me just run this and show stuff. So what we are trying to do here is to download the BERT model, which has been pre-trained, right? Pre-trained BERT model, so as to basically use it for mass language modeling. Okay. So import torch, and we have done import of several stuff. From transformers, we basically import BERT tokenizer because you have to tokenize input text, and also BERT for mass language modeling. Okay. We basically use BERT-based uncased model. So load the corresponding tokenizer, load the corresponding model. And then basically just give it this text. I really masked the movie. It was quite interesting. Yeah. So we are basically giving it masked text and tokenizing it to get inputs. The mask token actually has there's a special token for it. So the special token is 103. So remember the 101 is for I think CLS, 102 was for SEP token, 103 is mask token. And therefore, when you try to tokenize this, you essentially get the CLS token in the beginning. This is I, this is probably really, and then this is mask, and so on. So until you end up with a SEP token at the end. Okay. So that's basically that. You, of course, take those inputs, pass it to the model, get the outputs. If you look at the output, it basically shows you a 1x13 output. So effectively, it is showing you that it actually came up with several replacements for this word mask. Okay? It came up with several replacements for this word mask. Well, at the output, of course, it came up with, since there were like 13 tokens overall, it basically came up with outputs for each of those 13 positions. all of them like vocabulary size in that senses, but hey, we are interested in a particular position, specifically the third position, which is the mask token. And we want to figure out what is the maximum probability logits, what is the maximum probability, what is the maximum probability tokens that it wants to assign at that particular position. So you can actually just print the top one. So you can basically say that I just want the maximum probability one that basically is enjoyed. So the mask language model sort of fills this. I really enjoyed the movie. It was quite interesting. But if you want to print, you can, of course, print the entire ranked list. I mean, here, just the top 5 are taken. So top 5 are enjoyed, liked, loved, enjoy, like. Okay? Now, the last 2 may not be exactly accurate because I really enjoy the movie is probably not that accurate. I really enjoyed the movie is more accurate, but they are not really too bad as well. Okay? So if you basically have text of this kind and want to do mask language modeling, or other, we talked about mask language modeling, this is how you can actually do it by downloading the mask language trained model, okay, but for mask language. Okay. Similarly, we talked about NSP, next sentence prediction. So another Jupyter notebook just shows to you how you can actually do NSP using the BERT model itself. So here, again, I'm importing BERT, but now I'm importing BERT for next sentence prediction. Okay. And then loading the model and tokenizer is just the same, no change there. But to get the prediction, I need 2 sentences this time, so as to predict whether they are next to each other or not. So I take the 2 pieces of text and I give the tokenizer these 2 pieces of text. The tokenizer is smart. If you just give one text, then it basically just appends CLS and prepends CLS and appends SEP token. But when you give it 2 pieces of text, it sort of understands that these are the 2 text pieces, and it has to actually put CLS, text 1, SEP token, text 2, and then SEP token again. That is what it is doing there. Okay. Essentially, after you have done that, of course, you can actually print the inputs like that. And then once the inputs are ready, you can actually get the prediction by passing those inputs to the model, get the outputs. You can actually print the logits, but what you are interested in is whether it is next sentence or not. So you can print the second sentence a continuation or not, depending on the logit values. Okay. So in this particular case, it basically says the model predicted that the second sentence is a continuation of the first one. And then you can, of course, try with another example as well. That was a great movie. It rained in the morning. Have to do nothing with each other. So fortunately, the model in this case nicely says that the second sentence is not a continuation of the first one. Okay. So essentially saying, yeah, I mean, what we learned, you can, of course, get it done in using Hugging Face and Jupyter Notebook easily. Okay. Now, let's say if you have labeled data and you want to fine-tune a pre-trained BERT model on your own data, this Jupyter Notebook is about showing how you can do fine-tuning using your own labeled data. What's going on here? Huh? Oh, attendance is going on. Acha. Oh, some special way of attendance, not sure. But anyway, everything will be shared. Yeah, everything will be shared. Yeah. Okay. So how do you do fine tuning? Let's say if you have fine tuning for sentiment classification, right? So you install, so there's a library called as datasets library. You install it. It basically comes with several datasets, several public datasets in that senses. And then I'm importing several things: torch, transformers, datasets, may say load dataset functionality. I'm also importing TQDM. TQDM, what is TQDM? People must have used here, right? TQDM? Huh? No. Huh? Not for data augmentation. It's basically just the progress bar. Exactly. It's a much more fancy for loop, right? So as to get a good progress bar, right? And then also to compute the matrix, you'll just import here things from scikit-learn are imported. Right? I'm also printing what am I using? I mean the CUDA device or the CPU. Not printing, but deciding the right device. I'm loading the data. This is a standard data set, so I'm not really downloading it from somewhere and so on. It basically gets shipped as part of the datasets library. So for that matter, it's basically the functionality is there in the datasets library. It's downloading from Hugging Face anyway. So when you say Stanford NLP/SST, just like you can download models from Hugging Face, you can also download data sets from Hugging Face, right? So it's downloading the data. And once you have the data, you can, we can print the, oh, so this is not executed. Let me just execute it so that you can see the outputs also. Yeah. So you can print a particular sample and then check out what this data set is all about. But as it says, it's basically sentiment analysis data. So SST is a sentiment analysis data, and we are just training it for sentiment, fine-tuning the BERT model for sentiment analysis. Of course, you can use the same pre-trained model for sentiment analysis, but its accuracy is going to be pathetic. And then we'll actually fine-tune it, and we'll see how the fine-tuned model will give much better results compared to the pre-trained one. The Jupyter Notebook actually does all of that, but depending on the time that we have, we may or may not wait for it to fine-tune completely. Okay? So I'm assuming everyone knows on Colab you can actually get like a free T4 GPU, which used to be, which is not very cheap. So fortunately, this is actually compute power which is made available for free. If you have a Colab Pro account, then you can actually get better things, right? Better things as well. And Colab Pro account is also very cheap, about some 3,000, 4,000 rupees per month or something like that. Yeah, something in that ballpark. Okay. So yeah, so this is a sentiment analysis task. So this is the review, contains no wit, only labored gags. So that's a negative sentiment, and therefore it is marked with a negative sentiment nicely. Sorry. This is a labeled data. Okay. Tokenizer, of course, since you are going to be fine-tuning BERT, you need a BERT tokenizer. Okay. And then this one is basically just tokenizing. So it's taking the entire data set and using the map functionality in Python so as to run tokenize function on each of those examples in the data set. So the data set is basically our sentiment analysis data set. It's tokenizing each of them. Okay. Because to be able to fine-tune BERT, you need to give it tokenized input, right? So therefore, it's sort of tokenizing using a standard tokenizer. Standard tokenizer in the sense the BERT tokenizer. Okay. So there are some 67,000 examples, and it takes some time. So tokenizers don't take a lot of time to run. It will be done, as it says, about 1.5 minutes to tokenize. Okay. Once the text is tokenized, of course, we can also look at each of those individual input IDs and then try to make some sense. So it's a tensor, of course, and we can also look at input IDs, but we have looked at it anyway several times. Okay? So the next step is to load the model. So our data is ready, it's tokenized, but we have to use it for fine-tuning, right? So therefore, I'm loading the model to begin with, and it's a pre-trained model. I'm just loading BERT-based uncased pre-trained model. Okay? I've said number of labels equal to 2, and when I say number of labels equal to 2, it actually loads the pre-trained BERT model, and it also puts a hidden layer at the top on top of CLS with 2 output neurons, saying that, hey, I'm going to fine-tune it or use it for binary classification. Okay? So that's that. Now, since I have to do fine-tuning, I must define data loaders. So, when you have data that you want to use for backpropagation, you need to do batching. And for that, PyTorch basically has these data loader concepts. So you take the training part of the data and the validation part of the data, train data loaders, create data loaders with batch size 32. And you're also doing shuffling on the training part so as to make sure the data is sufficiently shuffled and randomly shuffled in that sense, right? Now, even before we fine tune, this is the evaluation loop, or rather the evaluation code, so as to just figure out how good the pre-training model is. The pre-trained model is, on this task, the sentiment analysis task. Okay? So you take the test part, the eval part, and eval data loader. That's basically the evaluation part. And you actually, of course, take the batch of those input IDs and the attention mask. Depending on that, you take all of these things to the device. Now, remember, whenever you have to do backpropagation or inferencing or anything, you must take everything to the device, to the GPU, because otherwise it will just do everything on CPU. Okay? So you take the device and then you compute the outputs from the model. So you give those input IDs along with the attention mask. Again, attention mask is important because in a batch, there could be certain examples which are shorter in size, and therefore you don't want to use that to compute the inference labels. Right? So you give that as input and you get the output from the model. You get the predictions. You get two probabilities because you mentioned there are two classes. And you take the max guy or rather the argmax for the guy, and you essentially add that to a list called all labels so that you can print the predictions. Of course, you can get the predictions for all the test examples, and you can compare with the actual predictions so as to get the accuracy. And you get the accuracy. Accuracy is poor, 48%, right? Basically saying it's random accuracy because, well, you did not really fine tune, especially the last layer, right? The last layer is really randomly initialized, and that is what you get. Okay? So that's that. So therefore, you must fine tune, and to fine tune, you first need to define the optimizer. So Adam W optimizer with some learning rate. And this is the fine tuning process. So you set the model in the train mode for 3 epochs for range 3. So 3 epochs, I'm basically running batch by batch train loader. This is the standard fine tuning. Everyone here has done PyTorch, assuming, right? So essentially, yeah, this is basically zeroing out the gradient, and this is essentially getting the batch of input IDs, attention mask, labels, passing them, taking them to the device, and then actually computing the prediction, computing the loss, backpropagating the loss, updating the weights. Right? So once all the epochs are done, you can of course evaluate the model, and once this gets done, we'll basically see that the accuracy is way better than 48%. Okay? So this is how you can fine tune the BERT model. All you need to do is to basically tell the BERT model, hey, yes, download the pre-trained version, but with number of classes equal to 2, and then the fine tuning is basically the standard fine tuning code for any PyTorch model in that sense. Okay? Questions? Any questions so far? So what have we looked at? We have basically looked at how you can use Hugging Face to code up demos in like 10 lines of code, whatever be the task, whether it is sentiment analysis or summarization or image to text or whatever be the task, right? And then we have basically looked at the individual pieces. So we have looked at what happens when you run a transformer pipeline. So essentially loading the model, loading the tokenizer, how does the tokenizer work? And finally, how do you actually do fine tuning of a pre-trained BERT model? Okay? So hopefully this will not take too long, as it says 23 more seconds for the fine tuning to happen. And after that, it will take some time to evaluate, and we can just compare the accuracy quickly. Okay, any questions so far? Any questions? How many of you have done this before? Fine-tuned some BERT model? Few of you? Okay. Rather, probably half of you. Yeah. Okay. So the training is done. Evaluation is going on, and the evaluation data is not too large, so it should rather finish soon. Yeah, 10 more seconds. And then we will see that this model will provide hopefully around, yeah, it provides about 87% accuracy on the task. Right? The random model gave like some 48%. Okay. Any questions? If not, let's. I think this one was T5, so maybe we'll do it later. Yeah, so we can look at T5 later. But any questions so far? Any questions? No. Sorry, sentiment analysis is? Padding at the end is done automatically. Correct. So when the padding is being done, the attention mask is being set appropriately so that it does not really incorporate, it does not include those tokens for coming up with the predictions. Right? Okay. Uh-huh. Go ahead. Uh-huh.
Some model understands some question,
Mm.
some, and there are guidelines how to write a. Why not ask the model itself because you understand it better, you generate prompts?
No, absolutely, you can do that. Nobody stops you from doing that anyway. You can actually ask model, hey, tell me a prompt to do this. Why not? In fact, there is an entire line of work called as prompt optimization. That basically means that, and we use those prompt optimizers inside Microsoft also. So there are some prompts which are very complicated. For example, the prompt to decide whether something is offensive or not is actually, it has like 100 different policy clauses. Somebody in Microsoft, some ethics people actually designed those guidelines in English. Okay? And then we basically have to convert them to prompts. Now, we basically give them to models, but then models are smart. You can actually design the same things in much shorter text. And shorter text is important because the longer the prompt, the more the latency, and the more the compute power required. And remember, when you have to basically support hundreds of millions of users, every microsecond matters for us. So therefore, shorter prompts are super important, even if they are, and of course, accuracy is important. And to do that, can we do it automatically? Yes, there are systems which help you do that. They are called as prompt optimization methods. For example, there is something called as Protegi. Just search for those, right? There are things like popular algorithms like Protegi, OPRO, popular methods which have been, which are popular, which are very useful, AP for automatic prompt optimization. Okay? Yeah, so nobody stops you from doing this. Yeah. Go ahead. Sorry. So these are, they basically take the model also as a parameter. And what model are you trying to optimize it for? That's true. And at Microsoft, believe me, we face this problem so much. OpenAI keeps coming up with new models, and as product teams, we have to basically latch on to those new models. What does that mean? We have to basically redesign the prompts. Now, that's just too much work for our developers. So essentially, therefore, prompt optimization is a super important thing for us internally. Automatically rewriting prompts to accommodate for the new model that the OpenAI guy just dropped to us, right? So, yeah. Uh-huh. Oh, there are several other mechanisms. That's right. That's right. So are there other ways of doing pre-training, right? There are many such mechanisms. Some of them I'll talk about for in the BART and T5 part. Okay? But there are more mechanisms also which I will not talk about as part of those things, but they're called as pre-training objectives. Just search for popular pre-training objectives, or like ask Bing Copilot, what are popular pre-training objectives. It will basically tell you several other objectives beyond the ones that we'll discuss today. Okay? And then the ones that I'm talking about are just based on text. But imagine now if you want to pre-train a model which understands text and images together. So essentially, our pre-trained English model basically understands the meaning of English words and relationship between pairs of words. But now in a multimodal setup, I want this model to understand that this part of the image basically means this in text. So there needs to be pre-training for that as well. And the kind of loss functions or the kind of tasks pre-training tasks that you will define there are going to be different. So there are therefore these multimodal pre-training objectives also. Yeah, such kind of models exist, right? So for example, visual BERT is basically a model which basically takes image and text together. Speech BERT is a model which basically takes audio and text together, and they come up with pre-trained variants of BERT itself. Okay? Multimodal pre-trained variants. Okay.
Data set library.
Hmm.
When we fine tune like it now, we have much less control than we just spike.
Yeah.
Instead of one layer, I would multiple layers.
Hmm.
But this keeps very fast.
Absolutely. Yeah. Yeah.
Graphs, early stopping, maybe at this time it is the modest point better.
Absolutely. Absolutely. See, multiple answers to that, right? One, so my kid is 7.5 years old, right? I don't give her calculator to do maths, right? Basically, of course, nobody learned maths here using a calculator, else you won't be here anyway, right? We all learned our own ways, right? Yeah, ye use karna rather than a calculator, right? So, so sure. I mean, when you're learning, it's always good to learn from the base, right? But the point is that what is the learning for is the question. So if you're basically learning for the sake of academic elegance, sure, you want to understand everything. And even there, right, there are depth-first learners versus breadth-first learners. Okay? So, for example, if I basically want to do a PhD in legal summarization, I don't think I care about how Adam W works, man. Who cares? And let me just use it as a library, right? Because I'm not doing a PhD in how to build better optimizers. I'm just doing a PhD in how summarization is done. Makes sense? So basically, it really just depends on what particular thing you want to learn about. If you really want to learn about, nobody stops you from looking at the source code. Just go look at the source code, modify there. Yeah. But if you basically want to do things quicker, essentially, for example, I don't code now. I mean, all of this code, as I said, was written by a colleague, right? So for me, I mean, if you basically give me like hundreds of lines of code, I'm not going to even look at that. I mean, I'll just have someone look at that and abstract it out to me, really, right? So it depends on what stage of learning you are in and what you want to learn about. There are always ways to basically just go deeper and figure out the right things. Okay? The other part that is important is optimization. So these libraries are good. So certain basically libraries are really nice for faster coding, but then they are not good for deployments because they are not really the most optimized code possible. But then there are fortunately other libraries which take the code, which take the models that build using these libraries and convert them to really optimized versions, which you could deploy. For example, there are things like deep speed. There are things like Onyx. There are things like faster transformers, which basically take your models and then convert them to their C++ variants so that you can actually optimize for serving time latencies. Okay? So serve them to basically deploy them for large scale deployments. Okay. So that's that. Any other questions? Yeah. Hmm. Uh, yeah, that's a good question. Well, I don't know how would you train such a model first to begin with, right? Because to be able to understand internet slang, it should be trained on internet data. I mean, in that sense, and unfortunately, these days Twitter is out. The big guy basically just made it, pay for use kind of stuff. But anyway, I mean, first, so I don't know how do you even train a basic model? Keeping up with the latest trends is even more complicated. Yeah, I mean, what is the use case? So is the use case to write SMS messages in a particular way? Huh. Agreed. I mean, then I would probably just depend on OpenAI to do this. And essentially what I could do is have some prompts and regularly, maybe every 6 months, just put those prompts to the OpenAI's latest GPT API. And we are assuming that OpenAI is continuously training their models anyway. So just use the GPT API and just keep getting the outputs from that. And based on those outputs, train my local model. Okay? Agents. And what should each agent do? You can use agents, but each of those models is just an agent, basically. I mean, not. I mean, see. I mean, what you meant is just some regular call to a model, and agents are not meant to do that. I mean, agents are. Yeah. I mean, so agents are just another names for large language models. But anyway, I mean, therefore, let's not unnecessarily bring the agent framework here. All you need to do is to just call, let's say, some larger model because it learns on very large amounts of text data, world text data. Yeah, I'm sure there are some studies on evolution of language and so on, but not that I know of. Yeah. I don't know. Some people might be doing here studies on evolution of language. There are people who do that, but not that I know of. Probably that is not even NLP. I mean, there are people in linguistics or some such folks who actually do that. Yeah. But again, I mean, I don't know why. I mean, well, that could be interesting for sure. But again, I mean, no business use cases that I see around that. I mean, that's interesting just for historians' perspective and so on. But no business use cases that I can think about. Was there a question? Okay. So let's take a break. I think it's 3:30, right? So it's good time to take a break, and then we can talk about BART and T5 after that. But go ahead.
We type some prompt.
No, it doesn't get confused exactly because it has seen a whole bunch of those spelling mistakes on the web anyway. So it understands those spelling mistakes also as logical text. That's it. Yeah. Right? So essentially, it's just a part of it. In fact, yeah, I mean, because the spelling mistakes that you make are typically frequent spelling mistakes anyway. So it has learned from them as well. Right? Okay. Cool. Okay, let's take a quick break and come back in say 5 minutes, 5-10 minutes. Let's continue. Let's resume, folks. So let's talk about BART and T5, and then I also had something to talk about NLP applications. But again, I think we have talked about lots of applications on the way anyway. But whatever is the time, depending on the time, we will do that or skip that. Okay. So let's talk about BART and T5. And as I said, if you remember, right, if you recall, transformer, if you basically take the encoder part and the decoder part, a pre-trained encoder is basically an example is BERT, and there are many other such models. Okay. Uh, Now, those models, how do they differ from the standard BERT? Well, either they are pre-trained on much larger data, or they have been trained with a lesser number of parameters, more layers, less layers. They have been pre-trained using other objective functions compared to MLM and NSP. There are several other objective functions, right? Or they have been, or they use different tokenizers, multilingual in that senses. So that is how those encoders differ. Yeah. On the decoder side, we talked about GPT, and there are other kinds of decoder models as well, like Llama, which you will cover in the next few days in the course. Okay? And then there are Llama-like models. Of course, there is Llama 1, Llama 2, Llama 3 itself. But then there are other models which have become popular, like Falcon or like the Phi series from Microsoft, Orca series, and so on and so forth. Right? But then if you basically pre-train the entire encoder decoder guy, T5 and BART are examples of those. Okay, so that is why we'll talk about T5 and BART now. Okay, so how is BART pre-trained? What is BART, right? BART basically is a combination of the way BERT pre-training is done and the GPT pre-training has been done. Okay? So BERT is a bidirectional encoder. It tries to do two things, MLM and NSP, masked language modeling and next sentence prediction, right, for pre-training. GPT basically uses auto-regressive decoder, right? It basically does next word prediction kind of pre-training. Okay? What BART does is basically it does pre-training by doing the following. It corrupts the text with an arbitrary noising function. We'll talk about what that arbitrary noising function is. Okay? So it corrupts the input text with some arbitrary noising function, but at the end, it wants to reconstruct the original text. Okay? So as you see, here is some noising being done on the BART side. So what does BART do? BART basically, corrupts or adds noise to the input. So here it has basically deleted B and D tokens. But the output, it expects it to generate the full output. Okay? So that's that. So, and let's basically talk about what kind of noising functions BART uses. Okay? BART uses any of these 5 different noising functions. So if you basically have this as the input, there are 2 sentences, A, B, C dot, D, E dot. Okay? You could do any of these. You could basically do token masking. So basically, you masked out a few tokens here, B and D. Yeah. You could do token deletion. So basically saying just delete the tokens. Okay? Just delete the tokens, basically meaning the model has no information about where the tokens have been deleted from, right? Because when the model sees the input, it just sees the input. Okay? It doesn't know where the tokens have been deleted from. Okay? Or do sentence permutation, basically meaning if there are 2 sentences in the input, you could basically have the second sentence come first and the first sentence later. Okay? Or do document rotation. So as you see, it has been rotated. So basically the document actually starts from here and then A, B, C, D, E. So that's that. Or do text infilling. So essentially, this is very much like a token masking, except that sometimes these spans could be multiple tokens rather than one token itself. Okay? Rather than one token itself. Okay? So there are several of these noising methods. And what BART does is to use all of these different kinds of noising methods, any of these noising methods for any particular sample. It randomly chooses a noising method, gives the noisy input as the noisy text as input. And on the output, it expects a noiseless output. Okay? On the output, you want to basically get the original noise-free output. So that's how BART has been pre-trained. Okay? That's how BART has been pre-trained. BART model became very popular because it could do very good summarization. So essentially, remember for summarization kind of scenarios, of course, you can just use a decoder-only model, but typically an encoder-decoder mod setup makes a lot of sense. So encoder-decoder setups typically make sense when there is a semantic difference between the input and the output for your sequence-to-sequence learning setup. You know? So when you just say, hey, complete this text, like in auto-completion, the encoder-decoder setup is okay, but not really needed. But when you talk about question answering, or you talk about summarization, the input is a document, the output needs to be a summary. So there are semantically two different things. And there, these encoder-decoder setups become naturally applicable. Okay? So that's BART. So BART is effectively a bidirectional autoregressive transformer model, where the idea is to add noise to the input and expect the output to be generated in a noiseless manner while doing autoregression as well. So in the sense, you still have the shifted outputs being provided as extra inputs. Okay, so that's BART. Now, the next one is this T5 model. And again, these models are super popular, but there are, of course, other models which came up which didn't really become so popular, but these are super popular. T5 again comes from Google. So basically, it's called T5 because there are like 5 T's in it: text-to-text transfer transformer, right? And they basically said that, hey, whatever be your text, whatever be your task, we will express it in terms of text. And through the T5 model, Google's goal was also to learn a generic model which does not really need specific fine tuning. Okay? So they also wanted to come up like, hey, I also want to have like a single model which can decide what task needs to be done based on the prompt token. So just like OpenAI came up with this philosophy of prompting, starting from GPT-2, they also, I mean, it was almost the same time period. So they also wanted to have prompting. So they also said that, hey, if I have to, train the model and test it for translation purpose, I will add these tokens, translate English to German. For grammar check, I'll add these tokens, Schola sentence. For sentiment check, STSB sentence 1, and so on. So they said that, hey, for various kinds of tasks, I'm going to add special kinds of tokens while training. And then for those tasks at testing, I will have only one model. And depending on the prompt token that is provided, the model is going to do that particular task. So treat every NLP problem as a text-to-text problem. Take text as input and produce new text as output. Any problem will be text-to-text problem. Even if it is a regression problem, it must generate the number. Sure, I mean, generate it as a text. And when it came up, of course, I was like, I found it really awkward that you're generating numbers using as text in that senses. And is it really going to be as accurate? Now, of course, this was 2019, 5 years down the line. Clearly, you can generate numbers also using GPT, right? And very accurate numbers at that. So it can actually do reasonably accurate maths as well, involving several digits. Right? So T5 was pre-trained using a C4 corpus, the colossal clean crawled corpus. So this is again a corpus that these guys introduced when they introduced the T5 model. So that's that. Basically, we'll see how it is pre-trained on the next slide, but it could be used for various kinds of tasks, whether it is classification tasks, generative tasks, regression tasks, and so on. Okay. So in T5, they questioned, even BERT, as in why use 15% of your tokens to be masked, why 80% of them were actually masked, 10% replaced by a random word, and 10% not touched at all, right? So they tried out all kinds of corruption rates or masking rates in that senses. Okay? The T5 paper was a very interesting paper. So it basically had very huge number of details about hyperparameter tuning. So actually talked about why a particular number, why a particular percent of masking of the tokens works, which pre-training strategy works and not. Right? Somebody asked, right? Hey, are there more pre-training functions? You asked. You asked, right? Yeah, see, here, T5 folks basically tried out several of these pre-training choices, multiple functions. I already talked about some of them on the BART side, but there are more things that these guys tried out. So let's see how T5 tries to add noise to the input text, and then of course ensure that on the output side you get back the original input. That's basically the way T5 is pre-trained. And remember, whenever you're adding noise to the input text, it's not like you need labeled information so as to get back the original text. The original text you already have. So this is self-supervised, right? No extra annotations required. So in T5, in one of these random spans kind of masking, the original input is this: thank you for inviting me to your party last week. Okay? the actual noise wala input, the input with the noise looks like this. Okay, you first decide spans to be masked. You no longer mask out just words, but spans, multi-word spans, multi-token spans, more accurately. Okay. So, for example, in this case, for inviting is masked out. Well, in this particular case, just one token last is masked out. Okay. So first you decide 15%, or rather you decide a few number of spans. For each span, you choose how many words you want to mask out, such that overall it is like 15% of the words which get masked out. Okay. You don't really mask things, but you replace them with a sentinel token, a special token. So for each placeholder in that sense, for each mask, for each span, right? So X and Y in this particular case. And at the output, what you expect is not the original input, but at the output, you expect that it should tell you X is for inviting and Y is last. And then there's a special token Z to indicate end of output. Okay. Okay. So that's the kind of pre-training that they did. Rather than just doing particular token masking, they said that, hey, we'll do span masking. And rather than doing masking, we'll actually replace them with sentinel tokens. We'll tell the model, this is where you must replace something. But the model is supposed to figure out how many words were missing and therefore generate those words. Okay? So that's called random spans objective. So random spans as an objective, randomly decide where the span should be and how many words are being replaced by the sentinel token. But as you see, they tried out various other objectives like prefix language modeling. So input is thank you for inviting, output is me to your party last week. Now, of course, just split every sentence into two parts and do this prefix language modeling. You could do BERT style. So you could say, thank you for mask token, me to your party, Apple week. I mean, replace some words and mask out some words and so on. And then at the output, you expect it to generate the target text. So you could do several such things which are mentioned here. But what they found was that the random spans objective gives the best results. So therefore, the standard that they used for pre-training is just random spans. Okay, so that's how T5 model has been pre-trained. The random spans objective along with the C4 corpus with like 34 billion tokens. That's what they actually used to train the T5 model. Okay. Now T5 models basically are in different sizes. So the base, 5 different sizes in the original paper when it came out. Base model, small model, large model, 3 billion, 11 billion parameter models. Okay. Clearly they differ in terms of layers. So for example, T5 small is 6-layer plus 6-layer, 6-layer encoder, 6-layer decoder. Okay. Similarly, you see large model is 12 plus 12, and then there are these 24-layer plus 24-layer models. So 24-layer encoder, 24-layer decoder. But it's not necessary that the number of encoder layers should be the same as decoder layers. So there are people who basically use 6 layers in the encoder and just 2 or 3 layers in the decoder. So essentially, there are such asymmetric combinations as well. Okay? Asymmetric combinations as well. Okay? What you see here on the right side are various tasks. So results for various tasks. So when the T5 paper came up, of course, it was like a big deal. This was 2019, and OpenAI was still struggling to make its GPT-2 work as good as other publicly available models, while Google had already come up with this awesome T5 model, which was generic, which could do multiple tasks using one model, and it was really beating all other models. So across several tasks. So in fact, until 2019, Google was literally at the top of this AI game in that senses. They actually came up with BERT, which was at the top of the leaderboard. Then they came up with T5, which was really awesome. And post that, it was OpenAI in that senses, coming up with GPT-3 and later models, which are way better than any of the Google releases. Right? So that's that. So across multiple tasks, you would observe T5 11 billion parameter model just gave super awesome results, best results. Okay? It could also do completions really well. So you could basically tell it to fill in certain words. For example, this is an example taken from the paper itself, where I love peanut butter and what sandwiches. And you can actually control the length by telling it that, hey, generate something with this length. And it could actually come up with really good text in that sense. Is really, of course, there is hallucination. It's basically to the best that you could obtain in 2019. But it could really come up with really good results considering that time period. Okay, so that's all for this part, folks. Any questions about T5 BART? Yeah.
BART is missing selecting like essentially and similar that something similar happens but by an agent from the outside.
Yeah, absolutely. So in fact, there are also studies which basically try to figure out the robustness of these models to adversarial attacks or to noise. I mean, attacks may not be always adversarial. Sometimes it could just be noise in input data, right? So, I don't think there's a very, very conclusive answer to that though. I mean, although the pre-training objectives seem to say that yes, T5 kind of or BART kind of models should be good at that. But one can say the same thing about BERT also in that sense, right? You're masking some words and you're trying to guess those words and so on. So I don't think there is a very, very conclusive agreement on which models are basically best at handling those adversarial attacks. But there are pieces of work which try to figure out how robust a particular model is for a particular kind of a task and a particular kind of input perturbation. Okay? There are studies which basically say, hey, this is the degree to which it is robust. I mean, generalizing over those studies, I mean, honestly, I don't know. I mean, maybe there is a good generalization as well, but yeah, that's that. Hmm. Saptashi should answer that. Yeah, you know. Yeah. So basically, his question is, can these models identify that this text was generated by me? Yeah. And that is what Saptarshi and group have been doing for quite some time now. Trying to figure out whether something is LLM generated or human generated. Uh, uh, yeah. Go ahead. Yeah, watermarking in text is very complicated. That is the problem. So in images, it is easier because images have so much of flexibility. So you can hide a lot of things and watermark those images. But in text, it is very complicated. Yeah, so I mean, sorry, what was your point? Is useful for identification? I mean, it may not be, right? Because yeah, I mean, if you are a clever person, you can always add all of those profile attributes and ask it to generate appropriately, right? So that's that. So essentially, for example, I use that to solve my kiddos' homework sometimes, right? So basically, very recently, she was given a holiday homework. Create a poster of Birbal cooking khichdi, passing the message of water conservation. Now, what the hell, right? Yeah, I mean, to be creative, I basically just said create a poster like a 7-year-old would do. Right? And add all kinds of other qualifiers that you want to, and then generate a poster, and then have the kiddo copy. But so yes, I mean, it was partially ChatGPT generated, but nobody can claim it to be so, right? Yeah, I mean, being Copilot generated, but anyway. Okay. Any other questions, folks? Any other? Yeah, correct. It's still next word prediction. It is auto regressive because it's generating after all. Yeah. Huh. Pre-training is just this. Yeah, pre-training, I mean, for T5 model, yes. So for pre-training of, I think for pre-training of the T5 model, I don't, yeah, well, for the pre-training part, they did not really do any of that. For fine-tuning effectively, yes, they actually added special tokens for translation task and so on. Yeah. Pre-training was generic. Pre-training was as generic as just take the noisy text and try to predict the noiseless text in an autoregressive manner. Correct. Lot of variety of tasks. Yes, label data. Yeah. But exactly the point. It is not generic as that. Your instructions could be only based on whatever you fine-tuned it for. So if you fine-tune it for translation from English to German, then it works. But if you didn't fine-tune for English to French, it won't work. So yeah, I mean, those are the limitations. In fact, T5 was English only for that matter, with very few non-English tokens. And therefore, they came up with MT5, which was specifically trained for multilinguality. But again, I mean, it will only work. It only worked for kind of use cases which it was fine-tuned for in that sense. It was not a generic trainer like the GPT model. Okay. Good. So that's that. That's that part. Yeah, I actually had some half-baked slides saying, yeah, I mean, whether you want to do internships or the grant, essentially do email me. For applied, we always have applied researcher positions open. So some of you may be graduating soon. So please do send across your resumes if you want to be considered. MSR also has the RFs program, Research Fellows program, but it's a 2 years program. So essentially, it's ideal for people who want to do a PhD but don't know whether they want to actually do a PhD or not. So in that case, you can actually work in a research lab setting for 2 years and then figure out if you want to do or not, right? And lastly, remote collaborations are always welcome. So essentially, you are doing something interesting, and if people have bandwidth, and there's an interesting project, sure. I mean, I actually do a whole bunch of remote collaborations. Hey, is Karthikeyan around here now? Oh, you are Karthikeyan, okay. And yeah, there's a remote collaboration that I'm doing. Hey, good to see you. Yes, and we never met, so therefore I didn't even know that you are from IIT Delhi, working with Professor Mosam there. Yeah. So therefore, remote collaborations are also welcome. I just do it over Teams and Google Meet and so on. But that's that. Okay. Okay. So we have some time. Let me just spend some time on some applications. All of this I'll share with Mayank, and you can probably share with people as well. Okay. And then we don't have too much of time. So therefore, what I would do is just broadly talk about, let's say, a particular application. Maybe I'll broadly talk about first the broad thing that I do, and then talk a little bit about query auto-completion, and then we can call it done. We have probably half an hour now, right? So that's the time that we'll spend. Okay. So in school, everyone has done summarization, right? And that used to be one of the most boring things, right, to do. Given a large essay, just summarize. It was so subjective that even probably the teacher didn't know what to do there, right? But the teacher would always say, understand this, and then write in your own words. Now that used to be called as abstract. That is what is called as abstractive summarization, right? Oh, I mean, he can tell you more anyway. He's doing legal summarization. So that's that. But what we used to do was called extractive summarization. We would basically try to figure out important sentences and then just try to output them as part of summary in the budget that has been allocated. So 10 sentences, matlab 10 important sentences, and put in a summary. But today's systems can actually do really good job at summarization. So you can take input text of that kind. Sorry, somehow the pen does not seem to be responding. Anyway. Because I've not enabled editing. So, okay. So today's systems can actually take complicated text like that and generate really abstractive summaries, very crisp summaries, which capture the essence of the input text and give you the final outputs. Very popularly used for news summarization typically, right? Now, 5 years back in time, you could go to your favorite search engine like Google and ask, when was Modi born, right? And it will flash a good answer directly. Okay. But you couldn't ask questions like how many rivers in Brazil are longer than Kaveri. So those kinds of questions were very complicated because that would basically mean that it needs to figure out how long is Kaveri, and then which are the rivers in Brazil, compare, figure out length. So those things are not directly supportable using, let's say, Sparkle queries on some knowledge graph. It has to involve a whole bunch of natural language understanding and processing. But fortunately, today's systems can take paragraphs from multiple web pages, and they can actually answer questions which are not answered on any single web page. So they can actually combine evidence across multiple web pages and then come up with a final answer by doing logical reasoning over these multiple pages, oftentimes used in retrieval augmented generation as well, right? So it can also tell you, in fact, what are the supporting facts on these web pages that were found so as to come up with a good answer. These are all good applications, right? Machine translation is yet another application, right? So essentially, in machine translation is a very complicated task. To be able to support 100 languages, 100 languages from and to for translation, you would really need 100 C2 language pairs kind of data to train such systems, right? Because for every pair of languages, you need like labeled data to train such a system. Fortunately, now we have these multilingual models which really don't need all of that. So and we can actually support such systems by just doing training using, let's say, a central language like English. You really don't need 100 C2 pairs to be able to do that. Thanks to the multilingual pre-training, many of these language pairs can be, or the models can be trained for many of these language pairs even without having labeled data across those pairs. Yeah. So that's that. Yeah, yet another interesting task which many of you probably don't know about is called ads copywriting. Yeah, it's a super important task in the ads world, where the idea is that if I'm an advertiser, and as an advertiser, if I have, like, say, 10,000 products or 100,000 products for bigger advertisers, and I want to put out ads. So I can put out ads on some ad exchanges like Google Ad Exchange or Bing Ad Exchange and so on. But to put out ads, I have to design those ads. So I have to have a design team which basically says, okay, this should be the picture which should be shown for this particular product. This should be the text. I do want to show the money, and I do want to show the company name as well, right? So what is the text that I should write? And of course, the objective function should be higher clicks, right? So I want to ensure that the probability that the person will click should be as high as possible. So now, fortunately, people can do automated ads copywriting. So given a product catalog, the systems which can automatically write ads. Okay. Of course, there are systems which can do automated machine reading comprehension. Given a passage, they can actually answer these questions. This is one of the interesting things, which stuck to me when I was reading one of these papers. I actually forgot which paper this has been taken from. But consider this as the input. Which sentence has the correct adjective order? And whatever English I learned in school, nobody taught me that there is a order for adjectives also that have to be put up before the noun. And there are two options: big, circular, pink, thigh, silver, driving car, silver, circular, driving, pink, thigh, pink car. I would have thought that both of them are equivalent. I don't know. Maybe I'm too old to learn, or my school didn't really teach me this English. But interestingly, the model outputs first a rule saying that adjectives have to be in this order: opinion, adjective first, then size, then age, then shape, then color, origin, material, purpose, and then the noun. And then it also says that yes, big is basically size, circular is shape, pink is color, and so on. And therefore, it argues and tells why A is the correct answer and not B. Okay? New things, new rules which I didn't even know existed. You can do other kinds of NLP tasks like creating lists. So imagine Zepto, Blinkit, or whatever you use. You point to some sort of you're reading on your phone some recipe, and you just want to say right-click order, and then it automatically creates basically a shopping list on Zepto or Blinkit and automatically orders that. Of course, you can verify the card before it orders. So that's basically something that you can do today. You can do multilingual generation as well. So generate stuff in Telugu or generate stuff in Spanish and so on. Okay. You can do title generation. So given a particular abstract, you can actually use it to come up with the title of the paper. right? Sometimes we do that as well. So at least ask GPT to actually come up with fancy titles, and then yes, modify them a little bit so as to come up with much more, more accurate titles. But that's that. In the ads world, coming up with keywords is super important. So why is that important? So when you see an ad, right? So let's say you're reading a Times of India page, Times of India, because, well, it has ads and ads and ads, right? Every web page has like crazy number of ads there, okay? So when you're seeing those ads, they try to make a lot of effort in terms of showing relevant ads, okay? Essentially, if you are reading some sports-related news article, they would show you sports shoes ads and so on, okay? To be able to do that, they need to understand the content on that current page. And it's basically like taking the current entire page cut text as a query and putting it on a database of ads. It's just that the query is so large, so you can't really, that's very complicated to query the database with such a large query. And therefore, what they typically do is to take selected keywords from those web pages and then actually query the ad database. So how to find those keywords is the other question. Now, of course, you can depend on the meta keywords which the web administrators put up when they're creating pages. But how many people have done any web page design here? HTML coding? So if you have basically put up, how many of you have ever put a meta tag in them? Right? Very few, right? And even if you have put, then typically it is the default thing, right? I mean, essentially you don't end up, really spending or wasting time adding those keywords there. So therefore, most of the web pages are actually with junk meta tags, if at all. Okay? So. So Bing has ads. I mean, Bing page has no ads at the top. At the Oh, MSN, yes. I mean, MSN, yes, but Bing is a very clean page without any suggestions as such. It's as clean as this. I don't know which one are you talking about. No, I mean, Bing is just like this. I mean, it's bing.com. It has to be the same for everyone in that sense. Yeah, MSN, I agree. I mean, MSN is basically, a portal for that thing anyway. I mean, so essentially, yeah, I mean, there are going to be a whole bunch of things here. And it's basically a news stuff as well, right? So it's like, it's not. Yeah, so this is not basically bing.com. So, I mean, if you don't know the search engine, this is not. That's true, but Google Scholar also the search bar doesn't mean it's Google, right? I mean, anything as a search bar, you can't say it's just a search engine. I mean, well, it's a search engine, but it's not the same search engine. Anyway, so keyword tagging, yes, you can do it automatically now. You can take web pages and automatically figure out important keywords. Okay. You can of course do chemical understanding. So imagine basically looking at this chemical and telling me its name. Now that is possible. Fortunately, I think this is from a paper called Galactica model, which was trained specifically for scientific use cases. So you can take this particular image and ask it to come up with the name, which is this methyl 2 cyclohexyl 2 2 dimethyl something something XYZ, right? So it can process those molecules and bonds and tell you the full name. Okay? So you could, so people have also been using this for several of those pharma tasks. So coming up with drugs, appropriate drugs for treating particular kinds of diseases. Like you can actually, so this has been typically a very difficult task because to understand a particular kind of a virus can be handled using a particular kind of a molecule. You have to first synthesize that molecule and then do the experiments, essentially, right? Now you don't need to synthesize. Fortunately, what you could do is just tell, hey, if I had a chemical with this amino acid sequence, right? What will be the, what will be its properties, or can you come up with a description for it automatically? So even before synthesizing, you can actually ask this guy, hey, can you tell me what will be its properties so that you can actually at least predict what kind of molecules are more promising, and then spend energy in terms of really manufacturing them. That senses, right? Explaining code, of course, you can use these models. There are code-based LLMs as well these days, which you can use so as to understand what this particular variable C is doing in this code, or use them for completion. So on the left side, of course, you're just seeing a ChatGPT demo, but big deal. Some of you might be using GitHub Copilot, which allows you to automatically generate large pieces of code. So you just say draw scatter plot and actually fills up all the remaining parts. Similarly, for Twitter, you can basically just say, I want to fetch tweets from the user, and it generates all of that, in some ways templatized code in that sense. Right? Any of you used GitHub Copilot? Many of you use, right? So you would surely know, without GitHub Copilot, now can you code is the question, right? I mean, so people who use GitHub Copilot, essentially it's just crazy, crazy fast, right? Crazy fast. Okay. I'll spend some amount of time just talking about query auto-completion because I work in that area. And yeah, so let's talk a little bit about what goes on behind that auto-completion thing, right? So this is what it is, right? Auto-completion. I mean, essentially, you type a few characters, FAC, and shows you Facebook, Facebook login, MICR, Microsoft, and so on. Auto-completions. Sometimes it also shows you entities if they are, I mean, if they are linkable to some entities, right? So if I wanted to search for deep learning, I would type D and then see the results. I don't like them. There's no deep learning. So DE, I don't see deep learning. And then finally, yes, I hit luck. Yeah, there is deep learning. And then I stop as a user. So technically we call this as a prefix, and this as a block which a user sees. And this entire thing is a conversation. It's like a conversation going on between the user and the system. Where the user is typing a character at a time, and the system is showing some results. Okay. So sorry. So then so interestingly, the system looks so simple, but it's actually pretty complicated. So there are many blocks which enable this drop down. Okay. So I mean, what you want to do is to rank suggestions. The first thing is where you get these queries for showing in the drop down. Well, these are queries that people have typed in the past. So just you just make use of those queries. You just reuse those queries. Okay. That's also a problem, right? Is it personalized or not? So you, of course, want to do personalization to a certain level, right? Yeah, that requires data of the user. And yes, I mean, sometimes you have data for this particular user, right? So you are several times logged in onto Google. So Google knows who you are, right? Many times you are not logged in into Bing, but we know from the cookie who you are and so on. Okay. Yeah. So personalization can be done. Sorry. Yeah. And typically we also know in general what did you browse. So even if you didn't search, typically search engine companies also have browsers. So essentially Google has Chrome, Bing has Edge, and so on. So based on the browsing data, we know who you are in that census, right? So so it can be personalized. Then there is, of course, the first thing that you can do is to show most popular completion. So people typed F for Facebook, show Facebook at the top, right? Time-sensitive suggestions. So many times you want to show certain suggestions in certain periods of time. Like in the US, on weekends, if somebody typed DI, you would show Disneyland. But on non-weekends, you may show something else with DI rather than Disneyland, right? On weekdays, you may show something else, right? On 13th of February, somebody's typing V, yeah, show Valentine's Day gifts at the top. But on 15th February, stop showing that, right? Nobody cares for Valentine's Day gifts on 15th February, right? So time sensitivity is important. Location sensitivity is super important, right? So essentially, here you type IIT, you should see Gandhinagar at the top, but go back to Hyderabad, you don't see Gandhi. I mean, why should you see Gandhinagar at the top is the question, right? So that's that. So location sensitivity is important. So you could, of course, make use of popularity as a data, popularity as a signal to show things in the drop down. But you could also make use of session co-occurrences. What does that mean? That if your previous query was XYZ, then maybe your next query should be something. Okay? So essentially, although that is not very popular, but the popularity, the conditional probability is very high, right? So essentially, let's say you searched for Indian prime ministers, and then you typed basically N, you should just see Narendra Modi, right? Although with N, maybe Narendra Modi is not the most popular query, but since your previous query was prime ministers, you would basically want to suggest Narendra Modi because the probability of Narendra Modi coming up after Indian prime ministers is super high. Okay. So sometimes users also type spelling mistakes, right? So essentially people type in, this is how my mom would type WhatsApp, right? WATS and then app maybe, right? So now, you may or may not have completions for this kind of a thing in your query logs. Okay? Several times you have them, by the way, because several people make these frequent spelling mistakes anyway. So in some ways, you're redefining the name for WhatsApp as WATS APP, big deal, right? And therefore show them. But remember, I mean, users making spelling mistakes while typing is acceptable, but Microsoft making a spelling mistake in showing suggestions is not acceptable, right? So therefore, even if there is some things that match in the try, you would not want to show WATS APP as a suggestion. So, so being able to resolve those spelling mistakes that users make and still show the correct suggestions is something also that one needs to take care when designing such systems. Okay. Handling defects. So, I mean, now if you're using NLG models, they can come up with completions like Deepika Padukone is a monkey, dances like a monkey, right? And then you don't want to show those though. So you have to somehow still ensure that any offensive or complex suggestions like this don't turn up, right? So for example, somebody may actually do even more complex offensive queries like, did Bill Gates fund COVID? अब इतना तो बोल दिया तो अब आगे क्या होगा, like Bill Gates fund COVID research and so on. You may want to show that because several news articles are talking about that, but you don't want to, of course, show that, especially from Microsoft, right? So that's that. So how do you handle these defects? And sometimes there are defects. They are not offensive, but they are just defects. So for example, things like partial completions. So where can I find? So the user just typed where, and then you show where can I find in the drop down. Now that doesn't work because the user is expecting some complete suggestion rather than a partial suggestion. Okay? So how do you handle those defects? What do you do with non-prefix matches? So the user typed something and there's nothing in your previous query log, right? That matches with what the user typed. What do you do then? You show nothing, right? So basically queries like travel from name some not so popular place, like travel from Shillong to Sen, and you want it to complete Francisco. Now, very few people ever search for travel from Shillong to San Francisco. There might be someone from Shillong here, no offense, but it's just that very few people search for that, and therefore you will not find things of that kind in past query suggestions, in past queries that people have done. And therefore, and sometimes you can be very limited just because Bing does not have a very good presence in India. I mean, in India, probably, the Bing search query log is very, very sparse. So many times you don't really have good matches. And then what do you do in those cases? Okay? So in fact, how do you even index, previous query logs? So, all of you must be knowing about the trie data structure. Must have heard at some point or the other trie, T-R-I-E, trie data structure. So you index those query logs in tries. But then how do you basically support quick matches on such trie data structures? How quick? In terms of latency, you have to compete with users' typing speed. So that's that, right? That's the speed at which you want these things to work. I mean, of course, incorporating internet latency and so on as well. Okay. When things don't match, then maybe you want to use T5 kind of model, some generative models to generate things, to fill in those gaps, right? Recall gaps. The things don't match in the previous query logs, you want to generate suggestions. So using some NLG methods. Okay. And then when you want to do them on web search versus search on mobile phones, searches within enterprise, you may want to come up with a different experience altogether. For example, on a desktop, if somebody is searching for F, you want to order the suggestions based on popularity, with the most popular one at the top, the least popular one at the bottom. But on mobile phones, maybe you want to reverse the ranking because essentially on a mobile phone, the typewriter is right at the bottom, and it's much easier to click the last suggestion than the topmost suggestion, right? So you may want to redesign the systems in a very different manner when it comes to different form factors like mobile phones or other kinds of settings like enterprise settings, where the data could be authentication related. So for example, when I am trying to, let's say, build some system for search within Microsoft, I don't want to use Satya Nadella's search queries to show drop-down completions for normal people like me, right? So because some of those queries can be very, very confidential in nature. So then for enterprise query auto-completion, there are different kinds of constraints that one needs to care for. Okay. Yeah, so, and then there are details. I mean, there are details about how do you do those then, right? Essentially, the simplest way of ranking is, of course, ranking using popular queries, wisdom of the crowds kind of a solution, which is good, which works most of the times, except that you have to also care for language-specific popularity. You see, several times you don't know what is the language the user is typing in. So for example, in India, everybody sets their language as English. but people don't always search in English. I mean, people search in Hindi, in Telugu, in Tamil, in whatever, transliterated into Roman script. You know, so you have to guess the language so that you can then do an appropriate completion based on the language the user might be typing, and based on just a few characters that the user has typed. So the user might have just typed 3 characters. Of course, the user starts by typing 0 characters, but you want to guess the language and then suggest a completion. Yeah. Yeah. Yeah.
It's like whichever is the highest hit, whichever gets the most, that comes in the big day. So, but the thing is, then how then give some context for the so then if something has recently happened, but it has like very popular, like some accident has happened, but that has been high popular, then that won't show up. So you want to check wherever there is there is a high slope of searches, that's small amount of time.
It's called burstiness. Yeah.
But like it is festival breaks, someone so we most of it like Christmas. But if there's an accident on the Christmas day, like the Christmas accident, so there is this conflicting interest, conflicting the ranking. Rank these things which are how to decide this thing should be above this should be below because
yeah.
It also rank also when we something that we do ranking, we need to re-rank it because this is there some populated algorithm.
I mean, well, some things are basically, not copywritten, but more proprietary in nature. In that sense, is probably not even patented because at some level, even patents are public, by the way, right? I mean, so that's that. So but the way people do these kinds of things are based on personalization because some people actually do care about looking at. I mean, of course, there needs to be some re-ranking, right? But what should be the objective for re-ranking is the question. I mean, you cannot really say that always showing trendy things is the best thing to do. Or always, I mean, who will figure out what is the golden data? Right? So golden data is decided by clicks. If the users clicked, then that must be really good. If the users did not click, by the way, that doesn't tell that the user did not like it. It's just that they never saw that. Maybe they just kept typing and typing and typing, right? So who decides what is the golden ranking? Well, it's the user clicks. At least the positive feedback is good. And then when you want to learn this ranker, you have to basically decide, use a lot of signals, including the personalization. So including what this particular user likes. Many users like to figure out trending things and they will click on them. Many users don't want to see trending things and they won't click on them. So you have to basically also use user features and decide how to train this ranker based on click data. Yeah, it could just be a simple regression, right? So simple regression, just trying to come up with a score for every candidate that comes through the pipeline.
Some people decided on what profession they are. Some people decided which website it is.
Absolutely, we can only use those features which are available to us. I mean, their profession is not available, so we can't use it. Totally agreed. I mean, yeah, there could be things that we cannot do, and therefore, many times you may not like those drop-down things, and so be it. I mean, we just try to do what we can, right? So essentially, if you don't have that data, you don't have that data. That's right. So yes, so basically there is a user persona which is maintained, and that user persona is actually used to do personalization based on the cookie or the login. Yeah, it will basically not personalize for you, as simple as that. That's right. So I mean, essentially, see, personalization is always done in a short-term manner. So essentially saying, because user interests keep changing in the long run anyway. So typically, if you delete the cookies, sure, I mean, but it will keep setting it again. You keep deleting, sure, I mean, and in that case, you probably want to use DuckDuckGo, right, which is known to not use user history at all as a search engine. Yeah. Okay. Okay, folks. So that's that, and I think it's time as well. Maybe we can talk a little bit more in detail. But I mean, there are more details. But rather than this, if there are more questions, maybe we can take that up. I mean, in fact, there's a 3-hour tutorial that I did at several places last, I think, a year back or 2 years back. So there are those videos and slides as well on this topic. Oh, privacy is a factor. Absolutely true. So what we typically do at Microsoft, at Bing, I can talk what we do at Bing, right? So we delete all of those queries which occur less than a number of times in any region. So in a particular region, let's say in a particular country, if less than 10 users queried for something, we delete those queries, right? We also, of course, delete things which get associated and the user does not like them. So examples of such things are, Adam Smith suicide. So somebody types Adam Smith and we show suicide, and this guy is like, "Why the hell are you showing that?" Right? And now Adam Smith is a very common name. We won't do anything, even if somebody tells us to do that. But if there is a very, very unique name, right? And 10 of your friends basically decide to basically just query, and our threshold is 10, then we'll start showing that stuff, as soon as somebody types your name in that senses. It could be any nasty stuff, right? Supreme Court case, Manish Gupta Supreme Court case, and so on, right? So people don't like it. And then we basically have systems which can automatically take that feedback and just delete those things from our logs in that senses. But there are other privacy guidelines as well. So I mean, in fact, whenever we do anything at Microsoft, we have to get approval from our privacy board internally. For example, usage of this kind of data from browsers and usage of data about your historical query logs and so on. So all of that has various kinds of restrictions. So in certain countries, you can surely not do that, and we don't do that. So for example, in China, it is heavily regulated. In Arab countries, again, it's super heavily regulated. So the kind of, and then the definitions of what is offensive or not also differs from country to country. So there are crazy number of policies basically which have to be applied. Yeah. Sorry? Okay.
Where they say that the personalization is done only on the mobile device. And just show this parameter that's made.
Yeah.
That a possibility that's been explored or that's not possible.
Yeah, I mean, so what did you say in the beginning? Google uses federated learning?
Yeah, Google feedback. They claim that it's federated learning.
Yeah, it's better they claim that, right? Because I also don't know what do they do. They may claim that. Well, I mean, I think, so, every software for that matter actually has settings. So when you go to Google, there are settings to basically say use my history or not. Okay. Similarly, when you install Chrome, there is a setting which says use my history or not. So essentially, the user has basically denied usage, then we clearly don't use stuff. But if the user has allowed stuff, then sure, we use stuff. That's that. Federated learning is possible only in certain scenarios. I mean, in many, many scenarios, it's just not possible. So it's just difficult to do that. Yeah. Okay. And I can tell you 100%. Well, I mean, this is recorded, so let me not tell you anything. Anyway, go ahead.
There is an article. You said about feedback. You check those feedback if that is not working. So there is a human behind that feedback, or if
several times they are human systems, several times they are automated systems. So yeah. No, not really. I mean, many times it is basically human evaluated. Many times we triage using automated systems, but then final step has to be taken by a human. For every single feedback that we receive. Exactly. Yes. Yeah. Seriously, that is being done. We may not be doing it for 100% of the cases in the sense that we don't triage everything, but whenever we take steps, we typically have a human in the loop. We have basically several vendors which do this. That's right. Yeah. Yeah. Absolutely. Yeah. See, I mean, certain times. So, for example, trending topics matter when the user has just come on the search box and not typed anything. So, if the user really wants to find something that is trending, that's a bad thing. So, if something is trending, as soon as the user clicks, you just show in the drop down. And then after the user has typed, typically the probability that the guy will click on something that is trending is very low. So then you don't show trending stuff anyway. Yeah. Yeah, absolutely. But then you have to weigh, I mean, whether you want to show the trending thing or you actually want to show something that is very popular for a long period of time, right? And again, what do you show when you are showing trending is also important because let's say that, how do you say something is trending, right? So, I mean, you cannot wait for enough queries to come in to be able to say that something is trending. Let's say a very big accident happens. Now, before people actually start searching for it, you want to show it in your trending. And how do you show that? Well, some of the things that we do internally is we take news headlines and essentially ask GPT to generate synthetic queries and populate our trending cache. So even before people have actually done those queries, we figure out, oh, this is trending, news article. Let's basically just start showing trending things. So, and then you need models to do that. I mean, you have to wait for, I mean, but how else do you know the news anyway? I mean, using online news articles. And we keep receiving news feeds anyway. So, yeah. Yeah. Absolutely. Absolutely. Yeah. So systems are complex. You have to care at the language and region level, and then essentially figure out whether this user understands this language or not. You don't want to show Telugu to everyone who is in Telangana, but yes, I mean you can potentially show to some people who have a history of searching in Telugu as well. Right? And there are more complications. For example, you want to show Hindi queries, but you don't want to show it in Hindi script. Who types in Hindi script? Devanagari script, right? So, but potentially, if you wanted to, you can actually show. So, in fact, Google also keeps doing these experiments. Several times, you go there and you'll find, especially if you try to type something like Gokul and so on, you will actually see in Devanagari script, aisa likh ke aayega. And then, but many times if you are in Hyderabad, nahi aayega wo Devanagari script and so on. So you will keep experimenting with things, but there are all of these complicated choices, right? Uh-huh. Hmm. Oh, yes, we do a whole bunch of anonymization or what we call as scrubbing on the query logs. So even if some query passes our filters of more than, let's say, a few number of times, credit card numbers, PAN card numbers, all of those are scrubbed off. So, but that's the basic rule of storing query logs. I mean, we don't store query logs with any of that information ever in any of the pipelines, essentially, without scrubbing off stuff. So that basically gets done as the 0th step anyway. Yeah. Okay, so well, anyway, I mean, there is a whole bunch that you will go through. This is just the second day of the summer school. Hope you are liking it. Yeah, I think, I mean, 10 more days. 10 more days, and I'm told that Saturday is also not allowed for you to go around. So Saturday is also a working day for you. So all the best and have fun. Have a lot of learning here. Build new friends. And I would basically just say, if you don't have a WhatsApp group, just make a WhatsApp group so that you stay connected with each other, right? Because that's going to help a lot in the long run. Yeah? Okay? Otherwise, I think we'll stop here. As